Hello and welcome to this lecture on the course scope and the structure of the course. So what are you going to learn? We are starting with a section on the introduction. This is the one in which you see this video. Then we are going to dive into natural language processing with some early steps in this direction with some introduction. After that, we are going to see how we can apply some pre-trained models to our needs. Then you will find out how to fine-tune a model in a case where a pre-trained model might not be enough for your needs. Afterwards, we are going to cover some very interesting lecture on vector databases, and subsequently, because it's very much related to this one, we're going to talk about Retrieval-Augmented-Generation, RAG. In the section after that one, we're going to dive into OpenAI and ChatGPT and GPT 3.5 and GPT-4. And all of these different areas, vector databases, RAG and OpenAI, will be bundled then in some capstone project in which we are going to develop a chatbot. After that, we are going to see some more advanced topic, which is relevant when you want to train your own model. And this lecture or this section is called data augmentation. So you will learn how you can adapt the data that you have and augment it to improve the performance of the model. Then the next topic is on open source LLMs. So in contrast to OpenAI and Google and all the other ones, there are also some open source LLMs which you can use, and I'm going to show you how you can apply them. And then we will have a section on prompt engineering. So here you will learn how you can define a prompt in the best way to get exactly what you need in the format that you need so that you are happy with the result and the output of the model. And that's it. Then in the final section, we are going to wrap up, and this is basically what you can see here, the complete scope of the course. So a really broad range of different topics all around NLP, and this is going to be a lot of fun. Then if we are inside certain topics, how is it then structured? We are typically starting with some theoretical background. I always call them 101 lectures. So in these PowerPoint slides, I'm going to explain you how a certain technique is working, and you will learn everything that is essential for the understanding of what we're going to do. And then we are going to apply this in practice. So we are taking the theoretical knowledge we have gained and work on a very specific problem that we have defined to get some deeper understanding of the concepts. And then also we will have some exercises and solutions in which you can become active and try to solve a certain problem on your own, and you can take a look at the solution that I provide afterwards in case you are stuck completely. Okay, this is what you can expect from the course. So there's really a lot of content, and we can start right away in the next video. Hello and welcome. Before we dive into the course, I really would like to introduce myself to you so that you have a better understanding of who you're dealing with. My name is Bert Golnick, and I have an educational background in aerospace engineering and economics. But nowadays I'm actually working as a data scientist in wind energy, and in this work I daily have to work with Python mainly, but also with R, with SQL, Flutter, HTML. So there's a large variety in the tech stack. And I'm also acting as an online trainer. I provide several courses. You might have seen my other courses before. I also provide courses on PyTorch and on specific subsections within PyTorch. And also I'm an author at Medium. You can find my articles there. And I also would like to be connected with you. So don't hesitate and reach out to me via LinkedIn. You can find my handle here. And these are the different ways in which you can connect to me. And so you have a better understanding of who I am. Thanks and see you in the next lecture. Hello and welcome. In this lecture I'm going to provide you some guideline on how you might work with the course, because that is depending on your level of expertise. If you're a complete newbie, you can work with the course in a different way than if you're already experienced with natural language processing. So let's take a look at that. Here we can see the different sections, and then I have separated these two different roles, and you can define whether you consider yourself to be a complete beginner in natural language processing, or if you already have a sufficient level of expertise, then you are a senior in NLP. If you are a beginner, then I would recommend to you and consider that mandatory to start with this lecture on the course introduction in which we are currently, and then after that one go through the NLP introduction and also work through the application of pre-trained models, and then the model fine-tuning, as well as the OpenAI topic and the prompt engineering. These can be considered freely selectable, so you can jump into these ones at any point whenever it suits you. The topics vector databases and Retrieval-Augmented-Generation are sequential, so that means that you should start with RAG, with Retrieval-Augmented-Generation, only after you have watched the section on vector databases before. And then, once you have done that, you can try to work on the capstone project on the chatbot. So that one should be only started after you have consumed the content on RAG. And that's for the role of the NLP newbie. If you are a senior, it's slightly different. I would consider only the course introduction to be mandatory, and then you might skip over the NLP introduction. I would consider that completely optional to you. And then a lot of stuff is completely freely selectable for you, but also the topics on vector databases and RAG, these are still sequential, so jump into the RAG topic only after you have consumed vector databases before, and then try to work on the capstone project, so that part is the same, but all the other ones are freely selectable for you. And you can jump into the different topics because they can be considered standalone at that point. Good. I hope this helps you to find your way around in the course and to get started in a smooth way. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now I'm going to show you how you can get the material. For that, please head over to my homepage, gornicdata.de, and once you are here, you can find out about my other offers, like other trainings I'm providing outside of Udemy. You can also book some direct meetings with me, some mentoring sessions, but you're here for finding out about the material. So please click here on this button, Material. And here you can see the material for the different courses that I provide. And there are different options how to get the material. I will just show it based on one example. You can click on the zip icon, and this will directly start the download. So now the file material is downloaded as a zip, and you can just open it and extract it to a local folder, and then you can work with it. That's one way. If you're more advanced and a bit more experienced in working with Git, then you can just click on the Git icon. So once you do this, you will be forwarded to this course page on GitHub, and then you know your way around. You can just click on code and grab the Git URL and then clone the repo, and afterwards work with the local repository. So these are the two different options. Again, please just head over to the material on my homepage. Then you find the different courses which are provided via Udemy, and then either you directly want to have the static zip file, and download that one, or you can directly get access to the Git repository and download the material from there by cloning the repository. Good, and this is what you need to get started and have the material on your local computer. Thanks a lot, and see you in the next lecture. Hello and welcome to this lecture. In this lecture I'm going to show you how we can set up our systems to work with the course. At first we need to have Python installed, so you can head over to this URL to python.org/downloads, and then I would recommend to you to use the same version that I have used when I created the course. So that's the one, Python version 3.11.6, mainly because the version 3.12, which was around nowadays, is not compatible with PyTorch at the time of the creation of the videos. So just stick with that version and you should be running in no problems. Then we are going to work with some virtual environments. It's not totally necessary, but it's very good practice to work with virtual environments, and you will see in a second why this is the case. So it's looking like this then. In our environment we are working with the installed Python version, and then inside our environment we are going to have all the different packages that we have installed. And then we are going to interact with the environment from Visual Studio Code. So this is my preferred editor, and I would recommend to you to use the same. But if you are familiar with a different one, no problem, just find your way around yourself. That's totally fine. All the examples I'm going to show are based on VS Code. And you can install Visual Studio Code from this URL. So you can just head over there and download it for the system that you're using and installing it. And then once you have installed it, you can see at the left-hand side some pane with different small tiles. And there is one for the extensions, the one which is highlighted here in red. And then you can add some extensions. So I would recommend to you to install Pylens and Python. These are considered to be must-have extensions, and some others are optional. I'm a big fan of GitHub Copilot because it's making my life a bit easier, but no need for this one because it's costing some additional money. You're totally fine if you don't have Copilot installed. And the other one is just for the styling. So I like the theme from Atom 1 Dark. That's my preference, but these two are just optional and you don't need to have them. Alright, and a quick reminder on environments. If you know all about environments, you can just skip this part. But if you don't, then here's a quick recap on why environments are necessary. Imagine that you are working on different projects. I typically work on a bunch of different projects at the same time, but then the different projects are possibly having some legacy and were developed over a long time. And maybe at that time of the creation of the first project, Python 3.8.5 was active, and then all packages which are installed with certain versions. And then if you want to switch to a different project and you install a different Python version, a more recent one, you might have a different version for this package XYZ, and then that's a mismatch. So you cannot have packages if you're just working with one shared environment in different versions, and you cannot have different Python versions. So here at this point you would run into some problems. Typically one of the two different projects would start to run into issues. So this is the reason why this is separated, and then you can have for each project a dedicated environment with all specific Python versions that are relevant to make it work, as well as the different package versions. All of them are then suited to work for this specific project, and everything is fine. So this is something that I would recommend to you if you don't work with environments yet. There are different environments. Also here, if you are an expert and you know about other options as well, you're totally free to go and use Poetry or Conda for your environments. But what I'm going to show you in the setup in the next video is how to set everything up with Venv. And then here is a quick recap on how you can set up a new environment with Venv. So you just have to run this command. We will do this in practice in the next video. And then there is a certain way how to activate the environment. So you need to be jumping into the environment, and you can see then indicated by the brackets, and inside the brackets you can see the name of the environment, that you are actually working against this environment, and every package that you are going to install is going to end up in this specific environment. So when you then run pip install with a specific package, then it's going to end up in this environment, and everything is contained and working in the way we are intending it to do. I don't want you to install every single package by hand, so there is a more clever way to do that. Here also a quick recap for most of you, I guess. You can run pip freeze to get an output of all installed packages in an environment. And then here is a short sample output. So then on the screen you would see the package name and the corresponding package version which is installed. And then you can pipe this output directly with the greater sign to some file. And typically it's done like this. You run pip freeze piping to the requirements.txt. And then inside the file we can see all the different packages and the corresponding package versions. And then if you want to restore the complete environment from the requirements file, then you can do that by just running pip install -r followed by the name of the requirements file. And then in a batch job, all the different packages are installed. And with this one-liner, you should be able to run everything and the environment should be ready to go. So this was a quick overview on how our system is going to look like, and we're going to see this in practice in the next video. Thanks a lot and see you there. Hello and welcome to this lecture. Now we're going to set up your system. First of all, we need Python to be installed on our systems. So please head over to python.org and then you can click on downloads and go with the most recent version. Or if you want to be absolutely sure that it's working exactly in the same way that I have created it, then you can just scroll down to downloads or releases. And I'm working with the version 3.10.11. So just scroll down a bit. So that is then completely the same version that I have used during the creation of the videos. So you might also just download that one and start the installation procedure. Just make sure at some point during the installation that you set the check mark that you want to add Python to your environment variables. So you want to add it to your path variable. That's important that everything is working, just to make sure that this is the case. And then this is the complete Python installation. Good, you can manage that. Then the next part is that we need to install Visual Studio Code. So you can just head over to code.visualstudio.com and open this link. And here on this page, you can just click on download and download it for the system that you want to use it for. Just install it and start it afterwards. So when you start it, it will look like this. And then you can just open the folder that we have created. And now we are inside this working folder. And this is the way how we are going to interact with the system. So now we are always working from inside this folder. And from here you can open the different scripts that we have created and work with the course. Good. Then the next part is that we need to install certain extensions. So inside VS Code, we just need to install these must-haves, pylons and Python. So let's head over here. We can find the extensions under this tile. And then all you need to do is you need to search for Python. Then we can see here the Python extension. So then there will be some install button and you can install that. And the other one that we need is pylons. All right, here it is. Same story, just click on the install button and it's going to be installed. Good, these are our extensions. And the next part is that we need to set up our environment. So for that, you can just head over to View and show the terminal if it's not visible yet. So then you can see here at the right hand side in the bottom part, the terminal. So in the terminal, we can just create our new environment by calling python-m venv. And that one is creating the folder venv in the working folder. And then here, all the different packages that we're going to install are going to be found. Now we only have to move into this environment. Otherwise, we would always work with the base environment. So we have to move into our venv folder, scripts. And here, if we're working with the CMD, then the corresponding activation function is activate.bat. If you would work with PowerShell, it would be activate.ps1. And if you're working with Linux, there's also another activate function, but we are using this one, activate.bat. And you can see that it works at the beginning. So the text inside the brackets is corresponding to the environment which we are using. Now every package that we're going to install is going to be found inside this environment. And it's empty for now. And we are going to install now all the different packages in just one batch. So here you can see the command for that one. It's pip install -r requirement or requirements txt. So that is what we're going to run. Of course, it cannot find it in the scripts folder. I have to move upwards again. And now I can install -r requirements txt. I just have to press enter and then all the different packages which are going to be summarized in this requirements txt are going to be installed. This might take a few minutes, just be patient, and then after that you are ready to start with the course. And that's it. These are the different steps that you need to follow to set up your system and being ready to work with the course. Thanks a lot and see you in the next lecture. Hello and welcome to this new section. In this section you will get some introduction into natural language processing, and this will be the foundation for the rest of the course. So here we will start with the understanding of word embeddings. This means basically that a computer or a model is not implicitly able to understand text, so it needs to have some internal representation of texts, and it's doing this with a concept which is called word embedding. So it's creating long vectors of numbers which are then internally representing texts, sentences, or just single words. So we will start with this understanding, and to get this understanding we will cover different concepts. One very simple one, which is, spoiler alert, not working, is called one-hot encoding. If you have some background in machine learning, you will know this concept before, but here, just as a brief reminder, you will have, for example, a column called color, and then in this column you have different expressions. So there are, in this case, 3 different distinct expressions, which are called orange, green, and blue. And then what one-hot encoding is doing, it's creating columns for each of these distinct expressions, and it's putting a 1 whenever this observation is true, and a 0 otherwise. So this is then the transformation which is representing the one-hot encoding. But as we will find out, this is not working. We will dive deeper and get some understanding of some actual model. This is one of the first models which was showing the value of NLP, which is called BLAF. And we will see how good this is working. And we will create some code which is taking different words from different categories and putting them into a 2-dimensional space. And this will show that the model is actually able to get the understanding of these concepts. Otherwise, all these different words coming from the category of algebra, for example, would not be clustered together. Here, with the different clusters which are formed for the different categories, we are directly able to see that the model is actually able to get this contextual understanding of the meaning of the words and the concepts. So this is our foundation on the word embeddings. And then afterwards, we are going to create some sentiment model. So we are going to take some text corpus. We are using some pre-trained word embedding model, extract the word embeddings, and create some neural network based on that. And we will see how good this very simple approach is working. All right, this is the outlook. This is what you can expect from this section. And now let's directly jump into it. See you in the next video. Hello and welcome to this section. In this new section, we are going to talk about natural language processing. And I'm really happy to be able to add this section because I wanted to do so for a long time already. But now it's here. We will start with some very quick introduction. So what is actually natural language processing, or in short, NLP? NLP is a specific field of artificial intelligence which is focusing on computers to understand, interpret, and generate human language. Of course, this one is including a lot of deep learning, and deep learning is used here to analyze and manipulate text and speech. And these deep learning algorithms are able to extract some very meaningful insights, and to be able to do so, it's requiring really large amounts of data. So it's really making use of large unstructured text data that might come from social media, from Twitter, for example. Later on in this section, we are going to deal with Twitter tweets, but also social media posts, Wikipedia, customer reviews, and so on. And in the end, there is really a wide range of applications. You know, of course, we have chatbots. By now, you will very likely have played with OpenAI, ChatGPT, but there are also the competitors around from Google. Google has also provided several models like BART, and Meta is also having some own models like Llama. So the zoo of different models is increasing nearly daily. And the field for which you can use it is really large. So we can use it for sentiment analysis, for translation of texts, for the recognition of speech, and much more. So how does it work? If we want to work or even develop our own NLP model, the flow is the following. We have certain text input. So we have, for example, the string, I like this book so much I cannot. And then this one is passed into a neural network, and there might be different kinds of predictions. So it could be that the next words should be predicted. So then it could sound like, I like this book so much I cannot put it down. It could be provided to some sentiment analysis, which is returning the polarity or the sentiment of the sentence. It could also be that you provide this to some text summarization algorithm, And then it could provide some return like this is a positive book review. Or you could apply this to some translation. So this would be the German equivalent of this text. But of course, there are some technical steps and some technical hurdles we have to take. So the problem is that we are working with deep learning, and deep learning can only work with numerical inputs. But here we have strings. So the main topic is actually how can we convert the words that we are using into some kind of numerical representation. So we want to put in this sentence, pass it into a network and get some prediction, but networks, like I told you, can only consume numbers and not text. So there is one additional step that needs to be taken, and this is the conversion of text into this numerical format. So we need to convert this into some numbers, basically a large tensor, and this is called word embedding. There are different techniques we will learn in this course, several ones, but usually the good ones are all based on neural networks. So in the end, if you're working with NLP, deep learning is involved in 2 stages of this process. It's involved usually in this step of the word embedding, and then later on this word embedding is used in the neural network development. So it could be also involved directly in the neural network. So then there is some kind of embedding layer, but you could also have it separate. You have the word embedding and then just fine tune some additional layers. But you can also use the embedding directly and pass it to some neural network. And there is a bit of vocabulary that we need to be aware of, because this is not the same kind of vocabulary that we are using in deep learning in general. So if we have, for example, some review, like I like this book so much, we need to pass it through a process which is called tokenization. And out of this tokenization, we get the following results. We get a list of different tokens. So basically all the different words are taken and separated. So in the most simple case, it's finding out that there is a space in between and then the words are separated, but there is more to it. So this is the first step of the tokenization, and there are different tokenizers that you can play with. Then the next term that you need to be aware of is the document. So we are starting with just one review, and if we have a complete sentence corresponding to this review, this could be called a document. And if you have a lot of different reviews and then of course a lot of different documents, then you take all the different documents together, and this is called a text corpus or just corpus. So these are some terms that you need to be aware of, like tokenization, document, and corpus, and that we need to get started. So to wrap up in this short lecture, we have started with the high-level introduction into NLP. You have learned what NLP is and what the main steps are in here and some important vocabulary. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. In this lecture we are going to talk about word embeddings. So in the last lecture we have seen the overview, and the word embeddings are the first step where we are going from the text corpus into the numerical representation. So we are converting in this step our words or even the complete sentences into numbers, and we are representing with this the different words as unique tensors in some higher dimensional space. And ideally, these word embeddings are able to cover the relationship from one word to another word. And in one of the upcoming lectures, we are going to actually create this graph that you can see at the right-hand side. So here we can see one specific word embedding. And for a given category, you can find some close words, which are actually calculated by the algorithm. And then we are going to visualize it here in this two-dimensional space. And we can see that these different topics or these different terms corresponding to the category are actually mapped very close to each other. So here this specific word embedding is able to capture the relationship between the words. And you can see here that the words which are similar are mapped quite close to each other. Usually there is deep learning involved in this step, but we are starting very simple and use some non-deep learning approach at the beginning. Good. We are starting always with a sentence, and then you can break it down. We spoke in the last video shortly about the tokenization. So the different words are separated in the first step in the tokenization, and then this one is corresponding to a tensor. So here we are going to have then a tensor with different numeric values. But how do we do that? And there are different ways to come from this text world to the tensor world. So on a high level, we are having these different options. We can go with one-hot encoding. We can use some frequency-based approach, or we can use some neural network approach. We are starting with the most simple one, with the one-hot encoding. In one-hot encoding, what is done is that each word in the order that it's passed in is provided with some index. So we are starting with 0, and then we have an index for each and every word. And what then is done is that we have the index and we have all the different words. And then for each word, there is one specific one in this row, which is corresponding to this index. So here, if we are just starting with this sentence, then we would have here a 1 at the position of the it, then a 1 for the was at the position 1, and so on. And you can imagine if there would be a different sentence, then we have here on the top all the different indices corresponding to the complete vocabulary in all sentences. And then for the specific words in the sentence, the ones are mapped wherever a word is counted. So this is very simple, but simplicity comes with some problems because we are getting the curse of dimensionality. Here we are having as many columns and rows as we have words in all different sentences. So the matrix that is created is very sparse. That's not the problem, but it's super large. That is really a problem. So even with a very small data set, you can run into memory problems. So this is the biggest problem. And the next problem is that there is actually not much embedding here. All the words are isolated from each other, and the distances between the words are similar. And the algorithm is not able to find out which words are actually similar. So these are the biggest problems, but to have some starting point, nevertheless, we are going to implement it. Then the next type of embedding is frequency-based. And there we have different options like the count, which is very similar to the one-hot encoding. So here we are getting the count of the words in the document. Then we have TF-IDF, standing for term frequency inverse term frequency. Here this is based on the count of the words in the document and in the corpus. So words which are frequent in a document are considered important, but words which are frequency in the corpus are not that important. So this is the kind of logic that is behind this. And this is working better than this first approach. And there is some other approach called co-occurrence, which is getting the similarity of words in a certain way. In the next lectures, we are going to implement the first approach, the one-hot encoding, to have some baseline. And afterwards, we are going to cover the neural network-based approaches, which are much more powerful. So we are covering these ones after that. so that you have some scope of what we're doing in the next lectures. Thank you very much and see you there. Hello and welcome to this lecture. In this lecture we are going to talk about sentiment analysis with one-hot encoding. And here you can see the dataset that we are going to use. So it's a rather small dataset. It just has 27,000 tweets, so sentences, which are then categorized into different sentiments. So the sentiments range from negative to neutral and positive. And this is the dataset that we are going to work with. It's based on some Kaggle dataset. So here you can see the source of the data. And here is also some example of the text that we have, and then the corresponding sentiment. And what we are going to develop is the following. We are going to take all the texts that we have and we are going to one-hot encode all this data. So once we have this huge matrix of one-hot encoded data, we're going to pass it through a very simple neural network. So the classical steps are followed. We are creating the dataset class, we are creating the data loaders, and then putting it through a very simple neural network. And as a result, we get back this confusion matrix. You can see here that the performance is not perfect. So there are quite many misclassifications. And then in some later lecture, we are going to check if we get a better result based on some word embedding. But here we are just starting with the very simple approach of one-hot encoding all the data. And this is what we're going to implement in the next lecture. Thank you and see you there. Hello and welcome to this lecture. Now we are going to implement our sentiment analysis based on one-hot encoding. And since there is a bit more code, I'm not going to type everything and just go over it with you together. So I've opened here the file 25 sentiment OHE, standing for one-hot encoding. And as always, we are starting by importing the packages. So here we have the typical suspects. One thing special is the count vectorizer. This is basically our function that we are going to use for the one-hot encoding. So this is a feature from sklearn. So under sklearn submodule feature extraction.txt, we can find this functionality. Other than that, you cannot find anything new. Everything else we have seen before. So we can go to the next part. We are importing the data. So we are making use of this Twitter file stored in the subfolder data called tweets.csv. And we are importing it and it looks like this. Basically, we are focusing on the column text and the column sentiment. These are the two relevant columns to us, which we are using. And now, since we have imported it, we can create a new column called class. Because you know that PyTorch cannot use any text directly. It can only work with tensors, and we need to map the different sentiments to certain numbers. So to keep the ordering of the categories, I applied the following. Negative is assigned to 0 because the lowest class has to start with 0. Then a slightly better result is neutral with 1, and the best result is positive. So you can also treat this as some kind of regression problem if you want. But here I now implement it as some classification problem. So these are the different categories and IDs. And I apply this mapping here in this line and create this new column called sentiment. If we check that, we can see that the new column is created and we have the corresponding target variable in here. Then I define already here the hyperparameters which I'm going to use during the model training later on. So the batch size and the number of epochs. I separate the independent and dependent features. So the text column is ending up in X in the independent features. And we are going to use the newly created column called class for the target variable. Then we perform the classical train test split. So I'm using a lot of data for testing in this case. So I made the split at half, so 50% for training, 50% for testing. You can play with it and assign different numbers. And now we are implementing the one-hot encoding. So we create an instance of this count vectorizer, and then we are applying the fit transform method on the train data. And then we get back the one-hot encoded independent features for the training dataset. And we use this one-hot encoding and just transform it on the test data. So these are our objects. We can also check the results. Take a look at xtrain one-hot. So here you can already see that it's a really large matrix with 13,740 rows and nearly the same size for the columns. So it's really using up a lot of space. This is the main reason why the word embeddings are better in this case. So we keep in mind the size of this for later comparison. And we just move on. We can now use the data that we have and create our dataset class. Let's just call it sentiment data. And we pull in our independent and dependent features, use them as some internal objects, and we define the three different classes: init, length, and getItem. So completely normal things here, nothing special. We just create the tensors during the instantiation, and then we can easily define the length of the object. And for the getItem, we can directly use the index and pull out the corresponding item from the independent and dependent features. And also we can easily create our train dataset and our test dataset. And in the next step, we create our data loaders. So here we just make use of our datasets that we have created the step before, pull in our predefined batch size, and apply the parameter shuffle to be true as well. Here for the test loader, I use a larger batch size because it's still not a problem to put it into the RAM. So I can have with one batch every dataset covered. So these are our data loaders, and the model is quite simple. We just have one hidden layer. So we start with the number of features that we are putting in. Then we have one hidden layer, and then we directly go to the output layer. So if we stack it all together in the forward function, we have here our linear layer in the first stage. Then we have some nonlinear activation with our rectified linear unit. We put it to the next linear layer and activate it with softmax in the end, because we have three different classes and we want to get back the probabilities for each of these different classes. So log softmax is the activation function we are using at the end. Now we can create an instance of this model. We just have to provide the parameters. So the number of features is defined by the number of columns of our numpy array for the train hot, for the one hot training data, and the number of classes is 3 in this case. For the loss function, we are using the cross entropy loss, and for the optimizer, we are using AdamW. The W stands for weight decay, and in certain cases, it's supposed to work slightly better than the normal Adam optimizer. So we are going to use this one, and here is our training loop. So the train losses are created as an empty list at the beginning, and then we iterate over our different epochs. And then in every epoch, we are iterating over the batches which are pulled from the train loader. As always, we zero the gradients at the beginning. Then we make a forward pass through the network. As a result, we get our predictions, our log predictions. And these ones are taken as the first parameter of the criterion of the loss function and then compared to the actual results which are coming from the object y_batch. So with this we can calculate the loss, we can extract the current loss, and we can calculate the gradients and update the parameters. Then we append our current loss corresponding to the current epoch and print the results. Let's see. We just run it, and since the dataset is not too big, it's running quite fast. We had to find a batch size of 80. Let's see, yes. So even if your computer is not super powerful, it should be done within a minute or so. So I will just wait until this is done. Now we can check the progress of this and get back this result. So the losses are reduced quite nicely. It's actually in very nice shape, not much of noise in here. So we can check with the test data how good this is actually working on unseen data. So we iterate over our test loader and calculate our log predictions, and then we need to find out which of the 3 different objects in each row is the actual maximum. So we can get the current class. This is done with torch.argmax. So with this we can find out which of these 3 different objects is corresponding to the highest value. And now we can just reduce the dimension of this one and convert it to NumPy, so that we in the next step can calculate the accuracy score based on the created object and our test data. And then we put it into some answering sentence and round it. So we have an accuracy of this model of 63.6%. And we need to evaluate whether this is a good result or not so good result. So we need to find out what the naive classifier would provide. The naive classifier would just guess the most dominant class and always predict this one. So we calculate this one, and the naive classifier is at 41%. So it's definitely better, but there is definitely also room for improvement on this model. And hopefully our approach, which we are later going to implement based on word embeddings, is providing some better result. If we want to take a look at the heat map, we can also do that and show it in here. So this would be the heat map bringing together the predictions and the true values. So we can see that the majority of the data is on the diagonal line, so it's correctly predicted, but the off diagonals are having also lots of data. So yeah, we have 36% error, so this is a lot, and hopefully we can improve this later on. But in this lecture we have implemented a very simple approach on sentiment analysis. So we have encoded all our texts with one hot encoding and then created some super simple neural network model and created some classification model on this, and finally tested out how good this model is performing. And with this we have reached the end of our lecture on sentiment analysis with one hot encoding. Thank you very much and see you in the next lecture. Hello and welcome to this lecture. In this lecture we are going to talk about word embeddings which are based on neural networks. And here you can find some good explanation on what word embeddings based on neural networks are, because these are representations of words as low-dimensional vectors in the mathematical space, and they are able to capture their semantic and syntactic meaning. So this is the main purpose of word embeddings. Here you can see our overview of the different types of word embeddings. And the last part here on the top we have not covered yet. Now we are at the stage of doing this. So we are covering the neural networks, and there are different ones. We are having here different options. We have Word2Vec, we have GLAV, BERT, GPT, which you possibly know from ChatGPT, and many, many more. So this is just a short list, but there are hundreds of different word embeddings. And we're going to start with the first class here with Word2Vec, which can be actually splitted into two different types, because there is one approach called continuous bag of words and another one called skipgram. So let's find out how they are working. But before we go into the very details, on the high level, let's recap what we're going to do. We want to create this mapping so that the algorithm is able to capture the context or meaning and also the similarity to other words. And this is closely related to each other. Also, we want to reduce the dimensions because we have seen before that one-hot encoding is creating very large matrices. And with this, we also want to avoid some memory issues. So this approach based on neural networks is working like this. We are having our corpus, our neural network, and as a result, we get our word embedding. And the first class of algorithms here from this field is, as we have seen, Word2Vec, and specifically continuous bag of words. This specific approach was developed by Google in 2013, and it's working like this. So you're having some sliding window, and you're taking this sliding window and go over the complete text, and at every word at the position n, you consider the complete window, which is covering 2 words to the left and 2 words to the right, and then the word in the middle is our dependent feature. This is our target feature on which a model is trained, and the other 2 words to the left and to the right, these are considered to be the independent features. So what is done then is that the complete corpus is split up and the independent and dependent features are created. So at the beginning, if we have a sentence like "it was a bright cold day," then we can split it up. The first 5 words are "it was a bright cold." Then the A is in the middle, so this is our dependent feature, and "it was bright cold." These are the independent features. Then the sliding window is shifted so that now bright is in the middle and the surrounding words to the left and to the right are the independent features. I think you get the idea. So it's working like this. We have here a very simple neural network. We have the words which are passed into some embedding layer, and then the result, the output of all of these embeddings, are averaged, passed into some linear layer and some softmax activation to get some predictions, which are considered together with the true values in the loss function. So this is the complete approach of the continuous bag of words model. And the opposite is skipgram. It's basically the complete same approach. It's just putting it on top. So now the input is the middle word and the outputs are "it was bright cold." So we just take the independent and dependent features and switch it around. But the model type is completely staying the same. Good, that's it. So these are the 2 different options which we have in the field of Word2Vec. Then we have the next type, which is called GLAV. So this is one of the more complex approaches, and it was and is still a very popular approach. So GLAV stands for Global Vectors for Word Representations. It was developed by Geoffrey Pennington, Richard Zocher, and Christopher D. Manning in 2014. And here you can see the paper title, Global Vectors for Word Representations. And this one is based on the co-occurrence matrix of words in a complete corpus. And here the count is taken into account. So how often does a word appear together in the same context? So then a matrix of word co-occurrences is calculated, and then some matrix factorization is created to obtain the word embeddings. So the factorization is based on singular value decomposition, SVD, and we get a resulting embedding which is dense and in a low dimensional space. In the coding lectures we will see which different options we have here. And this one is able to encode the words as vectors of other words. And one nice feature is here that certain word analogies are possible and easily to be calculated. So this one is already showing that the algorithm is able to capture the meaning or the context of certain words. Another approach is called BERT, and actually BERT stands for bidirectional encoder representations from transformers. So we have covered transformers in an earlier lecture. So you can see transformers are taking it over. They are going into all the different fields from deep learning and showing their effectiveness. So this one was developed in 2018 by Google. And I'm not going into detail here. It's just that you know that there are different variants. Actually, a large number of different variants are available, like Roberta, Albert, Electra, and so on. And that you get a feeling on how large these models get. Here, this base model from BERT is having 110 million parameters and a file size of 440 megabytes. And this is just the base model. Then there is a large model, which is having 340 million parameters and a size of 1.3 gigabytes. So you can see that these models are getting really, really heavy, but also extremely powerful at the same time. And then just some words on another one that I've selected here, which is called GPT. So you will know this. This is the word embedding behind ChatGPT. So GPT stands for Generative Pre-trained Transformers. It was developed by OpenAI, and it's not strictly a word embedding, but some contextualized word embedding. And here the embedding for each occurrence of a word is based on the surrounding words in the text. So also this one is based on transformers, and here you can see the numbers for GPT-3. GPT-3 has already 175 billion parameters. So you can see these models are super large and heavy, but if you have played with ChatGPT, then you know already how powerful they are. So let's wrap up what we have learned in this lecture. In this lecture we have worked with word embeddings based on neural networks, and we have seen how they're working on a quite high level. In the upcoming coding lecture we are going to use one of them, GLAV, which we have seen before, and get some feeling on how to work with it and how to develop some model based on it. Thank you very much and see you there. Hello and welcome to this lecture. In this lecture we are going to talk about GLAV and how we can work with the GLAV embeddings. So at first we are going to import the packages, and I've created for this one file in the subfolder 360 NLP. And you can name it whatever you want. I just called it GLAV intro. And at the beginning, as always, we are importing the packages. So we are going to need only torch, and we are going to use torch text. Since this complete topic of NLP was added to the course quite late, it might not have been part of the requirements TXT at the time of your installation. So just make sure that torch text is installed. And we want to import only the submodule vocab as vocab. Good, let's run this. And as the very first point, we are going to import GLAV. There are different models from GLAV, and you can see this on the developer page. You can see it here. If you go to the Stanford page of this project GLAV, then you can see here the section of download pre-trained word vectors, and here you can see all the different files. We have GLAV in different sizes and shapes, so we are going to use this GLAV 6B model because it's the smallest one and easiest to handle for us, and the results are still amazing. So we are going to use this one, which is based on Wikipedia and GigaWord. It has 6 billion tokens and 400,000 words and also different embedding sizes. So we can use it with a 50-dimensional vector space, 100 dimensions, 200 or 300 dimensions. And you can see here there are even much bigger models. So you can see it also in the size of the file. They are increasing with size, but also the capabilities of the models are increasing. Good, how do we do this? We just have to make use of a specific function in this module. Vocab provides access to Claude, and we just need to provide here a name. And the name of the model is 6b in our case. And the dimensions, we're going to work with the 100-dimensional space. Let's run this. And if you run this for the very first time, what is happening is that the model is downloaded and you can find then a subfolder called .vector cache. Since the models are quite heavy, it's going to take a while. And then the zip files are extracted and you have the models available for later use. So the next time you just use it, you can see it was quite fast. We were able to load it quite instantly. So at first we can check the number of words and embeddings. So inside Claude, inside this object, we have now, for example, access to the vectors and we can check the shape. So this is the corresponding number of tokens. Here we have 400,000 and we have the 100-dimensional embedding space. Good, so this is the model we have imported. Now we can get the embedding for a specific word. So we are going to write a function for this, because later on we can use this a lot in different modules. And here we can just call it get embedding vector. And we are going to pass in a word as a string. So the first thing is that we need to find out the index of the word that is passed. And in Claude we have access to this via s2i, which is standing for string to index. We can just check it, s2i, add a specific word, woman, and then we can see what the index of this word is. And then of course we have the opposite direction, I to S, so converting from the index to a string. Let's just make the check. I to S. Let's take woman. We have the index 787 and here is the corresponding string again. So we have to map to the index and then back in the end. These are the two different options we have for this. So inside our function, we can now extract the index of the word by making use of this s2i functionality. And we just have to pass in the word. And then we can get the embedding. For this, we have in Claude the vectors. And here we just have to pick the element with the word index that we have extracted. Good, that's it. And then we can return our embedding. Let's just try it. Get embedding vector for chess. And then you can see that we get here this tensor. Let's just have a final check how this is looking. Here we have this 100-dimensional vector space. Another functionality that we're going to need is that we need to find out the closest words based on some input word. Okay, again, let's create some function for this. Get closest words from word. So we pass in again here some word, and then we want to have maybe the closest 5 words. So we specify here a parameter of how many objects should be returned. So the first parts are that we need to get the word embedding. So for the word embedding, we can actually make use of the function that we have just created. So here we can call get embedding vector and pass in the word that is passed. Now we have the embedding vector, and now we can calculate the distances. We are calculating the distance between all the 400,000 words inside Claude and compare it with the embedding for this one specific word. And for this we can make use of list comprehension. As a result, I want to get back a tuple where I have at first the word and then the distance from the word that is passed and the current word that is returned here. So we are going to iterate over all the different words inside Claude. So here we now extract all the words. Let's just check it quickly. All right, these would be our words. And now we want to create this tuple. So the first element is the word, and the second one is the distance. And we can make use of torch and the functionality dist. So with dist, we can calculate different distances in vector spaces. We are going to use the Euclidean distance, and we just have to pass in 2 different tensors. So you can see here the parameters. The first one is a tensor, the second one is a tensor, and then the parameter p is corresponding to the distance type. So 1 would be the Manhattan distance, 2 is the Euclidean distance. So we just go with the default here. So we can pass in our word embedding as the first parameter, and the second parameter is going to come from the embedding of the current word in the list that is iterated over. So we call get embedding vector on the current word, and then we have to cover a bit to make it work. So we need to get the current item and not use it as a tensor, but just as a numpy array. So we can call .cpu.item, and that should be it. Then we have our distances, and the last part is just that we want to get the top ranked distances. So we just need to sort it. And for this we can call sorted. We pass in our distances, and we can use some lambda functionality as the key, because here we have our tuple in the end. We have the word, and then the second element is corresponding to the index. So we want to use the second element and sort based on this. And then we want to filter it. So we don't want to have 400,000 results. We just want to have the top 5, for example. And then we have to save it in an object, dist sort filled, which we can return in the next step. Dist sort filled. And now we have our function for getting the closest words from a given word. We can check it just to see if this is working. Get closest words from word, and let's use, I don't know, chess. All right, there is a small typo. Oh yeah, I messed up the brackets. So here we need to close the bracket because this is what is going into the dist functionality. And then the last part, here we just need one less bracket, and that should be now working still. Okay, here is a W too much. Okay, now it's looking good. And now we can calculate the closest words. And in a few seconds, we will see that backgammon is very close to chess, grandmasters, Scrabble. Okay, so this looks quite reasonable. Great. And this is the main benefit of word embeddings. We have the similarity of the words, and they can be expressed as distances. And with this, we can implicitly see if the algorithm has understood the context of a certain word, because similar words are now much closer to each other. So this is great. And now I want to show you another very cool thing. That is that we are able to find some analogies. So we are going to use it in a way that we are providing the function with a given analogy, something like sister behaves to brother, like nephew behaves to, and then you would guess niece. And that is what we're going to check if the algorithm is able to find this out independently. So this is the kind of relationship that we are going to develop. So we are going to find word analogies. For example, let's take another one. King behaves to queen, like man to woman. And this is actually quite simple to implement. So let's create our function for this. Get word analogy. We are going to pass in several words. Word 1, word 2. In this case it would be king and queen. And the third word is woman in this case. And then we can also find the top ranked 5 words, for example. And the logic is surprisingly simple. So the logic is that we have the different words. Word 1 is, for example, the king, and so on. And the calculation is then that the different embedding vectors are taken, word 1, and from word 1, word 2 is subtracted, and word 3 is added. And this is then getting the analogy for the fourth word. And that's quite impressive that it's working that simple. So what do we need to do? We just have to pass in the different words as strings. And then once we have the words, we can get the embedding based on the helper function from above. And then we can put in this very simple calculation formula, and we get back a list of different words, which we then can just provide. Good. The first part is just that we need to get our word embedding, word 1 embedding, that is based on get embedding vector of word 1. And now we can just copy this a few times by pressing Alt, Shift and arrow down. Now we just have to slightly modify it. And now we can calculate our difference. And the difference is based on the formula that we have shown. Word 1 embedding minus word 2 embedding plus word 3 embedding. So this is now our result. We can also call it word 4 embedding. And to now get back, we just need to call our helper function, get closest words from embedding. So far we have only created this function for get closest word from word. Now we can just copy paste everything and create another helper function, find closest words from embedding. It's working very similar, so this is why I just copy pasted the code. Not the best style for copy pasting. I could also create another helper function and get the main functionality in there. But here I make it a bit simpler. So now we are not passing in the word, but actually the word embedding. So we can skip this first part and directly calculate the distances based on the given embedding, and that's all that we have to modify here. And this is what we're now going to make use of. So we calculate our analogy. So we can call our function getClosestWords from embedding, and we pass in our word for embedding. Good. And now we can return the result, return analogy, and we can check it. So let's call it get word analogy. And the first word, let's say we are going to use the example where we pass in sister and brother and nephew, and then see how this result is looking like. And actually, if you take a look at the page from the developers, then you can see this. So they have also created this kind of comparisons. So here you can see it. We have sister and brother and niece and nephew. And this is what the algorithm should provide. So if we pass in these two different words and then we get the vector spaces, and the algorithm should be able to find out that this pair is behaving similar to niece and nephew and should provide the corresponding word. Good, so the first word is sister. Now we pass in brother, and the third word is nephew. And now we can run it. So now all the different word embeddings are calculated, and the analogy is also calculated, and we get back the top results. So the first item is always the first word we have passed it in. We can forget about this one. The real results are starting here. So the closest analogy is niece, which is actually correct. But you can also see that the next ones would be granddaughter, which would be not correct. Also sister-in-law or cousin, but it's all making sense at least. So if the other results are not perfect, you could at least get some feeling why the algorithm thought these might be still close to these different analogies. Good. So this concludes our lecture on GLAV. What have we done? We have imported the GLAV word embedding, and then we have played around with it a bit so that we are able to work with it. We can pass in words and get back the corresponding embedding vector. We also worked on finding out what are the closest words. And also we were able to find out different analogies. So this concludes now our introductory lecture on GLAV. Thank you very much, and see you in the next one. Hello and welcome to this lecture. In this lecture we are going to work with GLAV again, and we are going to create some word cluster. And with this we are going to check the embeddings of the wording with GLAV. What we're going to develop here is that we are providing some categories. These categories could be like the ones I've shown here, algebra, music, numbers, and so on. And then we are looking for the closest words, which are corresponding to each of these categories. And then we are reducing the embedding space, which is having 100 dimensions, to just 2. We're using one specific machine learning algorithm for this, and then we're able to plot it, like here. And once we have done this, we can see here that the closest words which are found and which are corresponding to each of these different categories are actually mapped very close to each other. And this is showing us that the word embedding is actually working, and also the words that are found and which are relevant to each of these categories are making sense. So all of this is what we're going to implement now in the coding lecture together. Thanks a lot, and in the next lecture we are going to develop this together. Hello and welcome to this lecture. I've already opened the starter script. So the file is called 70 word cluster start inside our folder for NLP. And now I can hide this one. So we are starting by importing some packages. After we have done that, we can import our GLAV word embedding. Actually, if you want to play with a different type of word embedding, you can check it out. There are other ones. So you could just also use a different type. And once we have that, we can make use of the helper functions that we have developed before in our GLAV introduction lecture. So we are having here our function for getting the embedded vector given a certain word. And we are also making use of the function get closest words from word. So we are passing in a specific string, a word, and we get back a number of closest words to this one. Once we have that, here's a quick check. We look for the closest words to chess, and then we get back these different words in here. Good, once we have that, the rest is just classical Python stuff, not so much related to PyTorch, but nevertheless, it's quite cool what we will see in the end. So we are going to create a list of words, which is empty at the beginning, and we are specifying some categories also as a list. We have 400,000 words in GLAV, so you can use completely different words. I just go with these ones: numbers, algebra, music, science, and technology. And then I prepare some data frame. I will call it df word cloud. So this is a classical data frame where I have the category empty at the beginning, as well as the word. So this is just our empty data frame. And now we are iterating over all of these different categories. So for category in categories, we can just check every time that the category is printed to the screen. And we are finding the closest words for each run and for each category. So for this, we have the function get closest words from word. So we are passing in the word, which is the current category in the current iteration. Category. And how many do we want to have? Let's say we want to use the top 20. So this one is going to provide a list of 20 words in the end. And now we can create a temporary data frame having the same structure as before. We have the category. Here we just take the current category as a list and we repeat it with the length of the number of closest words. So we now have 20 times the current category, and the words, these are pulled in from the found closest words. So now we have a temporary data frame with these two different columns and the length of 20. And now we can concatenate this one with our word cloud. So the new word cloud is concatenated based on the old word cloud and the temporary data frame. And also we need to say that we want to ignore the index. So we can already run this. Now we can see that the current iteration is covering the numbers, and it's taking a while because every time it has to calculate the distances of the current category compared to all other words, and this is taking some time. And then the 20 closest words are found, and append it to the data frame. So once this is done, we can just check it. DF word cloud. Here we go. It's looking like this. I can see here I have a typo. I have birds and word. So now a new column was created. Let me just correct that. So actually here, this should be also word. And now we just rerun it. And then we will have the two different columns after that with the category and the word. All right, let's check that. Now we have our DF word cloud. Yes, so here we have the category and the corresponding words which are closest to the current category. That's looking all nice. And now the rest is just applying one specific machine learning model. Actually, I skipped the package import because I thought it's not super interesting, but here this one is interesting. This one is one specific dimensionality reduction technique, which is called t-SNE, T-distributed stochastic neighbor embedding. And with this one, you are able to reduce the number of dimensions drastically, because now we have 100 dimensions and we cannot plot 100 dimensions. We cannot visualize it and we would not be able to understand it. So with this cool technique, it's possible to reduce it to 2 dimensions, and then 2 dimensions we can easily plot. So this is what we're going to do here. So we have to prepare the data before we can put it into the model. So at first we need to get the 100 dimension word embedding for all words. So here we're going to create a torch tensor with the corresponding dimensions. So the number of rows corresponds to the number of words which we have here in our data frame of word cloud, and the number of columns corresponds to 100 because we have 100 different dimensions. So we could hard code it, but I always like to have it flexible. So the number of rows, this is coming from the word cloud shape at position 0, and the number of columns that corresponds to our graph dimensions. And these graph dimensions we have defined before. I've skipped that part at the beginning. Yeah, so there are different graph models which we can import, and there are 50 dimensions, 100, 200, 300. So I decided to use the 100 dimensional graph word embedding, and this is the parameter here, and then we pass it when the graph model is loaded. So we can make use of this parameter, and this is our number of dimensions. And now we can create an empty torch tensor, which we are going to fill afterwards. So torch.empty, and it's having the dimensions n rows and n calls. And now we just need to iterate over all the different rows. So for I in range n rows, here we can every time extract the current word. So the current word is stored in our data frame DF word cloud at a specific location, and the location is defined by the row with the index I, and the column is word. And then at the position I, and for all other columns, we are filling in the vector which we get by calling the function getEmbeddingVector and passing in our current word. So this way we are subsequently filling up this tensor. We can also check it and print the current state. So at the current iteration I, we are covering the current word. Let's run this. Good. So let's take a look at X. This is our tensor, and x has the right shape. Good. And now we are going to create an instance of our model. So the machine learning model we are going to use, as I told you, is called t-SNE. We want to plot it in 2 dimensions, so we have to pass the parameter n components, and this one is 2. And now we can extract here our parameters. So we just have to call this model t-SNE and the function fit transform. And here we can pass in our tensor x, but actually we cannot pass it in as a tensor, so we need to transform it to a numpy array by calling .cpu.numpy. And we can run it and check out the result. X t-SNE is looking like this. It's having 100 rows and 2 columns. So that's looking all nice. And now the rest is just a bit of data handling. We want to create a new column inside our data frame, df bird cloud, and the new columns are called x and y. So here we are picking the corresponding columns from our object x t-SNE. So, and we are assigning the right columns. And the residual part is just simple plotting. You can use a plotting environment as you like. I'm a big fan of ggplot, so I will use this one. I pull in the data, df bird cloud. And because here we have a lot of birds and often they are over plotted and hard to read afterwards, this is why I'm sampling it. So the result that you are having is looking a bit different, just due to the sampling that is taking place here. We need to specify the aesthetics. So we pass in the horizontal axis x, defined by x, the vertical axis y by the column y, and we also want to show the label. This one is corresponding to the word. So at the position, which is defined by the coordinates, we are plotting the word and we are coloring it with the corresponding category. Alright, the rest is just putting in the right geometry, meaning that we want to use geom text so that the text is shown, and we want to make it look a bit nicer. So we want to provide a title, and the title is GLAV word embeddings and categories. And here we go. This is our word embedding in 2 dimensions. So here we can see that we have, for example, the category technology, and in technology we are finding something like developing, computing, innovation, engineering, looking all good, and it's forming some kind of cluster here. So these words are quite close to each other. Let's check another one. Let's take a look at science. So for science, we are finding something like astronomy, biology, professor, science, study, or scientific, making all sense, looking very good. So with this, we can check and confirm that GLAV actually is able to get the meaning of the words in a certain sense. It's finding out that certain words are very much related to each other, and this is why they are mapped very close to each other in this 2-dimensional space. And actually I find this quite impressive if I think about it. So all that was provided at the beginning was a large pool of data, a large corpus of data that was provided during the training of GLAV, and then the algorithm implicitly found out which of the words are similar to each other. And we are able to pull out this information out of this large vector space and plot it in this 2-dimensional space. So this is super cool to me and quite successful. You can do the same for all other kinds of word embeddings, but if you use a modern one like BERT or whatever, it's working in the very similar way. So with this, we have reached the end of this lecture. And what we have done in this lecture was that we worked with Claude and we provided a certain category and found out the distances of all other words and checked out the closest neighbors to each of these words in these categories, and then we reduced the 100-dimensional vector space to just 2 dimensions and plotted it, and we're able to find out and confirm that the word embeddings are working very nicely and can confirm that actually these words are quite similar to each other. And that's all on this lecture. Thank you very much and see you in the next lecture. Hello and welcome to this lecture. In this lecture I will show you what we are going to develop together in the next coding lecture, because now we are going to develop some sentiment model, including some actual word embeddings. The dataset is the same, so that we are able to compare it to the previous lecture on sentiment analysis with our one-hot encoding. Now we are actually pulling in some real word embedding model, and the full process looks like this. We have our text corpus. This is our Twitter data that we have used before. Then we apply our pre-trained word embedding model. So we apply our text corpus on our pre-trained word embedding, and for every sentence, for every tweet, we get back a 100-dimensional word embedding vector. So we have now all our word embeddings, and instead of using our one-hot encoding, we use our word embeddings to develop our neural network model based on this. So we will use mostly the code that we have developed before, and just at some specific locations we are modifying the code a bit. So that's what we are going to develop in the next lecture. Thank you very much and see you there. Hello and welcome to this lecture. In this coding lecture I will show you how to implement the sentiment analysis, including some word embedding. I've opened here the file 90 sentimentembedding.py, and since there is a lot of code, I again will not type it directly, but instead go over the code with you together. At the beginning we import our packages. Noteworthy is here just the last one, the sentence transformer. This is one specific embedding that we can use to apply on a complete sentence. So before you can use it, you have to install it with pip install sentence-transformers, and then we are able to use this. I've done that before, so I can directly load all the different packages and just move on with the code. The start is the same. We are importing our dataset. So the dataset is stored in the subfolder data, and then it's called tweets.csv. It's shown here at the right-hand side. So we will focus in this analysis on the 2 different columns, text and sentiment. And the next step is that we need to work on the target feature. The target feature is here just a string. PyTorch, of course, cannot work with this. So we need to convert this into some numeric representation. This is what we're going to do in the next chunk. So here we have some mapping. The mapping corresponds between our category and an ID. The ID I defined starting with 0 so that it's applicable for PyTorch, and the lowest category of 0 is assigned to negative. Then we have neutral with 1 and positive with 2. And then with this mapping functionality, we apply this to a new column which is called class. Let's check this, and we can see here the last column was added corresponding to the class. The next point is to define some hyperparameters. I start with the batch size, then I define the number of epochs and the number of features. All of this is going to be used later in the training, but we are starting here at first with working on the embedding model. So the majority of the work is now to create the word embeddings and not just the modeling itself. So we use this word embedding model in advance to create our torch tensor. Here we are using this specific model from Hugging Face. If you take a look at the model page on Hugging Face, you can find the description. So this is a sentence transformer which is mapping sentences and paragraphs to a 768-dimensional vector space. So this is what we're going to use. Here you can also find out how to install it. And here are some examples, but we are going to go over the examples in our code. Let's just do this and uncomment here the different lines. Then we can see how to use it. So at first we need to create an instance of our model, and then we can define a list. So this is just one sentence in this list. And we can apply then the model by calling encode and passing the list to this encode function. And then we can take a look at this. Let's run this. And then we can see that we get this output. So let's just check the shape. Yeah, this is the expected result. We have a vector with this size, and now we are going to apply this to the complete column called text. So we have our data frame df, and here we have our text column, and we are going to apply it to every row of this data set. Since this is really some time-consuming process, I did this in advance in my case. So you can see here how to do this. You can just uncomment this and run it locally. So it's just passing in the complete column as a list and storing the result in this object X. And then I just dumped it with pickle so that I later can just load it again. Because it really took something like 30 to 60 minutes and I don't want to do this every time again. So I can just pull it from the file where I've stored it, but you have to run it at least once to create it in the first place. Good, I can just run it and I can check it. So it has the expected dimensions. So here we have the number of rows and then this 768 dimensional tensor. Good, now we can move on. The next point is just the classical train test split, where we use in this case a 50-50 split between training and testing. The dataset class is very simple, so it's just putting in the independent and dependent features, transforming it into some tensors, and then the length function and the getItem function are implemented as well. Based on this, the dataset objects are created, and once this is covered, we can create the data loaders. And our model, it's the exact same model we used before in the one-hot encoding. So we just have a simple stack of linear layers and in the end some softmax activation. And now we can create an instance of our model. So we can pass in here the number of features and the number of classes, and we have our model instance. For the loss, we use the cross entropy loss, and we use Atom with weight decay for the optimizer. Also the model training, the training loop is completely the same as before, as you have seen it in the one-hot encoding lectures. So here we just have the classical process of iterating over the epochs, iterating over the batches, and we have here our predictions which are created, the losses which are calculated, and then the calculation of the gradients and updating of the weights. So we can start the training process. In every epoch, the current epoch number is returned as well as the current loss. Now here, obviously, I have changed the number of epochs. Let's just have it similar to the one-hot encoding because I want to compare the results. Let's just do it again. So recreate the model and starting the training loop again. And now we are going to have exactly 80 epochs as we had it before. And afterwards we can check the training progress, how good the losses were reduced over the epochs. And once this is done, we can focus on the test data. But you can see it's super fast, so we can just wait a few more seconds and this is done. So this is also looking quite nice. Actually, we could have trained it a bit longer, but for the sake of this exercise, I will just keep it with this and move on. So in the next step, I'm working with the test data and I extract the predictions on the test data so that afterwards I can convert it into some NumPy array and check the accuracy. And you can see here it's significantly higher than what we had with the one-hot encoding. With one-hot encoding, if I remember correct, it was something like 63%. Now we have 68%. But one important aspect here is the size of the data that we are passing in. Because with one-hot encoding, we had something like 27,400 different rows and 27,400 different columns. So this is a huge matrix which is provided. And now we have something which is much smaller. So the number of rows is the same, but instead of 27,400, we just have 768 different columns. So we can calculate the ratio. So now the training data that we are working on is reduced by 97%. So with much less data, we get a significantly higher result. And this is really, really a good result that we achieve in the end. And also the rest of the code stays the same. We can calculate the baseline accuracy. So by pure guessing, we would have an accuracy of 41%. And with this, we have reached the end of our lecture. So just to recap what we have done, we have developed some sentiment analysis model, some classification model based on some word embeddings, and actually not just word embeddings, but sentence embeddings. So we were able to find a model which can be applied directly on complete sentences, and we make use of this 768 dimensional vector space, and we were able to develop a very simple model which is better and working with much less data compared to the one-hot encoding. And that's really a great result for such a very simple model. And with this, we have reached the end of this lecture. Thanks a lot and see you in the next one. Hello and welcome to our new lecture on transformers. Transformers are a very new deep learning architecture which became very popular over the last years. And in the next slides we are going to see why this is the case. At first, let's talk about why there was actually a need for improving the existing models. So the transformers were developed especially with the background on natural language processing, and the models from this field were supposed to be improved. And until then, RNNs, recurrent neural networks, were dominating this field, and some offsprings of RNNs like LSTMs and so on, what we have seen earlier in this course. And RNNs have some specific problems, or can have specific problems. For example, in NLP, the words are processed one by one. So one problem is that the training is very hard to parallelize. Then the next thing is that the order of the words is important in a sentence. So you can see here some very simple examples. Something like Alice loves Bob is definitely not the same, or not necessarily the same, as saying Bob loves Alice. So the ordering is important. That's the next thing. And RNNs are known to have problems with larger sequences. So the larger the sequence, so the further away some information gets, the RNN models are having the problem of forgetting some information which is in the far past. Furthermore, RNNs can have some problems in training, so they are suffering under specific problems like vanishing or exploding gradients. You can see here, this is the structure of some unrolled RNN, and this is basically the background for why there was a need for some improved model. Then Google developed in 2017 the first transformer models, and in 2017 Google has developed transformers, especially with the focus on translation tasks. And this model or these models have some main benefits, like they are able to keep track of the word order, they don't suffer the vanishing or exploding gradients, they are also capable of being trained in parallel, and they are applicable to really huge models. You can see here at the right hand side the network architecture, which is based on the original paper. So the original paper was called Attention is All You Need, and attention plays really a big role in all of this. As you can see here, there are three main features. The first one we are going to cover is the positional encoding, and then we have attention and self-attention. Let's take a look at the positional encoding. In natural language processing, the word order is important, as we have seen before. In RNNs, the word order understanding is based on a sequential pass of the words. And in contrast to this, the transformers use something that is called positional encoding. And actually on high level, it's a very simple idea. So take a look at this sentence I like to code. Everything that is done here is basically the different words are separated, and then each of these words is mapped to the position so that the order is persistent. So in retrospect, you're able to reproduce the original sentence. So this is basically everything. You have the different words and their positions in the sentence. For the purpose of explaining the idea, we just used here the numbers 1, 2, 3, 4, but in the original paper it was a bit more complex, so there are some sine and cosine functions were used for the encoding. The next concept that is used is called attention, and this concept was introduced in 2015. What is done here is that the attention is focused on every word in a source sentence to come up with the translation in the target language, and some interdependencies between the words are learned during the training. You can see here some mapping of the source sentence in English and the target sentence in French, also coming from a paper which is called Neural Machine Translation by Jointly Learning to Align and Translate. And you can see here in the source sentence, which is saying, it should be noted that the marine environment is the least known of environments. If you focus on the word noted, then this is actually correlated to a range of different words in French. And if you train the model on a large number of texts, then this understanding is improved over time. So this concept of attention is helping to learn the word order, but also the plurality or the grammar in a sentence. Then something that is kind of related to attention is called self-attention. And this concept helps to improve the internal representations of the words. So here you can see some example. So in this example, we have a word with different meanings. So the first sentence is saying orange is created by mixing yellow and red. Whereas the second sentence is not about the color, it's about the fruit. So the second sentence is an orange is a fruit of various citrus species. So we have two different sentences dealing with orange, and the orange is something completely different and it's depending on the context of the sentence. So this is a case where self-attention can actually help. So self-attention is extremely helpful to improve the context understanding. There are some very famous examples of transformers. So the first one I want to mention is Google BERT. BERT actually is not like my name, it's standing for bidirectional encoder representations for transformers. And you can see here how huge these models are becoming. So this model has 110 million parameters. That was top-notch at the time of the creation, but then some other models were created, like the also very famous OpenAI GPT-3, which is meaning Generative Pre-trained Transformers 3. And it's not a typo, it's actually having 175 billion parameters. And then quite recently Google Lambda was introduced. So Lambda is language model for dialogue applications, which is also extremely powerful, and it has around 137 billion parameters. And for getting some impression on the scale of these models, you can see here the size of the raw training dataset in gigabytes, which is immense, as you can see here, going from 340 to 3000 gigabytes. And then you can see the number of words or tokens and the number of parameters for different models. So these models are really state of the art and the results are really impressive. We have spoken a lot about NLP up to this point, and in this field of natural language processing, transformers can be used for any kind of task, like for text summarization, classification, sentiment analysis, and any other kind of task that you might see in this field. But it has shown that transformers can actually be used also for other fields. So transformers are also used in computer vision and also for time series prediction. So it seems like transformers are really capable and really flexible because they can cover a lot of different fields and improve the results. And in the next video, we are going to take a look at one specific type of transformer, which is dedicated to computer vision, which is called vision transformers. Thank you and see you there. Hello and welcome to this new section. Now you're going to learn how you can apply some pre-trained networks. And pre-trained networks nowadays means Hugging Face, because Hugging Face is the place where the majority of all models are living. You can find there many different open source models, and they are coming from many different tasks from within NLP, and we are going to explore all of them. So this is going to be covering all these different subtasks which are defined in here, and we are going to see how we can apply the models which are available on Hugging Face for our purposes. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now we're going to take a look at Hugging Face, and we are starting with the question, what is it actually? Hugging Face is a platform for machine learning and data science, and it helps users to build, deploy, and also to train machine learning models. Furthermore, it provides infrastructure to run and deploy some models in live applications. And also it's the largest community on machine learning, and it's hosting the majority of machine learning models. Let's take a look at the ecosystem. If we are starting with Hugging Face, the first thing that comes into my mind are the models, but actually there's more. So in Hugging Face, you also get access to certain datasets, or certain metrics are implemented. And also there is a lot of documentation, a lot of how-tos and tutorials which you can check out, which are showing up to be very helpful. And now we take a look at some specific areas, like we are starting to take a look at the models. And there are many different models. There are multimodal models. There are models on computer vision. And of course, the ones which are most interesting to us in this course, the models on natural language processing. But also there are models on audio or tabular data or reinforcement learning. But we are staying and focusing on the NLP models. And in here you can find then models on text classification, on translation, on summarization, on text generation, and also on film mask. All of them we are going to see in the next coding lectures, and we are going to explore how they are working. But if you're interacting with Hugging Face, with the models, then there is a very nice interface and a super simple API to use the models for model inference. There are two different categories of pipeline abstractions. You can run the pipeline by providing some task. That is the general encapsulation for specific tasks, and it could look like this. You create an instance of a pipeline for one specific task which you're defining and passing in. And then if you don't pass any model, then the default model from this task is selected. And here it's also saying that using a pipeline without specifying a model name in production is not recommended, because they might change it. They might change what the default model for a certain task is. But for us to explore how everything is working, we are just starting with this general approach and the default models. And it might look like this. So you have set up the pipe as here before with a specific task, and then you can just pass in the data and you get back the result. So really in 3 lines of code, the first one for importing the package, then for setting up the pipeline, and then for running the inference. These are just 3 lines of code, and you have successfully used some pre-trained model. So it cannot be simpler than that. The other way is that you don't provide only a task, but also a model. Or you could also just provide only a model in the pipeline. So then you get a very specific model out of a large range of different models which are available, and it might look like this. So you set up the pipeline. So this is very similar to before, but here we are now also defining the second parameter. So we also don't just provide the task, but also the model. And you can find out about all these models on the Hugging Face website. And then the pipeline is set up. So in this step, the model is downloaded to your local system. So for the first run, that might take a bit, but then you have it locally downloaded and available, and you can run it, and the inference is super fast. So then the API for running the pipeline is the same, and this is the second way of using a pipeline, by specifying a model. And then there are some more details. Here I just copied a screenshot of the complete definition of the pipeline. So there are more parameters. One that I think might be relevant more than others is the tokenizer, because typically we don't set that one, because we just use the default tokenizer of the model that is defined, but you also might specify it specifically. So we have the task, we have the model, then possibly also some other configuration and the tokenizer, and some other stuff which we're not going to cover here right now. Let's take a look at the input of the pipeline. We have seen before that the pipe, the instance of the pipeline, can consume just a string, like in this example at the top here, but it's also very flexible, so you could also provide a list of strings. So both is possible, and it's providing the results in either way. And in the next video, we are going to take a look at how we can code this together. Thanks, and see you there. Hello and welcome to this lecture. Now we are going to take a look at a specific task on text classification. And text classification is useful when you want to assign some predefined categories or labels to some given text. And you might use that for different tasks, for example, for spam detection, or if you want to categorize certain topics, or, and that might be the most relevant one, if you want to perform some sentiment analysis. In all of these cases, you might use this task on text classification, and the pipeline has the name text-classification, and then you have some text which you're passing into the model, like that one here. And there are many different models. In a case like sentiment analysis, there might be these two different categories, positive and negative, and then the algorithm would provide some probabilities on whether the sentence is considered to be either positive or negative. In the next lecture, we are going to see this in practice. Hello and welcome to this coding lecture. We are now working in the folder 20 apply pre-trained models, and we are going to the file general use. And in here you can see how we can apply this. So all we need to do is we need to import the package that we need, and that is from the transformers package. We are going to need the method pipeline. Let's run this. And then we can set up our pipeline. All we have to do here is we need to specify the task. And if we're working on text classification, all we have to do is we have to provide it as a string. And then we get the reference and the instance of this pipeline. Now we set it up, and now we can run it. So we can run it by just passing in the string, like this one. I like it very much. And then this specific default model, according to the task, is providing the result as a list. And then inside the list, we get back a dictionary with the keys label and score. And then here it's providing some positive label with a score close to 1, which is not surprising and a good result. You could also run it by providing a specific model. So not just providing the task, because then it's only using the default model, but you can also pass in a certain model. And how do you come up with this string? Well, you just have to head over to Hugging Face. And once you're here, you can check out the models. And on the models page, you can scroll down to the area of NLP. So we are here and we're working on text classification. So we click this area. Now we are getting a filtered version of all the models, and we only get the models from this specific task. And here they're sorted by popularity, I guess. No, by trending, we can see it here. So you can sort it in different ways, and you can check out the different models which are available, because with text classification, it might be providing sentiments, or it might provide other classes. So I'm just checking out this one, Roberta Base Go Emotions. Let's just see what this is doing. And here you can see which of these different emotions is most applicable to the sentence which is provided. So this is also some text classification model which is very popular, but we are using a different one. We can check it out actually. We can use the one that I have provided here. And we can also just search for the model. And then we can take a look at the model card. The model card is always the area where the complete model is described. And then you can see on which data usually it's trained. So this model is multilingual because it was trained on these different languages. And then often you can find some information about the accuracy and some contact person, and typically some more information, whatever the developers of the model want you to know about the model. And here at the beginning it's described what it's doing. It predicts the sentiment of the reviews as numbers of stars between 1 and 5. Good. So now, if we run it like this, we get a different output. Here we had the label positive. Now if we use this specific model, so it's quite fast in my case because I have loaded all of these models before. If you run this the first time, it's going to download these models, and these models might be quite heavy in certain cases, like in the order of gigabytes. So just be patient. And now the pipeline is instantiated and we can run it with this sentence. And now we get the label, which is 5 stars. Or you could also use the score which is provided. Good. And then another thing I want you to be aware of is that you don't have only this one option of providing the input as a string, but actually you can pass in a list of strings. So here we have two very opposing sentences. I like it very much and I hate it. And let's see what the outputs are. Yeah, one is 5 stars. The other one is 1 star, not surprisingly. So this is just another way of passing the data into the pipeline. Good. So with this, you have seen the general use of the pipelines. And in the next lectures, we're going to see some other tasks and how to use them. Thanks a lot and see you there. Hello and welcome to this lecture. Now we are going to take a look at one specific task, which is called named entity recognition. And named entity recognition is a process for structured and unstructured data, and it can classify named entities into some predefined categories. So the pipeline name is NER, and if we have some sample sentence, like that one here, Apple Inc. was founded by Steve Jobs, Steve Wozniak and Ronald Wayne on April 1st, 1976 in Cupertino, California. Then the named entity recognition is based on some predefined entities, which might be these ones. So you might have the entities organization, people, date, or location. And what it's doing and providing is for the different words in the sentence, it's providing the different entities. So then it would find out that Apple Inc. is an organization. Then it finds out about the different persons and the date and the location finally. So you can use it for breaking apart a complete sentence into its entities. All right, in the next lecture we are going to see how we can code this in Python. Hello and welcome to this lecture. Now we are going to take a look at a different task, which is called named entity recognition. The start is, as before, we need our pipeline from the transformers package, and then we set it up by just calling pipeline with the task. So we could also pass in the task in here as a name, or just fall back to the positional encoding, and then NER is used as the task. And then once the instance is created, we can pass in our sample sentence and we get back all the different named entities from the sentence. So let's run this. And here it's saying what the default model is, which is applied. And then we get back a list of different dictionaries where we have the different words, the positions with the start and end, and the entity with the corresponding score. Good. And this is how you can apply named entity recognition. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now we are studying a task which is called question answering. And this specific task is allowing us to understand and respond to certain questions, and alongside it's possible to extract some relevant information. So the pipeline is named question-answering and it's working like this. You pass in one document or a range of different documents into the pipeline, and you can extract some information out of these documents by asking a certain question. Alongside the documents, you might also provide a question, and then you get the answer on the question. All right, in the next lecture, let's take a look at the coding of this one. Hello and welcome to this lecture. The next task that we are going to study is question answering. And we are, as always, importing our package. So from transformers, we are using the pipeline, and now we are passing in our question answering into our pipeline. So we have to specify our task like this, question-answering, and we create the instance, and I call it pipe. And then in here, I can just provide the context as one parameter and the question. So the context which the algorithm is supposed to understand is the Big Apple is a nickname for New York City. And then the question is, what is the Big Apple? Let's see if it's understanding it. Good. And it's saying that it found an answer, that the Big Apple is a nickname for New York City. So that seems to work quite well. Good. Thanks a lot, and see you in the next lecture. Hello and welcome to this lecture. Let's take a look at a task which is called text summarization. And with text summarization, it's possible to distill some essential information from some source text, while at the same time it's possible to preserve the meaning and the key details of the text. And the typical applications of this one is, for example, if you want to summarize a document, or if you're working on social media posts and you want to summarize it, or if you want to summarize some news articles. All of these cases might be good applications for text summarization. And the usage is quite simple. You have some source text document which you're passing into the pipeline, which is called summarization, and you get a shorter text. That is why I made the size of the boxes differently. So then you can get back the shorter summarized version of the original source text. All right, let's see this in practice. Hello and welcome to this lecture. Now we are going to study the next task, which is called summarization. Again, we are importing pipeline from transformers, and we set up our pipeline. Here we specify our task to be summarization, and I also selected one specific model, which is this one. Also here you can just check out the model page, and we're looking for the area text summarization. And here that is the first and trending model that I selected. We can check it out and take a look at the model card. So it's a fine-tuned version of this T5 model, which is also quite famous. And then it's providing some information on how to use it. So here you can see it. Yeah. Good. So all we need to do is we need to copy our string. So we need to copy the name of the model, and we can specify it here in our model parameter. All right, and then we pass in an article. So I just copied the text from Wikipedia about Hugging Face, about the company behind Hugging Face. And then we use this as the context. And then we also specify some minimum length and the maximum length of the answer that we expect. So let's run this and process the complete article. And here's our summarized version. So Hugging Face was founded in 2016 by French entrepreneurs. And that is a good and very short summarization of this longer article, because we specified also very strict limits on the length of the result. Good, and that is how you can apply text summarization with this pipeline. Thank you very much, and see you in the next lecture. Hello and welcome to this lecture. Another task that is very relevant is called translation, and it's not too hard to guess what this is doing. It's allowing us to translate a text from some source language into one or multiple target languages. So we have one document in a specific language, and there are many different models available to translate this source language into whatever target language. So you can specify then the pipeline translation, or as we will see, translation underline and then target and source language. So with this one, then we can easily translate a document into some target language. Good, let's see how this works. Hello and welcome to this lecture. We are taking a look at a different task, which is about translation. So we are always starting with the import of our packages. So we import pipeline from transformers, and we just need to set up our pipeline with the corresponding task. And here it's slightly different compared to before, because here we have a bit of flexibility. We don't just call translation as the task, but actually we are able to use and define this piece, because then we can encode what our source language is and to which target language it should be translated. So with this, we are setting up a task to use a default model for translation from English to German, and then we just translate this sentence. So it's specifying which model is going to be used as the default model, and here is our translated text. Die Hauptstadt Frankreichs ist Paris. So that is perfect. It's perfect grammar, and also the content is correct. So everything is nice. And now you've seen how you can make use of the task translation in Hugging Face. Thanks a lot, and see you in the next lecture. Hello and welcome to this lecture. Another technique and another task that we are going to study is called fill mask. And with fill mask, it's possible to predict some masked, or you could also say some missing word within a given sentence. And such a model is able to fill blanks with some suitable words or some suitable tokens based on the context which is given. So on a sentence like that one, the capital of France is, and then you have to code it exactly like this. So this is then the area where the mask is going to be applied. And if you pass that one into the pipeline fill-mask, then it's providing the right answer. The capital of France is Paris, actually. Good, let's see how this works in the next coding lecture. Hello and welcome to this lecture. The next task that we are studying is called fill mask. And fill mask can be used also, as we will later see, in data augmentation when we try to augment some text database, because here we specify a sentence and a specific word which is left out on purpose, and that is the masked or the missing word. So all we need to do to achieve that is we need to import our pipeline, then we set it up with the corresponding task, fill-mask, and we need to encode the string in that way. So we can provide some sample sentence, and we need to provide our mask in especially this writing. And then once we run that, we will see that we get back a list of different dictionaries where we always get a score. So the model is telling us how certain it is to pass in this specific token. So it's most likely to pass in Paris in this case, and that's the right answer. And with decreasing probability, we can also see the other scores here. And yeah, the other ones would be obviously wrong. So here it's providing the right answer. Good, that's it for this lecture. Thank you very much and see you in the next one. Hello and welcome to this lecture. In this lecture we are going to discover zero-shot classification and what this will mean. But to understand the benefits of this very specific NLP technique, it's valuable to take a look at the typical training process. So in a typical training process, we have our inputs, our model parameters, and the model results. And we are starting with our independent data. So in this case, a large corpus of text. Then we have our network architecture with different layers and the corresponding weights. Then we are getting some predictions and we are comparing them with some true values. So in the case of classification, that could be a limited list of different classes. So for example, if you're working with texts, which could be either classified into invoices, orders, or whatever, then these would be our true classes. And here you can already see the problem if you are trying to deal with this in a classical way. Because imagine that you have trained your model on a limited set of different classes and now a new class is appearing. So what this typically would mean is that you now have to retrain everything. That is what we have learned up to this point in this course. Whenever you are changing the classes, you have to do the complete training again. And there is one very cool technique in the area of NLP, which is exactly this one, zero-shot classification, which is overcoming this problem. So let's just stick to the typical training process. Then we have the true values, the true classes, and the predicted classes. Based on both, we can pass it into the loss function and get some loss score, which is then passed to the optimizer, and the optimizer is taking care of updating the weights. That's our typical training process. And in zero-shot text classification, to be specific, it's working a bit different. So far it's the same. We have our training data, our pre-trained network. So it's not just the architecture, it's already coming with some frozen weights. Somebody has pre-trained it on a very large text corpus. And then we get our predictions. And the interesting part here is that I'm talking here directly about the inference, not the training process. Here in the inference, you are not just passing in the training data, but also some candidate labels. So based on the candidate labels, the predictions are created. So you get the exact same number of predictions as you have provided candidates, and you get the probabilities for each of these candidates. All right, so that sounds quite cool. And here is a short summary on the goal of this specific zero-shot approach. So the main goal is to apply a model to a task that it was not trained on, so that you don't have to retrain the complete model from scratch. You can directly apply it without much ado to something that it was not trained on. And this is also meaning that you can generalize a trained model to some new and completely unseen classes. So you are avoiding the retraining process, which is extremely time-consuming and costly. And you are doing all of this by making use of some additional information to make predictions for some new classes by relating them to the known classes. And in general, this technique is especially useful if you have a large number of different classes and if these classes are changing frequently. All right, there are some different approaches in this area of zero-shot classification. One is called attribute-based, then we have word embeddings, and then we have transfer learning. Let's start with the first one, with attribute-based. With this specific type of zero-shot classification, the classes are associated to the attributes that are describing the character. For example, animals. And staying in this example, the attributes could be, if you're working on animals, something like the animal has fur, the animal can fly, and so on. So during the training, the model is learning to relate these attributes to the classes. And during inference, the model is able to predict some unseen class by combining the different attributes. The next type of zero-shot classification technique is based on word embeddings. We have worked on word embeddings before in this area of natural language processing. Here in this case, the classes and the instances are represented in some continuous vector space by the word embeddings. And these embeddings capture the semantic relationships between the words and the concepts. And then these mathematical or geometrical relationships can be applied. So coming back to the word embedding we have worked on before, you can see then after reducing the dimensions of this word embedding of different words to just 2 dimensions, you can see then that different concepts which are related are close to each other. And the last type that I want to touch on here is called transfer learning. With transfer learning, the model is trained on some large data set, and the popular technique in this area is called natural language inference. In this specific technique, some hypothesis is created and finally tested and evaluated to be true, false, or undetermined, given a specific premise. So let's take a closer look at natural language inference. With natural language inference, you have a premise, you have some candidate classes, some hypotheses, and finally you get some predictions. How does this look in practice? Imagine that you're working on a text. The text is called "I watched the documentation and it was amazing." And you want to get one of the different candidates. So you want to find out if this text is representing either a movie, a book, or a play. So implicitly what the model is doing is building some hypothesis. So it would, for the first candidate class, create the hypothesis the text is about a movie, then the text is about a book, and then the text is about a play. So this is what the model is doing under the hood, and then it's calculating some predictions. Based on some softmax activation, you get the final probabilities, which are then, in this case, I just made up the numbers, 97% for movie. So documentation is closer to a movie than a book or a play, which would be then the final class that you could consider in this area. But you could also easily imagine that a specific text is belonging to multiple classes, so something like multi-label classification is also easily possible with this approach. And we are working in the coding lecture, which is upcoming, with some model from Hugging Face. We have seen Hugging Face in a different lecture before, and you can see then on the Hugging Face page that in the area of natural language processing, there is a complete section on zero-shot classification, and then you can see all the different models available from this area at the right-hand side. And in the next video, I'm going to show you how to implement this in real life. Thank you very much, and see you there. Hello and welcome to this coding lecture on zero-shot classification. I show you here this page of Hugging Face because this is where we are starting. We are going to check out the different models from this area. So we can check under models, and then we can go to the area of natural language processing, and here we can filter for zero-shot classification, and we find here all the different models which are available. They're ordered here by trending, and also you can see here this is a very popular one, the one from Facebook based on BART large. We can click on it to get more information, and then if you scroll down you can also see some examples which we are going to follow along and how easy it is to implement this. But also what we can see here is that this specific checkpoint, this specific model is based on the multi-NLI dataset. We can just check that. So I click on it, and you can see this is our training data. It's having roughly 400,000 rows. We have here our premise. And if you take a look at one of the premises, you can see here the string that was evaluated, and then also the corresponding hypothesis that is used based on it, and then finally the label. So the label can have 3 different states. It can be entailment, so it can be confirming the hypothesis, it can be neutral, or it can be a contradiction. So these are the 3 different labels that are in the training data. And now we can make use of the model that was trained based on that data set and open the zero-shot start script. In here I have just imported the packages that we're going to use. So from transformers we are importing pipeline, and then later on we are making use of pandas. And we are starting by defining our classifier. So the classifier is making use of the pipeline. And in here we are specifying at first the task. So we are passing a task to it, and the task is zero-shot classification. And then the model is our second parameter. And here we're going to make use of Facebook BART large MNLI. And now we only have to pass in our task and our model. Let me just run that. If you run that for the first time, it's downloading the model to your local disk, so that is going to take a bit longer. But I have already done that before, so it should be loading a bit faster at my end. And now we're going to work on some documents. I've looked here for 3 different documents, the starts of 3 different books. So the first one is an example for a crime novel from Raymond Chandler, The Big Sleep. Then the second list item is coming from Tolkien's The Lord of the Rings, which is corresponding a fantasy novel. And then the last one, the last list item, is coming from Bill Bryson, A Short History of Nearly Everything. And that is corresponding then to some history book. At least that is what we are going to expect, because I want to work with something where I have a specific expectation. And now we can define our candidate labels, which are crime, fantasy, and history. Now we have that. We can now call our classifier, in which we pass our documents. And then as the second parameter, we pass our candidate labels. And we can store the result in an object called res. And now the model is run. So once we have that, we can take a look at the result, which is available now. Let's take a look. We have our object res. Here we have now for each of the different list items in our documents object, we have then the keys for the sequence. So this is the sequence that we have passed. Then we have the different labels and the corresponding scores. And this we have 3 times. So you can directly apply this to a larger list of different texts and get back the corresponding labels and scores. Good. Let's take a look at the item at index 1 that is corresponding to our book The Lord of the Rings from Tolkien. So we know it's fantasy, and we hope that the model found out the same. Here we have our sequence, we have the different labels, And the largest score is found exactly for this category, for fantasy. Great, so it found out the right one. But also history has a large percentage. So you could also argue that the model is thinking this is corresponding to some history book. So in general, we can be quite happy with the result. We can also make a data frame out of it. Because then we can directly put this into some bar plot where we are putting our labels horizontally, the scores vertically, and then we can also put in our title, The Lord of the Rings. And this would be the graphical representation of what we have just seen. So the model would categorize the beginning of The Lord of the Rings as a fantasy book, and it's correct with that. You can play with the different other results as well. That is what I'm going to leave up to you. I just want to show you one more parameter. You can also flag multiple labels, because you could imagine that a certain document can be categorized and belonging to two different classes. So we can just run that classifier and we can just run it on our documents with our candidate labels and with the parameter multi-label equals true, or we just do it for one specific item. And now you can see that the scores have been affected. Now they are not summing up to 1, so it's more like finding out if there are multiple classes available at the same time, which is not the case in this specific example. So it's still pretty sure it's just crime and not history or fantasy. But in other cases, it would be possibly helpful to set this parameter multiclass to be true, because the default is false. Good. I hope you like this technique as much as I do, because it's saving you a lot of time. It's super flexible, and with just a few lines of code, you are able to get this zero-shot classification up and running, and you can apply it to your documents. And with this, we have reached the end of our lecture. Thank you very much, and see you in the next one. Hello and welcome to this new section. Now we're going to talk about fine-tuning of a model. And the first question is, why is fine-tuning actually needed? Assuming that we already have some pre-trained network, and that one was trained on certain data sets, and it might be that your data set, your custom data set, is very different from the ones on which the network was trained. And then if you would just pass your data into the network, since it was not trained on that one, it might provide not sufficient results. So that would be not working. That's one reason. Another reason is that the model that we have is trained on a certain task. So for example, it's trained to be a classification model, but actually in our case, we want to use the model for something different, for regression. Or it's trained on one specific NLP task, let's say on classification, for example, but we want to use it for a different task, for film mask, for example. So then we need to adapt the final layer of this model and train it again. So these are just some examples when fine-tuning might actually be needed. And then there are different approaches, which we are going to study in this section. So when we fine-train a model, we can pass our custom data into the pre-trained network during training. And then the training is performed. It's iterating over your data in several epochs, and at some point your network is trained and adapted to the data set. And then you can just perform model inference, pass in new data, and you get back much better results than before. So this is the main idea of fine-tuning a model, and we are going to study different approaches in this section. We are going to start with a simple approach in which we are going to extract some features from some pre-trained network, and then we train some simple algorithm on it, and we are actually going to retrain the network, parts of it, or even the complete network, and that would be our actual fine-tuning of the model. And as you will see, the fine-tuned model is outperforming the more simple approach. So that is what you can expect from this section. Thanks a lot, and see you in the next lecture. Hello and welcome to this lecture. Now we are going to start to train a simple model on our dataset. But before we start there, we need to take a closer look at the tokenizer, and you will just see that there is the tokenizer, and that one is returning some text input IDs and some attention mask. But let's start at the beginning. So we have several texts. So here are certain strings, and then we are passing them into the tokenizer, and then the tokenizer is providing input IDs for each of the words. So whenever the word is the same, it's getting the same input ID. If it's different, then there is a different ID. So we get for the text 1 a token with a length of 5, and then there's also, because it's needed by the model, some attention mask. So in the end, we are going to have a certain length. So the tokenizer is providing an output in some rectangular shape. So all the different texts are converted to vectors of the same length. But since there is not necessarily the same number of tokens in each text, we need to fill the rest with zeros on the input IDs. And it's getting completely clear when we take a look at the attention mask that whenever we have an actual input ID, then there is a 1. Otherwise, it's just filled with zeros. So all the different tokenizers are providing this as an output. We have our input IDs and some attention mask. And then that one can also be performed in batches. So not text 1, text 2, text 3, but actually all of them are taken together. You can define some batch size, which is defining how many of these texts should be covered in the same step. And then everything is processed, in a batch way. And the simple model is working like that. We have our input IDs and our attention mask, and we are passing them into our model. And here we just use a small model, because then the fine-tuning is also a bit easier and faster in the end. We are using Distilbert base uncased. And here is just a schematic view of the network. We have some input layer, then a lot of different hidden layers, and some output layer. And the output layer is not necessarily what we want to have, as we see on the next slide. So we are disregarding that one, and we are interested in the last hidden layer, because that one is representing the inner structure and the context in the best way. So then we get here a 768 dimensional vector. That is the size of our hidden state. And for all the different texts, we have then here, each row is representing some encoded text. And we have our last hidden layer, which is having a dimension which is specified by the model. So this one is 768 dimensional. And this is our matrix that we have. This is regarded our independent data, which is typically called X in machine learning. And for these, for example, 1000 reviews, we have 1000 rows and 768 different columns. And for each of them, for each review, we have one review class. So there's a distinct number of different classes, and this is our target vector. So that would be our lowercase y. And then we have a structure that we can use like we know it from sklearn. We have some independent features x and some dependent feature y. We can pass it into some simple sklearn model, like for example logistic regression or support vector machines or whatever is suitable for the task that we want to solve. And then we can train the model on that. So basically we are extracting the features which are coming from the pre-trained network and train a different classifier on it. Good, so that is what we are going to implement, and you will see how to code this in the next lecture. Thank you and see you there. Hello and welcome to this lecture. We are starting by making ourselves familiar with the data at first. So I'm here working in the folder on fine-tuning and inside the file 20 EDA. And as always, we are starting by loading our packages. So first of all, from Hugging Face Hub, we are importing the method list dataset. And then for loading the dataset, we load dataset, and from there especially load dataset. And then furthermore, we just use pandas and seabone. Good. We can just get all the datasets by calling the function list datasets, and then we can print them in this way. This is actually taking a while because there is such a long list of different datasets, but I just want to give you some impression on how this might look. All right, at some point we get a list of all the different datasets, and the list is really long. So this is taking too long. I'm just stopping it. And I'm going to show you the page from Hugging Face. So we can just head over to datasets to check out all the different datasets. The one that we are going to use now in this section is the Yelp Review Full dataset. And it's twofold. It's having a split on training and testing data. In total, it has 700,000 reviews and the size of 300 megabytes. And the target label is having a value from 1 to 5. And then we have all the different texts according to this one. So this is how our dataset is looking like. And we can load it by just calling load dataset and assigning it to the object Yelp. Now you can see it's having the size of 300 megabytes, and give it some time to download all the data. All right, finally the data was downloaded, and here you can already see that the split was performed. We have some training data and some test data. Let's take a look at this object. It's a dataset dictionary where we have two different keys, train and test, and then each of them is having a dataset with the features, label and text. All right, then we can assign it also to our train.ds object by just grabbing from Yelp the key train. And we can also study the first element. And then you can see here the label. So we can see the text that was provided and the corresponding label to that one. Good. We might also take a look at the features. So the features are the text and the label. We can also check if there is any imbalance of the dataset. So for that, we can just access the labels from our training dataset and call from pandas, after we convert it to some data frame, we can call value counts. And then we can pass this one into the method countPlot from seabone. So here you can see that it's perfectly balanced. We have the same count for all the different classes, and this is a good starting point. So we don't need to work on the imbalance of the data because there is none. Good, we can also check the count of the words in each of the reviews and corresponding also to the classes. So the underlying assumption would be that possibly longer reviews are connected to worse reviews or something else. We just check that. So we can also again create some data frame, and here we create a column called review length, in which we are making use of some list comprehension. So we are iterating over the texts and we are splitting them. So then we have a list with every word, and then we can call the length function. And then we assign also another column called label, which is corresponding to the labels. Finally, we can put this into some box plot to just check if there is any specific behavior or relationship between the number of words and the reviews. And here you can see that there are quite many outliers, but let's maybe just specifically take a look at the median value. So this is the center of this whisker plot. And you can see here that better reviews are at least slightly related to shorter sentences. So that's maybe some outcome that might be interesting. And if the outcome is not so good, so if the label is 0 in this case, then the text is slightly longer. That concludes our lecture on exploratory data analysis. So we made ourselves familiar a bit with the dataset on which we are working now. And in the next lecture, we are going to see how such a simple model might be working. Thanks a lot and see you there. Hello and welcome to this coding lecture. Now we are going to set up some simple model, and we load at first all the different packages and our data set. So then we might also take a look at that. It's the same as in the last lecture. We have our dataset dictionary with our train and test data, and then we can also create an object of our train dataset. So we just have to call Yelp with the key train. And since 650,000 texts is just too long to train right now, I'm just making it shorter. So now we have here a much shorter data set, which is just having 1,000 observations. And as I told you in the theory lecture, we are going to use the model Distilbert base uncased. And that's our model name. We store it in here. Then we also can specify a device. If you don't have a GPU in your computer, then you can just set this parameter to CPU. If you possibly have one, you might just call this line. Actually, it's generic and you can just call it like this. So it's checking if CUDA is available, then it's setting it to CUDA, otherwise it's CPU. But to be on the same page as you, I will just use CPU, because this one is always working and it's just taking longer to train. And then we can create an instance of our model. For that one, we use the method AutoModel from transformers. And for the tokenizer, we use then the corresponding tokenizer, which is called Distilbert tokenizer. So first of all, our model, we have to call AutoModel from pre-trained, where we pass in the model name, and then to be sure, we can pass it to the CPU. And the tokenizer we can set up in this way. We call the class Distilbert tokenizer from pre-trained, and then we have the corresponding tokenizer to our model. We can also quickly test that. So we can just set up whatever text and pass it through our tokenizer and take a look at the result. And here, as you have seen in the theory lecture, we have our input IDs and our attention masks. Good. Now we can also make ourselves familiar with the tokens. So in our tokenizer, we also have the method convert IDs to tokens. So if we want to use our text, encoded text, input IDs at position 0. So it's looking like this. So this is our tensor, and we want to convert this to tokens. Then we can do that, and let's take a look at the tokens. Yeah. All right, so this would be our tokenized version, and we can also convert it back to strings. So here we have our class token, and this is then our back translated string. Good. We can also check how large the vocabulary size is by just calling the property vocab size. So here we have roughly 30,000 vocabularies. We can also check the maximum context length, and the maximum context length is 512 tokens. Good. Now we can create a function for the tokenization. So here we just create this function tokenize text, because then we want to apply this with a map call to our dataset. So here this one is consuming some batch, and then it's returning the tokenizer in which the batch is passed with the text. And it's important to return a PyTorch tensor. And then for the padding, we set the maximum length, and we set the truncation also to true. So in case that there are more tokens than allowed, it's truncating it. Good, this is our tokenized text function, which we are going to use now in the next call. So we create our Yelp encodings by calling our dataset, and here we have a map function, and we can pass it in like this. Then we also specify the parameter batched equal true, and then we also need to specify the batch size. And we go with 128 as a batch size. All right, I need to run the function first, and now we can create our encodings. And you can see the mapping is quite fast. And here we are. Good. The next thing is that we need to set the format. So we need to set the format to correspond to Torch. And then we do it in this way, that we specify the columns as input IDs, attention mask, and label. And then we have our Yelp encodings in the right format. And we can set up a function called getLastHiddenState. In that way that we perform some inference, we run the model, and we pass in some inputs, and we are keeping the last hidden state. And the inputs are defined in a way that we are taking a look at the items which are passed in a batch style, and then we keep here the key and the value pairs. It's all specified in a very specific way. Also, you can check this out on the Hugging Face documentation page. And what we want to return then is a dictionary with the hidden state as a key. And then from the last hidden state, we need to export the second dimension. Good. This is now our function getLastHiddenState, and we are using our Yelp encodings, and now we are mapping this function to the Yelp encodings, again with the parameter batched to true and the same batch size, and then we have our Yelp hidden states. Okay, you have seen how long this already took, and it's just 1,000 texts. Let's take a look at the result. We have now the label, the text, input IDs, and attention mask. Good. And since we don't want to do this again in the next lecture on the fine-tuned model, we just dump it into a subfolder called model. So just create this folder here, and we dump the file in here. So now we have this Yelp hidden states.joblib. Alright, and now some typical statistical training is applied. We just create some train test split. So we can grab for the independent features our object Yelp hidden states, and from here the key hidden states, these ones. And we are going to use 800 texts for the training. So we take everything until the cutoff of 800 for training and the rest then for the testing. All right, so this is the independent feature, and the dependent feature is just the label. And again, the same cutoff criteria is applied. Great, let's do this. And we have now some typical structure. We have 800 observations here, and then our hidden states with 768 dimensions and our target value. Good. First of all, as always, we need to create some dummy classifier to see in the end what is our baseline. How good is pure guessing? And the dummy model is having an accuracy of 16.5%. So that is just the baseline model, which is always predicting the most frequent class. But actually we want to see and train something better. So on tabular data, something like support vector machines is always working quite well. So we can set up our support vector machines classifier with a linear kernel, some cost parameter, and to have the same result, you can also specify the random state. And then with this instance, we can fit our data and score it. And already you can see that there are some very good patterns included in our hidden states, because the support vector machine is already providing an accuracy of 40%, so much better than the baseline classifier. Let's just try some other models, like for example logistic regression, and see how good this performs. It's even slightly better. And let's test, as the last example, also some random forest. Also better than the baseline, but not as good as our logistic regression. You might even try some other models. That's completely up to you. This is just describing the general procedure. So let's just recap what we have done. We have prepared our data in a certain way so that we extracted all the hidden states, and then we performed some classical train test split. So we create some training data and some tested data, and then we train some classifiers which are consuming the training data for the model training and the testing data for the scoring. And we have seen that even without much effort, just taking our deep learning model as some feature extractor is already providing some reasonable result. And that's the way how you could use some deep learning model as a feature extractor and train some rather simple sklearn model on it. That's it for this lecture. Thank you very much and see you in the next one. Hello and welcome to this lecture. Now we are actually going to fine-tune our model. And let's take a look at how this works. First of all, we need to work on the dataset. So there needs to be some separation between training and testing. We are going to deal with that. So that is the first step, to set up the dataset in the right way. Then we concatenate this one into some dataset dictionary, and we pass it into our pre-trained model, which is in this case, again, our Distilbert base uncased. And we are going to use from Hugging Face a very good interface, which is called trainer. So you don't have to define the more complex PyTorch training loop with all the different details. So Hugging Face has done a really good job on creating a trainer class, which is making the training of transformers models much easier. And we are going to see that on the next slide. Then we have our typical training loop, and at some point the model is converged and we are having our fine-tuned model. Great. Let's take a look at the differentiation between our pre-trained model and the fine-tuned model. So the pre-trained model is the one I mentioned before. It is trained to be a fill mask model, so the output layer is working a bit different than what we want to have it. It's the distill version of BERT, because that one is trained to be very small and still providing a lot of features and having a very good trade-off between performance and size. So here you can see the model description. Distill BERT is a transformers model, very small and fast compared to BERT, pre-trained on the same data. All right, and here you can see how to use it. So that model would be specifically working as a fill mask model. So if you provide a sentence like this one, the coffee is 2, and then inside the mask, it would fill out the mask. But what we want to have is a different output. We are going to train a dataset on some sentiment. So if you provide a sentence like the service is outstanding, it's returning then out of a list of 5 different classes, the one which is most representing the sentence. So that is a very good sentiment. It's considered to be a very good consumer review, so it would possibly provide a class of 5. So definitely the output layer needs to be different, and during the fine-tuning you have different options on how many layers you want to train. So you might want to train all layers or just the output layer or anything in between. So that is one parameter. Then we are going to develop some sentiment analysis model. And yeah, I spoke about the different output layer. Okay, let's take a closer look at the trainer which is provided by Hugging Face. The trainer is just a very simple API for training a model with PyTorch. And it's very powerful. It's supporting, for example, distributed training, or even if you have multiple GPUs or TPUs, that would be also supported. And it's optimized for transformers models. And it's actually said that you shouldn't try to use it on other models. But since we're working here only with transformers models, that's perfectly for our needs. So how does it work? On a high level, we just create an instance of our trainer class. And the trainer class is just consuming a few parameters like the model, which needs to be fine-tuned. Then you also need to specify some arguments, some training arguments, which are defining how the training should be performed in more detail. And of course, the datasets. You need to provide some training dataset, some evaluation dataset. And then once this instance is created, you can just call trainer.train and the training is performed. And then afterwards, you can use the model, or you could even push it up to Hugging Face so that others can use it as well. So this is the way how the Hugging Face trainer is working. And that is what we're going to explore in the next lecture. Thank you and see you there. Hello and welcome to this lecture. Now we're going to fine-tune the model. And for that we need to import some packages, like for example this automodel for sequence classification, distill BERT tokenizer for tokenizing everything. Then we also need the trainer and the training arguments, because we are going to work with Hugging Face's trainer class. Good. Then we also need to import the dataset dictionary and some other libraries for loading data, processing it with pandas and numpy, visualizing it with Seaborn, and some sklearn metrics and the dummy classifier. Good, let's run this. And then we can load our Yelp hidden states the one that we have created earlier, because then we don't have to do the complete pre-processing again. We can just load it from the file, and we are going to set up our model and our tokenizer. And the model is again our Distilbert base uncased model. We're going to train it on our CPU, because that is the option which is working for everybody. We are having 5 labels, so we need to specify that one. And now we are not using automodel, but actually automodel for sequence classification, because here we want to train some classifier. So we need to import and load this specific class, and then we can call from pre-trained and use that one as our pre-trained model. And then we also need to pass the number of labels. The tokenizer is set up as before, also from pre-trained with the corresponding model. And now we have everything loaded. We can also load our dataset. So we're going to use our Yelp hidden states, where we select the first 800 values for training and the last 200 for evaluation. Good. And then we are checking the shape of the input IDs. So this is our token length, and this is working just nicely. Then we set up our dataset dictionary, which is consisting of our train and test data. So now we have this object, and we are setting up a batch size as well as our training arguments. So in the training arguments, everything is specified that is going to be used by the trainer later on. So importantly, we need to specify here the output directory. Then we can also specify the learning rate and the number of epochs. We want to keep it short because the training is taking quite long anyhow. So we just train it for 2 epochs. And then we specify and hand over the batch size and define some other parameters, like we don't want to disable TQDM for showcasing the progress. At this point, we don't want to push it to the hub. We are going to do that later. And we are saving every epoch and putting our logs into the logs subfolder. So this is our training argument. And now we can set up our trainer instance. This one is consuming the model. That's the first parameter. Then we are going to pass over the training arguments, our training dataset, and our evaluation dataset. And then we can just call the train method on it to start the training. Let's see if this works. All right, the training has started, and now we just wait until everything is completed. Okay, the training has completed. And now we can check out the evaluation loss. All right, so this would be the way how you can train it and evaluate it. Actually, it might be a better approach to have 3 different buckets: training, evaluation, and testing. But for now, I'm just showcasing how to do that. You can improve the code still. So for the predictions, I'm also using now the test chunk. So I can just call trainer predict and running it on the test dataset. Again, that is something that you typically should do slightly different, so that there are 3 buckets instead of 2. But nevertheless, we can now check out the metrics, and we can check now the test loss. Test and evaluation loss is the same because it's the same data set, but we could compare that to the train loss in the very similar order. All right. Now, if we want to extract all the predictions, we can just do that by calling preds, and from here getting the properties predictions, and we can extract it with argmax, because the predictions are looking like this. Yeah, so for every entry we have now the probabilities, and then we want to get the argument which is maximum, so that we then get the class basically assigned. So this is the way how we do that. And we can also extract the true classes from our label and our predicted classes with this approach that we have seen now. So we can do that, and we can create our confusion matrix. Let's see. All right, so there are mostly the largest values on the diagonal value, and these are the true predictions. And then there are some predictions which are slightly off. So if they're off just by one value, then I would not consider that to be too bad, because if somebody provided a label of 0 and it is predicted as 1, then the prediction is not too bad. But if in a case like here, there are some predictions where 4 is predicted, but the actual class was 0, then that is completely off. But there are not too many observations which are completely off. So we can still calculate now the accuracy score. And we can see that the result is not too good. So I'm just rerunning the training, and I'm increasing the number of training epochs to 20, just to see if this one is improving the result. All right, I played a bit with the parameters, and now I used 10 epochs, and I get a much better result. So now you can see most of the values are on the diagonal line, just a few misclassifications, but only slightly, not drastic ones. So that result is much better than before. And also here, just to have the comparison in the same script, we can also create some dummy classifier and check out how this is performing. So if the model would be just purely guessing, we would get an accuracy of 16.5%. So we have a model which is way better than pure guessing, and also better than the simple model. And I'm sure if we provide more data, because deep learning is gaining very much in performance if you provide more data to it than just a few hundred observations, then we can easily get into the order of 90%, 95% of the accuracy. Good. And now we can also run some inference and make the predictions on the test data. Then we can also study some specific reviews. So we can extract the data and store the text here and the label as well as the predicted label. And then we can study that. So here we have our data frame, and we can check which of these predictions were right, which ones were wrong. So here is an interesting one which we might start to try to understand why it was actually a 4 and the prediction is a 1. So we might just dive much deeper. We could also study the reviews and the labels and the losses a bit more in detail and plot them for some further analysis. But now I'm going to show you how we can save the model. So for that, we can just open the terminal, and in here we can log into Hugging Face. Oh, here I see that my interface is not up to date anymore. So here is the corrected version. We should use Hugging Face CLI login. And here it's asking for a token. So if we head over to Hugging Face, you need to create some account. You can go to settings, and here you have then the different tokens. Now I'm going to create a new token. That one I'm going to call applied NLP. And since we also want to store the model in the hub, we need to assign the role right. Now we can generate the token and copy it. And here in the command line, we can just pass it in. All right, we can also add the token as Git credential. and the login is successful. So now we can call create model card on trainer, and I'm going to call this Distilbert base uncased Yelp. So I'm going to create this model card, and then I'm going to call push to hub, and here we have to provide some commit message, which is Yelp review classification. Alright, finally the model was uploaded and we get here the commit info, and then you can go to your Hugging Face page and then you can find there the model. Actually, I see here that I have named it incorrectly. It's taking the name from the folder, so I should have named it differently, but we can change that. Alright, under settings we can find here the name, and we use this name. Alright, let's call it new. Good, now we have here this model and we can use that. So we can just copy it. And we need to specify now our model ID. So here you can see the part where we are loading the model from Hugging Face. So we use it like every other model. From transformers we import the pipeline, we specify the model ID, and then we can run it. Alright, now the model is going to be downloaded, and then once we have that, we can run it. Okay, so the model is now available and we can finally just run it to see the output. So for a sentence like "it is not so great," we get most likely the label 1, and the second in order is label 0, so that seems to be reasonable. Great! So now you have also seen how you can store your model on Hugging Face and how you can use it from there. And with that we have reached the end of this lecture. Thank you very much and see you in the next one. Hello and welcome to this lecture on vector databases. As always, we are starting with some introduction. So what are vector databases? Vector databases are a special type of database, and in a second on the next slide we will see the differences to the normal databases. And this kind of database is able to store, manage and query data which is represented in geometric formats. And this is the main difference to structured databases. Since we are having a lot of these geometric formats, the embeddings, especially in NLP, so this is the reason why it became very famous in this field. So it's very famous in deep learning. When you're working with NLP or with image similarities, then vector databases are a good solution to the problems you might face. So vector databases are allowing you to search for similarities between different texts or between different images. And then you can also perform some clustering. You also might perform some real-time analytics. And as a summary of what a vector database is, you might say that a vector database stores high-dimensional data, let's call it directly embeddings, for fast querying and similarity analysis. Okay, I told you before, let's talk about now why you need vector databases. The reason is that the structured databases are not the best solution to the problems we might face when we're working with deep learning. Because the typical data that we get from the internet is unstructured. So we are working with images, we are working with texts. You might also deal with videos or sounds. All of this is unstructured. And the typical SQL database that you might know from some company environment, this is the perfect solution for structured data. So there is a different solution needed. There are also specific unstructured databases, but I'm not going to touch on these ones here because vector databases are fulfilling a fundamental need in the field of deep learning. But at first, let's talk about now about one of the applications, which is finding out about similarity. So if you're working with images, you might have a pool of different images. Let's call them candidate images. And you have a new image. This is called query image. And the question is, which of your existing pool of images is most similar to the one that we are asking here? So that's the typical task of image similarity. It works exactly the same if you're working with texts. So you have a large corpus of texts, a lot of different documents, and then there is one specific word or text which we want to query and compare to the different candidates. So the question is here very similar. Which of the existing text that you have is most similar to the query text? So the procedure is very similar, no matter if you work with texts or with images. So in the first case, you have a corpus or a number of different texts. You put it through your NLP model to get some word embeddings. So this means that for each text, you get one embedding, which is representing this text or this word. And in the case of images, you do the same. You take your image, you put it through your computer vision model. Let's call it CNN or possibly also some vision transformer. And then you can get some image embedding out of it. And since you don't have just one image, you have a multitude of different images, you get then a matrix of different embeddings and a number of different embeddings for each image once. So for NLP, we already know how to do this. For images, it's a bit different, but not too complicated. So we have our image, and then we are having some convolutional neural network, for example, and the typical structure is then that you have some convolutional layers, some normalization, batch norm layers, some activation functions, rectified linear units, for example, pooling layers, and so on. And then you have at the very end of the network some fully connected layer and the output. And the output is having a number of different classes. So possibly there are 1,000 different classes. And then if you want to get the embedding, you are actually not interested in the classes. Because you don't want to get the prediction of a class, you want to get the embedding. And the embedding is stored in the last hidden state. So you're only interested in the fully connected layer, and you can throw away the output layer. And that's all. So you just have to take your pre-trained CNN model, disregard the output layer, and take the fully connected layer as your image embeddings. And then the question is, how can you find the most similar data? This graph we have seen earlier in the lecture on NLP. So here we have some word embeddings based on GLAV, and here are different categories and then specific words from this category broken down to just 2 dimensions. If you don't know how we did that, just jump back to the lecture we had on that. And then if we're interested in one specific word and want to find out the distance to all other words, and then if we want to calculate the distance between 2 different words, we can use, for example, the cosine distance, which is basically calculating the angle between the vectors, which might represent the 2 different words. And then we can calculate this distance for the word we are studying versus every other word in our corpus. And then if we have an embedding vector of 768 embeddings, then there are in the end 768 different distances. And we would choose the closest distance out of this. So imagine that the pool of different images that you have is around dogs. So you have the image of dog 1, dog 2, all the way until dog n. And then you have all the different embeddings, and you want to test a specific dog image versus every other dog image. So based on the distance calculation, you can just calculate the distance of the dog test versus dog 1. Then you calculate the distance of dog test versus dog 2, all the way to the comparison between dog test and dog n. So if you're having not too many data, you can just store the result in some NumPy array. Actually, that's the go-to solution, I would say, in some small projects. But if you're working on a real mature problem, and if you have a lot of data, then it's possibly getting too slow, this approach. And this is where vector databases come in. Because what they are doing is that they provide some index. And if you've worked with databases a bit before, you know that indices are super important to speed up the comparison. So if you want to pull certain data from a database, it's very important that you have an index on a column. So this is making it much, much faster. And on the market, there is a number of different products. So you can check them out, like Pinecone, Chroma, or Redis. All of them are providing vector databases, and there are some other players out as well. But in the example that we are going to work on in the next lecture, we are just working with NumPy arrays. All right, that's it with our introduction into vector databases. Thank you very much, and see you in the next lecture. Hello and welcome to this lecture. In this one we are going to cover a topic which we have skipped up to this point because it was implicitly done by the models, but now we need to understand in detail what tokenization is doing. So what is tokenization? Tokenization is the process of breaking down a sequence of words or of a text into its individual units. And these units are typically words or parts of words, so subwords. And then these units are called tokens. This is something that you might have heard before. So this is the typical token that you talk about. And there are different approaches. You can tokenize on a word level, on a sentence level, or on a subword level. So there is word tokenization, sentence tokenization, or subword tokenization. Let's see what this means in practice. Here is some sample text. The text is: the quick brown fox jumps over the lazy dog. And then if you tokenize it, then you end up with a bunch of different tokens, basically a sequence of all the different words inside the sentence. And then you would end up with having all the single words in each of these different tokens. So that would be a word tokenization in this case. If you work instead with sentence tokenization, then the complete sentence would be tokenized. So there might be a longer text with multiple of different sentences, and then each of them is ending up in its own token. Here in this example, there's just one sentence, so there is in the end one token for this sentence. And why is this important? Well, it's a fundamental step in natural language processing, and it's typically the first step of all different NLP tasks. In the sequence of the different steps, we are starting with our text, we are tokenizing it, and then from the tokens, we are creating the embeddings. And then all the subsequent steps are following. But this is the step that we have jumped over up to this point, because often it's taken care of by the models for us. But now that we are working with vector databases, we need to take care of that ourselves. And if you want to practically implement that, there are different splitters. One is the recursive character text splitter, and that one is breaking down larger text into smaller units. And that one is repeatedly applied and splitting or segmenting everything in a process. And it's recursive because the same process is applied until the desired level of granularity is achieved. Good. And in the coding lecture, we are going to see this actually in practice. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now you might head over to this URL, because here you get some better understanding of the tokenizer. And you're going to learn about the interdependency between words, characters, and tokens. So here you can just pass in some sentence. Natural language processing is cool. And we can see here in the color coding the different tokens. So each token is having a different color. So what you can see here is that this sentence is consisting of 6 tokens, and in total we have 36 characters. So keep in mind that special characters like the dot are also using up a token, so this is also important to know, and often words are even requiring 2 tokens or more than just 1 token. And here is a rule of thumb, which is bringing together the relationship between token and characters. So as a rule of thumb in English, you can assume that a token is generally corresponding to roughly 4 characters. So if you have 75 words, that would correspond to 100 tokens. Alright, and that's it for this short X-course on tokens, characters, and words. Thanks a lot and see you in the next lecture. Hello and welcome to this coding lecture. In this one we are going to start with our journey into vector databases, and we are beginning with tokenization. Both is going to be handled in this script and in this video we are currently working on, and for this I have moved to the folder vector database, and inside here I used the starter script. And this is the one that you can see here at the right hand side. Good. At the top of the script I usually place all the different packages that we are going to use. So let's go through it. We're going to need regular expressions, so we import that one. Then we are going to use the recursive character text splitter and also the sentence transformers token text splitter. Both are coming from LangChain. Then in the end we also want to directly apply what we have done. So we will use our tokenization and put it for a quick example into some vector database. For that one we are going to use ChromaDB. And then from ChromaDB we also are going to use the sentence transformer embedding function for creating all the embeddings, and we need at some point to add all the tokens with a unique ID to the database, and for that we need this package UUID. Alright, that is what we need to load. And then I also provide you some function here which is calculating the number of the token length, which is calculating the maximum number of the token length. So we put in a list of our texts, so a long list with all the different splitted texts, and then we're going to find out which one is having the maximum length. So we are splitting it here, we are looking for all the different words, and then once this one is found and splitted, we are calculating the length and we are exporting it finally and telling the user that the maximum token length is whatever number of tokens. Alright, let's just run this. And then for a very first small test, I just copied in this lorem ipsum from some lorem ipsum generator so that we have some dummy text to play with. You can also use whatever other text, but this one was just quickly defined so that we can make use of it at this place. And now we need to set up our sentence splitter. So for that, we define some parameter at first, which is called model max chunk length. And that is 256. So we can check that out on the model card. And here on Hugging Face, I just looked for this model, which is the default model here. This is the all mini LM L6 v2. And if you go through the model card, then you can find here at some place the description. By default input text longer than 256 word pieces is truncated. So we need to make sure that our split texts are not longer than 256 word pieces, so to say tokens, because otherwise the remaining parts are going to be truncated. That is something that you should always check out in the beginning, that you make sure that your splitting approach is fitting to the model that you are going to apply. Alright, so we know that our model max chunk length is this number, and now we can set up our token splitter. And for that one we use our sentence transformers token text splitter, and that is requiring certain parameters like the tokens per chunk, and that is exactly the number that we have set up here in this parameter before. Then we need to pass in the model name that we are going to use, and that is a typical model from this area. So if you look for sentence models, then this is one of the most prominent ones. And then it could be that the different chunks that we are creating could be overlapping. There might be certain reasons to have overlapping chunks. Actually here in this case we set the overlap to 0, and this will be then our token splitter. And now we can apply that. So we are going to store the result in an object called lorem ipsum tokens, and the result is coming from the token splitter, where we are calling the method split text, and we pass in here our object, our text object lorem ipsum. And if we split everything, we have now our lorem ipsum tokens, which are looking like that, looking good. And now we can check out the length of this. So we have our max token length of this object. which is 110 tokens. So it's below the threshold of 256. So that is checked, all is fine. And that was actually our starting point for checking out how we can split a certain text, how we can tokenize it, and then what the final result would look like. So we would then have a list of separate texts with a certain length. Hello and welcome to this lecture. Before we actually dive into the actual coding, I want to show you the full picture, the high-level picture on what we're going to achieve in the end. So we are working on some vector database which is holding the Bible, and it's working like this. The first part is that we need to have the underlying corpus. So we need to get the data as text file. Then the next part is that we need to work on the tokenization. So we need to split the text apart into smaller pieces, which then in the later step are going to be added to the database. But before that, we need to set up our vector database. Once we have that, we can take all the tokenized texts and add them to the database. And finally, I'm going to show you how we can work against the database and raise any questions, and the database is pulling out the most relevant documents to us. Great, this is what we're going to achieve. Thanks a lot, and in the next video we are going to start to code this together. Thank you and see you there. And now we want to check out the real implementation. And for that one, I want to have a large corpus. And what is a large corpus? The first idea that comes into my mind is actually the Bible. And we can get the complete Bible from Project Gutenberg. So for free online books, you might just head over to gutenberg.org, and here you can find many different free ebooks. And in our case, we are looking for the Bible. And here we have the King James version of the Bible. I just downloaded the plain text UTF-8, which is having a size of 4 megabytes. That's nice. And we have stored that in the subfolder data. And here we have the Bible TXT. And it's looking like this. Good. So the first part is simple. We just need to provide the relative path to our data source. So it's one level up, so the dot dot. And then in the subfolder data, you can find the file bible.txt. And now we can open that. So we are going to use our text path. We are just reading it with the encoding of UTF-8. We are opening this as F, and then we can store the result in an object called text_raw, which is coming from f.read. Good, that worked. So we can take a look at that. Text_raw. Okay, that doesn't show too much because actually it's much too long. Let's just take a look at the first 1000 elements, and it's looking like this. So it's a very long string, and here all the text is structured in that way that now we have all the line breaks in here, all the different sentences are here dot separated. So we need our character splitter. So we set up an object called character splitter, which is set up based on our recursive character text splitter. And this one is also requiring certain parameters like the separators. So it's looking for specific occurrences of line breaks, for example, like this, or like dots for separating the different sentences. And then And then I'm going to use a chunk size of 1000. This is because a typical token size in English is having 4 characters per token. And then if you take our limit of 256 times 4, then you are slightly above 1000. So this is just a test that our chunks might be ending up with less than 256 tokens if we choose this chunk size. And now we need to apply that character splitter. We are going to create an object called TextSplitted. And this is just calling our character splitter with the method splitText. And here we pass in our raw text. So this is making sure that this recursive character text splitter is applied on our raw text. And then based on these parameters, the result is stored back into TextSplitted. So all of this is working very smoothly. Let's just make sure that our maximum token length is not exceeded. So the maximum token length is 219 tokens below our threshold. That's all perfect. Actually, we can also check out the number of tokens by just calling the length function on TextSplitted. So we have that many different tokens at that point. And now we are going to apply our text tokens. So in the end, we are going to store everything in an object called text tokens. And we are iterating now over all the different elements of TextSplitted. And then every time we are applying our token splitter, again with the method splitText, and we take the current example from the TextSplitted. And then finally we are going to end up having our number of text tokens. Let's just make this a bit more verbose. So let's say this is our f string. And this is referring to the total number of splitted chunks. And then we are going to copy this and we are going to compare that to the total number of tokens. All right, it shouldn't take too long, just give it a few minutes. And you will see that for certain character tokens, there were some additional splits performed, so that the total number of the tokens is larger than the total number of the splitted chunks. So you always start with some character splitter, and then you can apply the tokenizer from the sentence tokenization. This one. So this one is corresponding then to the model that is used by the vector database. All right, then we can also check the maximum token length of the text tokens. Okay, 216. All still good. And now we can set up our embedding function. And that is our sentence transformer embedding function. Here we can also specify our model name. So this is the one that we are going to use. And if you have some GPU, you can set the device to CUDA. Otherwise, just use your CPU. Yeah, you can see here the default is CPU. So you could just leave this parameter out. And the model name I also could actually leave out because that's also referring to the default. But anyhow, it doesn't harm. All right, and now we are going to check the size of the embedding vector. We can also look that up in the model card, but we can also check it here. So we have our embedding function, and if we pass in here a certain text token, so let's take the first element of our text tokens, and then we take the first element of here. Yeah, so this is the expected result. So the size of this embedding vector is 384. So there is a vector with 384 different numbers, which is representing the context and the meaning of the sentence. Great. That was all preparation work. Now we can actually set up our vector database. And here we are going to make use of ChromaDB. So we can just create an instance called ChromaDB and call chromadb.client. And then inside our ChromaDB, we are going to create some collection. And we are doing it in that way. We take our instance here, ChromaDB, and call create collection. Then the name of the collection in our case is Bible. And we can also specify an embedding function. That is the one that we have set up before. Actually, I run here into an issue. It's saying the collection Bible already exists. So we can handle it in two different ways. I can create a different collection, or we could use a different function, which is get or create collection. So it's just getting the one if there is one, or it's creating it if it's not available. Here for now, I will just create one. So we create one that is called Bible 2. All right. And now we need to prepare our IDs. And for this, we just create some list comprehension. So we are iterating over the length of our text tokens. And for each text token, we are just calling this UUID to get some unique identifier. So let's just check our IDs. We need to put here some conversion. We want to have this as a string. And now we call again our IDs. Yeah, maybe just the first 5. That looks better. Okay, these would be our IDs. Just to have any IDs, it's just necessary to have some. And now we can add all the different tokens that we have. So we have our reference to our Chroma collection, and that object has a method called add. And we need to pass here a reference to our documents. And the documents are all our different text tokens. And we also need to pass in some unique IDs. So for that one, we made that effort with UUID to create unique IDs. And now it's iterating, once I call this, it's iterating over all the different text tokens and adding them into the database. Let's just start that. That is going to take a few seconds, not too long. In the meantime, while this is running, we can already perform some query. So also with the same object, chroma collection, there's a method called query. And here in the query, we can specify some query text. All right. We might just ask about one famous character in the Bible. What did Noah do to get all references or the top 10 references to Noah? You can specify this parameter here as you like. Then the result is stored in this object, and then we need to pick a certain key from this dictionary, and that is called documents. Okay, but for that I need to wait until everything is loaded into the database, and then we can move on. Alright, eventually everything is loaded into the database, and now we are ready to run the code that we already set up. So we have set up our query, we are asking about Noah, and we take a look at the different documents which are returned. And you can see that part is super fast. So once all the data is loaded into the database, the querying of the database is super fast. And then you can find here all the different texts. We are just quickly checking it. So there is some reference to Noah. And here you can see it again. So that seems to work quite nicely. And that is your very first vector database that you set up. We are going to dive much more into this in the upcoming lecture, but let's just recap for now what we have done in this one. So we have worked at first with some simple sample text on lorem ipsum, and then we have worked on the tokenization of that one. We used the sentence transformers token text splitter on this specific text, and we also made sure that our maximum token length is not exceeded, the one from the model, because otherwise everything extending the length would be cutted out. And then we worked on some real data on the Bible, on a really large data corpus. We loaded all the data, and we at first applied our recursive character text splitter, and then afterwards we used our sentence transformers text splitter so that we have all the different texts stored in our text tokens list. And then finally we took all these text tokens, put them into our database, and performed our first query against this database. Good. That was, I think, a very good start into this topic of vector databases and also tokenization. Thanks a lot, and in the upcoming lecture we are going to see many more details of how to interact with vector databases. Thanks, and see you there. Hello and welcome to this exercise. In this exercise you are going to work with a dataset on movies, and I created a problem, as you will see here. So imagine that's me, and I have watched in the past many movies, and typically I know the plot still, but I forgot the title. And I really want to see that movie again, so I need to be able to describe the plot and get the title. What is the obvious solution if you're a data scientist? Well, write a Python function. So the solution is to get the movie data in the first place, then set up a vector database, write a Python function which is able to search for the title by describing the plot, and it could look like this. So you could write a function which is called getTitleByDescription, then you pass in some query text and you get back some title or a list of titles. And the power of NLP you can see here actually, because in the query text we have monster and underwater, and if you will check the description, you won't find either of these words. You won't find the word monster, you won't find underwater, but still the meaning of these words were understood so that the right title was pulled out of a large list of different movies. So that is what we want to achieve. So that is the problem statement. And here are some tips how you can do that. Well, the first tip is of course that you need to get the data. I already downloaded it. You can find it in the subfolder data and it's called movies.csv. But here is the ground truth. So it's a data set coming from Kaggle and it's rather large, 350 megabytes if it's extracted completely. And we are just working with the columns title and overview. That's our description and the actual movie title. So all the rest is not relevant. You can play with it. You can make more complex functions, but for me it would be enough if you just work with these two different columns. And then you need to import the data in the first place. That's clear. You can tokenize the text or check out if it's necessary. Then you need to set up a vector database. And you can take all the texts, all the sentences which are describing the movies and add them to the database. And last but not least, you will write the Python function for querying some text and getting the most relevant responses back from the database. So this is what I would like you to do. And once you're done, you can compare your solution to mine. So this is what you will see in the next video. There you can take a look at my solution on this problem statement. Thanks a lot and have fun with this exercise. See you in the next video. Hello and welcome to this coding lecture. I've opened here the starter script, 30 movies start, and we are starting by taking a look at the different packages which we're going to need. So we are going to make use of regular expressions. Then we are going to import the dataset as a pandas data frame. We will also, this is not totally necessary, but we will use Seaborn to plot the distribution of the number of words in the descriptions column. Then we are going to make use of the sentence transformers token text splitter. And then of course we need our vector database. Again, here we are using ChromaDB. And here we have our sentence transformers embedding function. And finally, also not totally necessary, but for better looking results, I just use pprint from pprint. And these are the packages that we're going to use. All right, then the first part is that I also left in here some function for calculating the maximum number of words. So it consumes a list of texts. So we have a long list with many different strings, and then it's calculating the maximum word count of that one. And also I left in the sentence transformers token text splitter definition, the same that we had before in our coding lecture. So we can run this again. And now we can start by importing our data. So here I store the text path as a separate object. So it's one level up, and then in the folder data you can find movies. This is a subset of the overall movies dataset. So you can also download the complete one from Kaggle and work with the total one. But this is just for showcasing how everything is working. So I just used a subset because then I can still upload it to GitHub. And then we can import the data. I'm going to call the dataset dfmovies_raw. And we are making use of pandas function readCSV, where we pass in our text path, and we can also work on the dates. This is not totally necessary because we are not making use of the dates, but we know that this is our date column and we want to parse it correctly. So we can import it like this, and then we can take a look at the first two lines. Let's see how this looks. So it's taking a while, even with the smaller data set. And here you can see the two different items, the two movies at the top. So the import has worked correctly. And now we need to filter a bit more, because in the end, we need to make sure that we only have movies in our dataset where a title is available. So if there is no title or if there is no description, and the description column is called overview in this case, then we won't make use of that one. So here we can create an object df movies filled, and we are going to create this based on our raw data, and we call drop-in-a and specify the two different columns which are relevant to check. So it's taking only the columns title and overview and keeping that one. Now let's take a look again at what we have here. And again, just a small subset of it. Okay, so we have dropped all the NAs based on the columns title and overview, and we still have all the other columns in here. And now we need to filter for unique IDs. And for that, we can make use of the functionality drop duplicates. So if there is any duplicate entry in the ID, so if there's a movie twice in the dataset, then we are going to get rid of it. Okay, and finally, we can take a look at the shape. Okay, great. So we have close to 37,000 different movies in our small dataset. And now we can check the max word count based on the column overview to just see how many words these descriptions are having. And the maximum description length is 193 words, which is below the threshold which is coming from our model. And since this is the case, and there are no further special characters in our overview column, we don't need to do anything with regards to the tokenization. We can just work with the different descriptions directly as they are. So that is making our life in this case a bit easier. And now we want to check the word distribution. So for this, we create an empty list, description length, and we are iterating over our movies data frame, actually the filtered version, and we are taking a look at the column overview, and we are separating all the different words based on this regular expression, and then we have a list with all the single words, and then we apply the length function on it. And that one is then appended to the empty list at the beginning, and at the end we have for each movie an entry which is describing the total length of the number of words. Good. And now we can quickly visualize the word count. And for that we can just use from Seaborn the hist plot. And this is just making ourselves a bit more familiar with the data. So here we can see there are sometimes very short descriptions. Typically it's around maybe 30 words in a description of a movie, but then there's a long tail and it's going up to close to 200 words as we have seen before. So this is our distribution. We can directly use these descriptions and add them to the database at some later point. Good. Now we can set up our embedding function. and that is our sentence transformer embedding function. And now we could set up our Chroma database directly by making use of client. That is what we have seen before in our coding lecture. But now I want to show you how you can also create some persistent database. So we can create ChromaDB, the object, and that is coming from ChromaDB.persistent client. And persistent client is requiring some path, and I'm going to call the folder db. So once we run that, we will see that we are getting a folder inside our vector databases. Here we go. That one was just created, and it's a SQLite, so a local SQL database which is stored in the subfolder db. That's nice, and now we can actually hide that one. And I will show you a bit more functionality on ChromaDB. So you could also just run ChromaDB db, and here we have the method list collections, and this one is empty at that point. Not surprisingly, because we just started. Cool. And now we can get or create our collection. So we create an object called Chroma collection, and that one is making use of our instance ChromaDB. And here we can make use of the function get or create collection. The name of the collection is movies, and we also need to specify some embedding function, and the embedding function is the one that we have defined up here. So that's now our collection. All the movies are going to end up in this collection. Of course, you can have multiple collections. So this is just, you can imagine it as a table in a normal database. So now we have here our movies table. And if we check again with list collections, you will see that now there is a collection with the name movies. Very good. Okay. Now we want to add all movies to our collection. And for that one, we need to separate the different items. So we are going to extract from the column ID everything as string and convert that to a list. Let's just check that. And that looks good. So we can directly work with these IDs. And now we need to have our documents. This is our overview column, so the description of the movie. Again, we can make use here of the function toList. And then this time, we don't want to just have the IDs and the documents. We also want to store some more metadata. So we are not directly going to add this, but actually we are going to store the titles as well. And the titles are stored in the column title. So again, we extract that one and convert it to a list. Now we have all pieces together. But then once we want to add it to the database, we need to add it as metadatas. And here we can create for each item in the titles an entry. So this is a dictionary where we have the key title and the value is title. So this is just a restructuring which is necessary because we can only add it to the database in that specific way. So now we have our Chroma collection, and we can call the method add, and that one is requiring the IDs, the documents, and the metadatas. And now this is going to take a few seconds because all close to 40,000 movies need to be added, and especially the embedding needs to be created for all the different descriptions of the movies. Okay, it took a while, but then it ran into some issue. So it's saying the batch size of 37,000 exceeds the maximum batch of 5,400. Okay, so we need to add all the IDs, documents and metadata in batches. Good, let's start that. In batches of, let's say, 5,000. Good. So let's check that, if that might work. So we are iterating from 0 to the total number of movies, length of IDs, and we have here our batch size. All right, and every time we pick our IDs from the position I to I plus batch size, the same holds for the documents and for the metadata. Good. Then we will also print I to just see how good we are progressing, and we start it again. Okay, it took some while at my end, but now all the different movies are added to the database, and now we can check how many of them have ended up in here. So we can call the get function to get all the different elements in here. All right, so with get we can get all the different elements in here, and if we check the IDs, maybe there is a more elegant way than mine here, but if I check the IDs, I get a list of all the different IDs, and then of course I can just call the len function and we'll get that way all the different movies in here. Good. So everything ended up in the database. That's perfect. And now we are ready to create our function to get the title by the description. So let's call it get title by description, and in here we provide some query text as a string, and then we can call our chroma collection, and especially here the method query. That one is consuming some parameters like the query texts, because there might be multiple. Here we just add one query text, but still we need to put it into some list. So here this needs to be passed as a list, and then we want to have more than just one result. Let's say we want to see the top 3 results based on everything. Good. And now we can iterate over it. Actually, I want to have this parameter, the number of results, defined up here. End results is 3. Then we can pass it here and make use of it in our for loop. Okay, and then we can pretty print it. So at first we define our title, because here in our response we have the key metadatas, and then, like I said, here we might have multiple queries, so the result is also provided as a list corresponding to the different queries. Here we only provide one query, so it's always at the position 0, and then in here we have all the different results, and from that one we are going to take the title. So that's our first result. Then we are going to print the description just to check if everything worked in a similar way. So we have the key documents. Same again. Here we have for each of the different queries. Since there is just one, so we need to specify the position 0. And then for each item, we take the position I. Then we have our descriptions. And then just for separating everything, we put this separator line, and that should be it. So now we have our function, and we can run get title by description. And like in the introduction video, I will use the query text monster and underwater. And once we do that, we get these results. So now we have these ones, Octopus, Sharkenstein, and Empire of the Sharks. So that seems to work quite nicely. And now you have your database ready, and you can just play with it. All right, so whatever you put in here, it's finding the right films for you, and that works out quite nicely. So let's just recap what we have done. We have imported all the data. So we started basically here at this point where we point to our movies. We imported everything as a pandas data frame. We filtered the data a bit so that we have unique IDs. And then we checked the length of the different numbers of words in each of these descriptions. And then we put everything into our database. So we set up our reference to the database. Now it's a specific persistent database in the subfolder DB. Then we created a reference to our Chroma collection, and we prepared all the data, all the different objects, so that then in a batch approach, we add all the different elements into the database. That took a while, but eventually we succeeded. And finally, we were able to create our function, get title by description, and we tested it in the end by providing some text and getting out the right films based on that. So that was really fun and worked out quite nicely. I hope you succeeded on yourself and came to some very similar conclusions and similar code. So that is concluding our section on vector databases. And in the next lecture, we take this to the next level when we are talking about Retrieval-Augmented-Generation. That is very much fun. I cannot wait to show you that. So see you there. Hello and welcome to this lecture. In this lecture, we are going to cover a super interesting topic, which is called Multimodal VectorDB. And you will see how cool this technique is. Actually, it's one of my favorites in this complete course. But for that, we need to take one step back and take a look at the models which are available. And if you want to work with a multimodal VectorDB, we need to use a proper model. And one that was developed for this purpose is called CLIP. CLIP is standing for Contrastive Language Image Pre-training. And the main takeaway from here is that it was actually trained on images and texts. And that is a feature that we are going to exploit. So the embeddings that are going to be created are representing the text that the images were trained on and the image features. Actually, we are not going to use the CLIP model, which, as you can see here, is created by OpenAI. There is an open source version. So if you head over to this GitHub repo, you can find OpenClip and some description on how to use that. So it was developed with the same purpose as CLIP, but just as open source. And we can make use of the encoder from that one. And then our vector database is looking like this. We are having some images. Since the original model was developed on docs, I just follow the same fashion. I'm also a big fan of docs, so I found some freely available doc images, and we are going to use them and pass them into our vector database by at first passing them through our embeddings model, especially the clip embeddings. And then we have them in our vector database, and the actual data that is stored is corresponding to the images, especially the matrix representation of the images, as well as the embeddings. We spoke about the embeddings, of course. This is why we are doing that. And if you want, you can of course also put in some metadata. All right, let's assume now we have our doc images represented in our multimodal vector database. How does it work then? The cool thing here is that we are able to query our database in two different ways. We can pass in an image, so that would be the approach with image querying. So we take another image, pass it into our vector database, run a query with this image, meaning that again the embedding is created and the nearest neighbors are selected. So in coding it would look like this. In the query list we are passing in the relative path to the image, and then we need to specify the parameter query images pointing to this list of images. In this case it's just one, and the rest are just typical parameters which we can define in Chroma. And as a result we find another doc which is pretty similar. Actually it's the same breed, and this is showing us that the nearest neighbor search is working. So that will be then our result. We can also export the distance of that image. So that looks quite nice, and that is just one way of querying the data. The other one would be to query via texts. So now we are not passing in an image. Now we can pass in a text, for example. So for example, doc in grassland. Then this one is encoded, and the actual code would look like this. Now we don't pass a path to an image. Now we pass in the actual text, and as a result we get the nearest neighbor corresponding to the text. And that's quite cool. So that feature really impressed me, and in the next lecture we are going to see how we can code this together. Thanks a lot, and see you there. Hello and welcome to this coding lecture. Now we are going to implement our multimodal vector DB. For this, please head over to our subfolder for vector databases and open up the starter script 40 multimodal start, and this is the one which we are going to use for this lecture. As well as the images, just that you see them, we have them all stored under data, docs. We have here the different images. Alright, and then we can actually start. Let's open up our starter script. As always, we are starting with the packages. So we are going to use OS, basically to find the images in the end and listing the directories. Then we need NumPy and matplotlib. Of course, we need ChromaDB. And this time we are also going to use from some utils submodule a specific embedding function. In the theory lecture, I spoke about the OpenClip embedding, and this one is then the corresponding function we're going to import, OpenClip embedding function. And then also from utils, there is another submodule, data loaders. From here, we are importing image loader. And then, of course, we also need OpenClip. Let's run that. We can also take a look at the GitHub repo. So that is the package that I've already installed, and more you can find here on this GitHub repo, on the usage, how to make use of this open clip model, and we are going to see that in action. So at first we need to import our model. For that we are going to use OpenClip, create model and transforms. And in here we are going to pass our model. That's the vision transformer, a specific model. We can also check the model card on that one. And here on Hugging Face you can find the corresponding model card with all the different details on the training of this model and how to use it. Alright, and this one is returning a tuple with the model and the preprocess function. So we are assigning that one to our model. The second parameter we don't need, and then we are going to use preprocess. And the first time you load that, it's going to take a bit longer because it's downloading the model locally. But for me, it's already done before, so it's a bit faster. Now we can prepare our vector database. You are used to that already, so we are going to create a client. It's fine that it's not persistent by now. If you want to make it persistent, you know by now how to do that. You can either use the persistent client, or you can also specify here some database in the parameters. And what we also need is our image loader. For that one we have used the image loader from the submodule utils and data loaders. And we need our multimodal embedding function. So that's also the one that we have imported. And now we can create our collection. So we create our collection by calling our instance of ChromaDB, and then we make use of the get or create collection method. We pass in the name of our collection, which is called docs, and then we are passing in our embedding function, because that's the one that we need in this process now, and our data loader. Good. And that should be it. Now we can just run that so that the instance is created, and in a second we can start to add our images. At first I create a reference to our image folder, and that's one level above in the subfolder data docs. And then we can extract all the image files. So in OS you can find the method listdir, and then we have all the different image files in here. So these are the 6 different doc images which I have selected. You can also just play with different images. This is just a very small sample size to just show you how this is working. So actually we want to have the image files in a slightly different format. We want to have them together with the image folder, and then we want to basically have the complete relative path to the images, not just the file names, but actually the complete image file names with the path. So based on this list comprehension, which I have set up here, we can just do that. So we're iterating over all the different image files, and we append here basically our image folder, so that our list is now looking like this. Good. And now, since we have that, we have everything in place. We can call our chroma collection and the add functionality. And in here we can specify our IDs. It's just important that the IDs are unique. So you cannot have the same ID twice, But that's not the problem because the files cannot be duplicated as well. So that's fine. And then we are using our documents, which are our image files. And we can also store the reference to the files in the parameter URIs. Good, that's it. Now we can run that so that all the images are embedded and stored in the database. You might also store some metadata as well. I'm not doing that right now, but you might store additional information to the images if you want that. And now this one is running. You can see it was quite fast for these 6 different images. And now we have our database. So we can just take a quick look. Chroma collection, get, just to see that everything is in here. That looks good. So everything was stored. And now we can create some helper function, because in the end we want to have a one-liner to show the query results. And we are going to use a function like this. So the function is called show query results. It's consuming 2 parameters, the query list, which might be a list of texts or a list of paths pointing to images. And then we have our query results. This is the dictionary that we get as a return from our querying of the database. Then we need to know how many images we have. So we can get the count by just taking a look on how many IDs there are and then pointing to the length function. And then we iterate over all the different items in the query list, because there might be several images or several search texts in the query list. So that's the outer loop. And the inner loop is that we are iterating over our count of the different results. And from them, we are extracting the IDs, the distances, the data, and the URI. And we are going to use matplotlib to take the data and print it to the screen. So that's just a helper function that we don't repeat ourselves and code the same stuff again and again. So now we can use that function and we can perform at first our first query. So let's define our query list. And the query list is dog and grassland. And we can call our query result. That is coming from a call to query from Chroma collection. And this is the main difference between querying via texts and querying via images. So here we now use the parameter query texts, pointing to our query list, which is just a list with 1 entry. Then we want to have the 3 closest results. And in the return, we want to include all the documents, the distances, metadatas. It's not the case right now, so it's empty, but who cares? The data and the URIs. So if we call now our query result, you can find here that this looks quite nice. We have all the results and we can actually use our function show query results with the 2 parameters. And here you can see it. Now the first one, yeah, it's looking good. We can see some grass. So dog and grassland seems to be fulfilling quite good. Here's also a bit of grass. And here's no grass. So the distance is already quite large. Good, that works out. Now we can just copy this and use a different query. Let's just say dog with black fur, and we run that. And we can see that the black dogs are coming first. I'm just checking that the model actually works nicely. Now if we look for white fur, we should see the Akitas first. White fur, yeah. Here there is some white fur. That one, I don't know, white selected this one. And then the Akita is coming. That should be enough for now for querying texts. Now I'm going to show you how to query for images. And the interface is the same. We set up our query list and we can pass in here a reference to an image. Let's take our Akita. And now the difference is, like I told you, it's not query texts, it's query images. So it needs to know how to process the data. And we are going to return 2 results with, let's say, 3 results. And we include all the different parameters. And finally, we can also show our query results. So let's see what we have here. Yeah, not surprisingly, we have now the image itself. It's already part of our database. So the distance is 0. Well, it's just a good confirmation that it's working. Then that one is also having a distance of 0 because it's the same breed and also looking very similar. And then there is already a significant distance because it's definitely a different breed and looking quite different. So this can confirm that our model is actually working quite nice. Great. So let's just recap what we have done. We have set up successfully our first multimodal vector database. So for that, we have used a multimodal model, which is called OpenClip. And then the rest was just using ChromaDB. We had to make sure now that we pass in the corresponding embedding function and the corresponding data loader. And then the addition of the images to the database was quite simple. We just had to create a list of all the different images of the dogs. And then we were able to directly call the add function from Chroma collection and pass in our IDs, documents, and the URIs. And finally, I showed you how we can make use of this and query for texts either, or querying for images, which we provide. And the algorithm is working quite well, so with that we can see that the most similar images or the most similar images corresponding to the text were pulled out of the database. Great. That concludes our lecture on multimodal vector databases. I hope you find that as impressive as I do, and you can use that in your own projects. So that's concluding now our lecture on vector databases. Thanks a lot, and see you in the next one. Hello and welcome to this new section. In this section we are going to talk about OpenAI, and we are going to cover these different topics. We're starting with the OpenAI API and all the different models which OpenAI is providing. So we are laying the foundation for the remainder of the course, because then we also speak about ChatGPT, which is underlying the NLP hype that we experienced recently. Then you will find out how you can set up some API key, because later on we are going to interact from Python with OpenAI's API. So we need to set up in the web interface the API key that we're going to use. Then I'm also telling you a bit about REST APIs, because this is what is happening in the background. You're interacting with some REST API service. And then we are going to take a look at the Python interface. So OpenAI is also providing some nice Python package, and you're going to explore how you can interact with the models from our Python interface. So that is what you can expect from this section. Thanks a lot, and we are starting in the next video. Hello and welcome to this lecture. We are now talking about OpenAI's ChatGPT, because that was a major breakthrough. And GPT stands for Generative Pre-trained Transformers, and then this is the complete name, Chat Generative Pre-trained Transformers. It is based on the model GPT 3.5. In the next lecture, we are going to learn more about the different models which are provided. It has a model size of 170 billion parameters, and it was fine-tuned with some supervision and reinforcement learning techniques. And the prototype was launched in end of 2022. And from the start, it became very famous and very much used, as you can see here at the right-hand side. So here you can see how it's compared to other models and also other services, how steep the growth of the user base was for this specific program. And this specific model is also stateful, so it's also able to remember some previous prompts. It has some moderation filters, which are enabling it to avoid some racist or sexist prompts. There are just a few limitations, so the model always needs to be trained on a specific training base, and then it's deployed, so it doesn't have any knowledge after the cutoff date. So at the beginning it was 2021. I think now there is some updated version which is trained until somewhere in 2023. And you will also see that the answers are often quite long, which is also based on the fact that reviewers during the training were preferring longer answers over shorter answers. If you head over to this specific examples page, which is provided, then you can easily find out about different techniques, about different types of applications. So here you can find different tasks for which ChatGPT can be used. And you can head over to this page to understand all of them in more detail. And then actually I'm just showing you here as a developer in which different ways I am using ChatGPT. So I'm using it, for example, for explaining some algorithms or concepts in simple words. So here you can see I asked it how can it tune hyperparameters for a CNN, and then it's providing a really good answer, very comprehensive on the different options. Also, if I want to debug some errors, I just take the error message, pass it in here and ask it what does it mean. And then it's also providing a good advice on how to move forward from there. Also, if I work on some code and I have some issues with the code, it's not working for whatever reason, I can use ChatGPT as a sparring partner for debugging the code. So I just hand over the code, ask it to debug it, and it's perfectly finding the errors with the code. And actually it provided a much better result than my original code that I provided here. So it's really explaining the issue in detail and providing a really good result. And also you can start creating code from scratch. So you can ask it, for example, can you do me a favor and create some code for custom training of a semantic segmentation model. And then it's describing the different steps and also provides you with certain code snippets that you can directly use. Also, if you want to refactor your code, you can also pass it over and ask it to restructure the code in a way that it's better readable or shorter. And here for this code snippet, it was also able to make the code much nicer. And I'm also using it for code documentation because sometimes I'm also a bit lazy and don't provide as many doc strings and inline documentation as I should. So then I can just ask it to create some doc string for my function, and it's then adding it to my function. Alright, these are just some examples in which way I'm using ChatGPT. And in the next video, we are going to take a closer look at the OpenAI API. Thanks a lot and see you there. Hello and welcome to this lecture. Now we are going to explore in more detail the API which is provided by OpenAI. At first, let's take a look at certain milestones which the company has surpassed. So it was all starting with the different versions of GPT. So the different models were deployed, starting with GPT-1, deployed in 2018, which is having a model size of 117 million parameters. And then you can see how it's scaling up. So the next model is more than 10 times as big as the previous one, with GPT-4 deployed a bit more than a year later. Then we get to GPT-3, again roughly a year later. Now it's already having 175 billion parameter. So again, an increase of the model size by the factor of 100. And then we are having GPT 3.5. So that is the model underlying ChatGPT, at least at the beginning. Nowadays, we also have GPT-4. But let's come back to GPT 3.5. This one is having the same model size as GPT-3, and it was deployed in beginning of 2022. Then in November 2022, ChatGPT was deployed, which was a wrapper and a nice interface to interact with GPT 3.5. And then in March 2023, the first version of GPT-4 was deployed, on which we don't know how many parameters this model has. And I want to add here one more thing, because what is the underlying base for all of this? Well, it's a paper, and that is the paper which is called Attention is All You Need. It's super famous, and it's the paper which is describing the idea behind transformers. And that one was published in mid of 2017. And all these different models that you can see here are mainly based on this paper. So all these extremely powerful models which we are seeing nowadays are coming and derived from this specific paper. So you can hardly find something scientific which is having such a big impact. All right, then let's talk about different models. In the ecosystem of OpenAI, you can find nowadays many different models. We are having GPT 3.5 Turbo and GPT-4 and GPT-4 Turbo. These are the different NLP-based models. So I have here the different model types color-coded. Then OpenAI also has some computer vision model, which is called DALL-E. And there are certain models for running some audio models. So we have some text-to-speech model and the opposite, a model that can convert audio to text. So both are coming from the area of audio modeling. And then we also have some embeddings, different embeddings models, which are also coming from the area of NLP, and some other ones on moderation or GPT base, which I don't cover here. So mainly we are going to interact with GPT-4 and GPT 3.5. And implicitly with the embeddings, which are also provided. Let's take a look at the playground. We are going to take a look at the OpenAI playground in a second. But here you can see the different parameters which are available. So it's always starting then with the model. So at the top right, when you open the playground, you can find the drop-down menu in which you can select out of many different models. Then the next parameter that you can choose from and which you can modify is the temperature. That is controlling the randomness. So you can scale it down to 0 to get some completely deterministic result, or you can even push it up to a value of 2. Then it's providing much more random results. And if you increase the temperature, then you get more variation in the data. And the result is becoming less accurate. Then we have the maximum length. That is a number which is counting the tokens which are to be generated. So you can limit the response basically then with this parameter. Now we also have some parameter called top P. We are going to take a look at that one on the next page. And we have some other parameters on penalties, some frequency penalty and a presence penalty. Both are controlling the repetitiveness. So one parameter is discouraging the model from repeating same words, and the other one is encouraging the model to include more diverse tokens. So both are going into this direction. And then I told you that we are going to cover the top P sampling. The top P sampling is provided in a range of 0 to 1. So you can provide this parameter, for example, to be 0.9, meaning 90%. And then the model selects the minimum count of words whose cumulative probability exceeds the probability value. And with this, you can find the right balance between diversity and likelihood. So here is one example. We are starting the sentence with "the coffee is really," then there is a range of different possible next words. So the coffee is really strong, bold, great, tasty. All of them are having a certain probability. As you can see here, these are completely made up numbers, but it's just for explaining the idea. And then if you provide the top P parameter, for example, to be 70% or 0.7, then it's only taking the words into account which are in the top 70% of the cumulative probability distribution. So here it would now only take the words strong and bold into account, because then we already have achieved the 70%. If we increase this parameter to 0.8, then suddenly the next word is also part of the selection list. So this is just giving you some hint on how this parameter is working. In the next video, we are going to take a look at how the Python package for the OpenAI API is working. Thank you and see you there. Hello and welcome to this lecture. In this lecture, I'm going to show you how you can get your API key. For that one, please head over to openai.com and you can click on Login. And then you have different options to create an account. So you can just click on Register if you don't have an account yet. Or you can use social login with Google or Microsoft or Apple. So I've done that before, so that I can just log in, and then I'm going to click on API, and then you need to set up some API key. You can see here I've created some before, and you can see then when they were created, when they were last used, and if you just click on Create New Secret Key, you can just call it whatever you want. I just call it Applied NLP Course. And now I'm clicking on Create. Now this is our API key. Just copy it. And then you can click on Done. So this is the one that we are going to use. Now you cannot get back to it. You have to click on the copy button when it was created, and later on, if it was exposed or stolen, you might just revoke the key here. But for now, let's assume that this is all fine. Then I'm going to show you how you can modify it then on your local system on Windows. So I just search for environment, and then I find these system properties. And then in the system properties, you can find here the environment variables, which you can then click. And then you can just click on New. Then we can just call it OpenAI API key. We can paste it in, click OK, and then it's available in our system. Good, once we click OK, it's available, and from Python we can use it then. Hello and welcome to this lecture. Now we are going to take a look at the Python package, which is provided by OpenAI. So the official package is called OpenAI. We can just easily install it with pip install OpenAI. Then if we want to interact with OpenAI, then we can just do it. We can import the packages, OS, because we want to fetch some environment variable. And then we need to import OpenAI from the package OpenAI. And then we can instantiate a client by calling OpenAI and providing the API key. And one very important advice is that you should never put your API key into your code. So always separate your code from your environment variables or from your secrets. So the best idea is to store it in some environment variable, and then you can fetch it via os.environment.get, and then you can pass in the name of the API key, which might be like this. So then the client is ready and you're able to connect to it. In the coding lecture, we are going to see where we can actually create our API key. So just wait for that. And then we can create our API call. So for that, we just have to call the client and then the submodule chat completions create. We need to set up some messages. So here we just define our role user and we provide some content. And we also need to provide some model, the model which we are going to choose. And for cost reasons, or a very good balance between cost and performance, is this one, GPT 3.5 Turbo. Then we get the response stored in our completion. And if we want to get this actual message, then we can just call it via completion.choices. There might be multiple choices. So typically we're interested in the first element and then in the property message. But you can also take a look at that on the next page. So the response might look like this. We can see here our dictionary and there are some parameters, but mainly we are interested in the choices, and then we get back a list. So we're interested in the first element and then from here in the messages and then in the content. All right, that's it. In the coding lecture, we are going to see how this is working. All right, then you can head over to Visual Studio Code, jump into the folder OpenAI. There you can find a file called chat.py. And here we have some boilerplate code which we can use now. We are importing OS and then we are importing OpenAI. These are the packages that we're going to use. Now we are creating our client. This is our instance of OpenAI. And here we can make use of our API key. So we are just fetching it from the environment variables in that way. Here you can see the name of it, OpenAI API key. Then once this client is instantiated, we can call our chat completions. And here we are creating our messages. So we are for now just working with the user prompt, and then in the content I just provided some sentence. The coffee is extremely, and then I'm asking it to extend the sentence. So these are our messages, and then we need to specify our model, which is GPT 3.5 Turbo. Good. Finally, we want to see that everything is working, so we just print our response, which is stored in completion.choices at position 0, and then the property message. Let's run this. And here we have the response. So the response is our message, and here we have the content. We might even just say we are only interested in the content, and then we get back this single word. All right, this was just a quick test that the connection is working and that we now have set up the OpenAI API correctly, and we are up and running and can use it in the next lectures. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now I'm going to tell you what a REST API is, because we're going to interact with OpenAI's API, and that is also a REST API. So the same logic applies here. Whenever you want to interact with some web services, The most common API standard is REST API. And REST API stands for Representational State Transfer Application Programming Interface. And you could say that web services typically communicate with the users via APIs. And the API is just defining a set of rules for applications to communicate with each other. And the system is quite simple. Let's say you, as the user, are sending a request to a REST API or some other alternative systems like GraphQL or gRPC. They work pretty similar. So you send a request, then the REST API might itself also ask for some data or some responses from other servers. Then it's getting the answer from these servers and providing it to the user. So this is the general system. You are interacting with the REST API server, and on the next page you will see a bit more details about the URLs. Because the URL is already providing a lot of different details about the REST API. Whenever you use a browser, you see this HTTP or HTTPS. This is our protocol which we are using. There are also other ones like FTP. Then we have our domain name. That is our .com or whatever top level domain address. Then we can specify a certain port, or if there is no port specified, then it's the default port of 80 for HTTP. And then you might see some other information behind that, starting with a slash. And then these are pointing to a specific application, to a specific resource, and also some parameters might be passed in that way. So this in total is then our RESTful API endpoint. And there are different HTTP methods. So we have seen this process before. Typically you perform some GET or POST request and you get some data retrieval. And as a response you get some JSON data. And then one of the HTTP methods is GET. This is just used for retrieving some data. Then we have also some POST requests. So this is typical in our case now because we also want to send some specific data. So then typically you use some POST request. Then there are some other methods which we're not going to use in this course, like delete or put for deletion or updating of data. So we are mostly working with POST requests. And we have seen these code snippets before. So we are defining our user request and we can use the wrapper which is provided by OpenAI. So this function or this class is providing all of the functionality to cover the REST API. But under the hood, this one is creating the REST API call, which is a POST call. It's sending it to the OpenAI API. And then this one is returning the JSON object as a response. Good. This is what you need to know about REST APIs in the context of this course on OpenAI's API. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now we're going to take a look at the web interface from OpenAI. If you head over to platform.openai.com, then you are greeted with this page where you can see a lot of different APIs that you might explore. So you can use this as a good inspiration to get started with the different areas. But here at the left hand side, you can find now different areas, like for example the playground. That is very helpful if you quickly want to explore something. So you can set up here your system prompt and the user prompt, and then you get some result once you click on submit. And here at the right hand side, these are the different parameters that we have seen in the video before. So we can select between different models. Then you can also control the randomness with the temperature. You can also control the length of the token which is generated. You can specify the top pre-parameter and also provide some penalties for the repetitiveness, for the frequency and presence. So this is our playground, but we are rather going to interact with OpenAI from some Python interface from VS Code. But here you can also just explore it in that way. Then we have seen that one before. Here you can find the API keys that we have set up. And another thing that I want to show you is the usage, because you might want to explore how much cost was created up to this point. So you can see here on a daily basis how much cost was created based on the different models and your activities. And then you can also make it a bit fail-safe. In the settings, you might just go to limits. And here you can just set up some monthly budget. So if you want to make sure that you don't run up into any surprises, just set up an upper limit on what you might be using, and then you won't be surprised with a high invoice. So I would set up these limits. Then you can also set up billing. And then you also might want to set up some payment methods. You can check out the history. So these are the typical areas with which I'm interacting. All right, thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now we are going to take a look at different models and the cost of these models. Please check out the source which is stated here, because the prices might change over time, but at the time of the recording of this video, these are the prices. So we can see here the different models, and there is quite some variation between the prices. And I want to just make you aware of the fact that if you use GPT-4, then the price is even 60 times higher compared to GPT 3.5 Turbo. So typically GPT 3.5 Turbo is the model which I am using because I'm quite satisfied with the results, and it's a good balance between performance and price. Thank you very much and see you in the next lecture. Hello and welcome to this new section. In this one we're going to cover the interesting topic of prompt engineering. The first question that we might ask is why? Why do we need prompt engineering? One reason is definitely that we can get improved results if we get the prompt right. Then we also have better control about the large language model if we set the prompt correctly. In some cases it's even inevitable, especially if we're working on very complex tasks, then you need to engineer the prompt right. Also for some advanced features, then you need to have some skills about prompt engineering, and you can improve the user interactions with it. Let's talk about narrow NLP and large language models. Because if we speak about narrow NLP, it means that we have some training data and then the data is trained in a model, for example, on text classification. Or you take the data and train it on some sentiment analysis, or zero-shot classification, or many other things like translations. So each task is having its own specific model, and each task-specific model is trained separately and used independently. And this is different with large language models, because with large language models, all these functionalities are covered under the same hood. So you have your data and everything is passed into some large language model, and all of these capabilities we have seen before can be covered with just one model. There are some advantages and disadvantages of large language models versus standalone models. Large language models can be used much more versatile, of course, because they are so broad in their capabilities. Also in terms of generalization, it's better and easier to use, and there is less maintenance required, especially if you use some closed source LLM, because somebody else is hosting and developing it for you. The disadvantages are the cost, because you have a large model for something that might be achievable with a much smaller model. So cost is definitely a downside. Then these closed source LLMs like OpenAI cannot be used offline. You need to be connected to them via internet. There also might be some privacy concerns because you just send your data to some third party, and if the data is super critical, there might be some concerns about privacy. And then since LLMs are so large, it's hard to interpret the data because it might be pulled out of a complete different scope. If we have a standalone model, some very task-specific model, then the result is much simpler to interpret. So, let's cover how prompt engineering is working. And first of all, what is a prompt? We are always starting when we are interacting with some large language model with some user prompt. And this prompt might include some context. Also the length of the results might be defined in here. You can define then also the format that you want to get out. You can define the tone. So all of these things are embedded into the user input, into the user prompt, or also into the system prompt, but that's a different story. So this is what the user is passing in. And then the model output, you know that it can be text or specifically code, which is just a subset of text. Or nowadays, since the models all become multimodal, there might be also images as an output. So now you know what a prompt is, but what is prompt engineering? Well, this is some iterative loop. So we have our user prompt, and the prompt might not be effective from the beginning. So we are passing it into our LLM, and then we get some model output, which you can evaluate based on the quality that you get and the relevance. And then let's assume this is you are the user. Then you can ask yourself if the LLM actually understood what you wanted it to do. You can also further work on the output. Is it returning an output in the format and in the style that you want to have it? And then you can iterate over everything, and you can adapt the prompt so that you start at the beginning again. This is some iterative process. You adapt the prompt, you get different results, and you have to check again how satisfied you are with the results. And if you want to engineer the prompt to improve it, then there are some principles. So one of them is that you should provide some very clear instructions. You also might divide the task into subtasks. The next advice might be that it's often helpful to use some delimiters. In certain cases, it might be relevant and helpful if you ask the model for some explanation why it came up with a certain result. Then you can use and define some personas. So you tell the model to act as somebody else, and then the model is reacting in that way. And that is called then to be using personas. It also might prove helpful if you provide some examples to the model so that it's simpler for the model to understand what you expect of it rather than some general advice. You can also control the output. There are different ways on defining the style of the output which you want to get. And also another trick is that you might ask it for multiple outputs in the first place and then to select the best ones out of it. And in the next videos, we are going to take a look at all of these principles in practice. In this lecture, we are going to talk about clear instructions, because clear instructions means that you want to include very relevant details, like for example, the output format that you are expecting, the complexity or the length of the answer, Also the level of detail. Do we expect the model to act as an expert or provide results only on a high level? So here is a bad example and a good example. So the bad example is write a function to calculate prime numbers. Well, what might be not so good about this one? It doesn't even state the language in which you expect it. Now, if you only work with Python, that's clear for you that you mean Python, but how should the model know? So a better approach would be to add many more details into it. So instead of writing it that general, you could write a function in Python to calculate the first 10 prime numbers, provide a docstring and document all code lines. So that should provide much better results. All right, let's check that in OpenAI Playground. Here we're not using the system prompt now, we are just using the user prompt. Write a function to calculate prime numbers. All right, once we do that, it's assuming that we are speaking about Python, so that's fine, but we can still improve it. And then we are using the longer prompt that we have defined before. Now we take this longer definition and yeah, it's still Python, okay, but it's also providing the docstring that we asked it for. It's providing some inline documentation of what it's doing and why it's doing it. So this is a much better function and a much better result. Let's take a look at another example. So another poor example would be, in which altitudes do airplanes fly? Let's take a look at that. Okay, let's see what the system provides. All right, this is already quite good. When I tried that before, it was only providing information about large airplanes, which were flying on a higher altitude, like this one, 30 to 40,000 feet. And it was not providing information about smaller airplanes, which are flying much closer to the ground. But still, we can check how we can improve that with this more versatile and more clear instruction. All right, so this is providing many more details about different types of jets, and I consider this a much better answer than the one before. Great, so now you have seen how important it is to write a good and very clear instruction. And in the next lecture, you're going to see how helpful it is to use some personas. Thank you and see you there. Hello and welcome to this lecture. Now we are going to talk about personas, and you will see what this means in a second. So up to this point, we just used the user prompt, basically in the same way as if you would just use ChatGPT, where you just have a text input field and cannot separate between system prompt and user prompt. But actually on the playground, you can separate both. So you can provide a prompt which is twofold, which is having one area corresponding to the system prompt, and then you also have the user prompt. And the system prompt, this is providing some instructions to the model, which is to influence the model behavior. Also with the system prompt, you can set the context and you can guide the response of the model. Whereas with the user prompt, this is the actual instruction, what the model should do. Let's take a look at some examples. So this is actually a cool one. You could provide the system prompt, you shall act like a Windows CMD prompt, only reply with CMD output, don't write explanations. And the user prompt would be then typical commands on the command line. Now we head over again to our playground and we pass this in as the system prompt. And then we use some typical Windows commands to get the output. And that's cool, right? I mean, this is really acting like when you're working with a command prompt, and now we can change into the different folders. We can change into the users folders and check out the different folders in here. It's all dummy data, but still it's really nice to make yourself familiar with a certain system. So now let's say I want to add a new folder under users for my name, Bird. And then we can check with dir again that the folder was created. And that's amazing. So I really like this example, and you can use it to act like a Linux shell or whatever. And you can use a large language model to learn to interact with certain environments, even if this model is just coming up with random data. And yeah, it's really behaving as if it is a command shell. Great, so we have seen how cool it is, how helpful it can be to tell the model to behave in a certain way. And there are many other ways on telling the model to behave in a certain way. And this was just a very specific example, but you can come up with your own ideas. All right, and in the next lecture, we are going to take a look at delimiters and in which way they can be helpful to us. Hello and welcome to this lecture. Now we are going to talk about delimiters and why delimiters might be helpful. Delimiters can help the model to separate different sections. So there are different typical delimiters. One would be the triple quotations like this. And then inside the triple quotations, you can write your text. Also typical are XML tags, where, for example, you put in your information in XML tags, like, for example, in these text elements. And then you might provide the system prompt. You will get some XML tags, text, tell the user which one is more correct. And then you have certain examples. Let's try that one. All right, so we set up our system prompt and then several of these XML tags. So Hamburg is in Germany, Paris is in Spain. And the first text tag is more correct because Hamburg is indeed in Germany. The second is incorrect as Paris is in France, not Spain. Perfect. So that works quite nicely. And this is just one example. So sometimes the model might have problems differentiating different sections, and in that case it's really helpful and beneficial to use certain delimiters. Thanks a lot, and in the next lecture you are going to learn why it's helpful to divide a task into different subtasks. Thank you and see you there. Hello and welcome to this lecture. Now we are going to take a look at the division of a task into different subtasks. And you do that because the model can, based on that approach, better and easier follow if the steps are described explicitly. So here we have some system prompt. So it's saying, use the following step-by-step instruction to respond to the user. Step 1, the user will provide text in, and then we use our delimiter approach again, translate it into German. Step 2, use the output of step 1 and translate it back into English. In both steps, no comments, only the translation. All right, let's try this. So again, we use here our system prompt and then some idiomatic phrase, which is valid in English, but it's having a completely different saying in German. So we will see. So it's saying, es regnet Bindfäden. All right, it's not really doing it. So it's just doing step 1, but it doesn't do step 2. So we are trying to solve that and provided a bit more information on what I'm expecting. So I'm saying step 1, step 2. Let's see if it's now working. Okay, after some further trials, I made it that way. So we have now the 2 steps described here. And then I just said in both steps, no comments, only the translation. We had that before. Provide response for step 1 and step 2. And now we have it. Now we have here the response for step 1 and the response for step 2. So sometimes it's helpful to have these subtasks defined, and this might help to get a better understanding. It was also shown in certain mathematical problems that if it's directly jumping to a conclusion, it's providing not the right result, but if you ask it to provide sub-steps, then it's suddenly getting the right answer. Great. In the next lecture, we are going to take a look the helpful advice of using some examples. So we are going to see how the model responds if you provide some examples to it. Thanks and see you there. Hello and welcome to this lecture. Now we are going to see how the model responds if we provide directly some examples. So in certain cases it might be beneficial to provide examples rather than general instructions. The typical approach is to provide general instructions, but in certain cases it might be simpler and better to use examples. So here we have some example. As a system prompt, we define provide output only as emoji, create a series of emojis which describes the sentence. And here is the example. A happy robot flies with an airplane to climb a mountain. I'm not super creative. This was my creation. And then you can see we have the happy robot flying and we can see the emoji for a mountain. So this would be the example that I provide. And then we want to have the corresponding emojis to the sentence, a man meets a woman and falls in love. Let's see how this plays out. So again, we are copying in our system prompt. And here's some special character we have to get rid of. Okay. And now we take our user prompt and we see, yeah, a man, a woman, and a heart. Okay, fair enough. That's looking good. And here is a different example. So we are providing some text and the result directly. So we are telling it what the input is. It's a beautiful day, and the output is tone. And then again, the next text is I'm sad, and we are expecting it to provide the corresponding tone. Now for that one, we only need the user prompt, and we can paste it in. And since the first one was positive, that one is now negative. Great. In the next lecture, we are going to see how we can control the output of a model. Hello and welcome to this lecture. Now we are going to take a look at different possibilities and options to control the output of a model. So you can control the format of the result, the length, the style, the tone, the context. So all of this is possible. And here is one example. So you can also take these examples and directly run it in the playground. So to get different results in terms of the format, you might provide a system prompt, like summarize the text in this specific delimiter. And then you can control, for example, the verbosity. So you could write in a paragraph, in a brief explanation, in detailed explanation. So these would be different options. And now let's take a look at that. All right, so we take our system prompt, and then we can write here in a paragraph. And let's take some sample text from Wikipedia on the solar system, and we pass this in like we told it here. We are putting it into this delimiter, and here is the information on the solar system, and we ask it to summarize it in a paragraph. Okay, that would be one paragraph. And now we can take everything and put it in here again and say in a detailed explanation. Let's see how the model responds now. right, so this is just one paragraph. Now this is not much longer, but a bit more structured. So there are also other examples where this might provide much different results. You might also go and specify the length. So you could tell the model to provide the result in just one word, in a single sentence, or in maximum 50 words. Okay, in one word, it's just solar system. And if we say in a sentence, okay, again, these are 3 sentences and it's not working perfectly. Let's say in less than 30 words. Okay, fair enough. That looks quite okay. Good. The next one is that we can ask it to define a certain style. So you might ask it to provide the response in the style of, for example, a certain person. A nice example is always William Shakespeare. Or you might ask it to provide the result in a valid JSON object, like with key and value. Here we can see the power of providing it with some example, or in XML format. Let's see how this works. So let's say in the style of William Shakespeare. Let's get rid of this assistant output and okay, it's even rhyming, so I'm not an expert on Shakespeare, but that looks a bit like Shakespeare. Good. And now we say in a valid JSON object, e.g., and then we provide it with the information in case it doesn't know it, that valid JSON should look like this. And that looks quite nice. So that would be some JSON object. Perfect. And the last one is in XML format. Yep, that's also nice. Very well. So that would be our example on providing the style. Then we can also ask it to provide the response in a specific tone. So that would be that we are controlling the mood or the sentiment of the model response. And that could be that the tone is very formal, it could be casual, humorous, or I also like that one, as if you talk to a friend, or as if you want to explain it to a child. Let's see. Summarize the text provided in, and then we say, as if you talk to a friend. Looks good. And now we try the one where we are checking as if you want to explain it to a child. So the model is really able to get the persona right and knows how to talk to certain people. And this one is much more suited for the understanding of children, and it's really helping out to provide the information in that way. All right, then you can also provide some more context. And this is a bit overlapping with the clear instruction that we had seen before. So for example, a poor example would be, what is the weather today? Well, where? So you might ask it instead, what is the weather today in the afternoon in New York? Of course, this is not working with ChatGPT because the model is not directly having access to the internet, but you might use it with Google Gemini. And another example is to ask it to write a fictional novel, which is starting in that way. It was a rainy night, and then it is asked to extend the sentence here. So let's see. We are just starting over again and directly go with the user prompt. And then it's taking the beginning of the sentence and coming up with something that reads quite well. It's really able to just understand the context and extend on it. Good. These were just some examples on how to engineer a prompt in a certain way. And I really hope it helps you to get better results out of your large language models. And with this, we have reached the end of this video. Thanks a lot and see you in the next one. Hello and welcome to this new section. And now we are going to work with some advanced techniques from the area of prompting. So let's just recap, why would we need some more advanced techniques? Well, if we just have some simple prompting, that might not produce some very coherent or very high quality content, because we are directly jumping from the user input to the response of the LLM. And in some cases, when the task is more difficult, the model might need some more help. So for example, it might, in specific cases, require some specific instructions to understand the problem a bit better. And otherwise, simple prompting might just produce some irrelevant responses, and that is a big concern. Simple prompting might just jump to the conclusions. And that is not just a problem that an LLM might have. Just a quick analogy. In the Middle Ages, it was said that the stork is bringing the babies, and that was just due to the fact that people observed that storks and babies are appearing at the same time. So people were jumping to the conclusion that the stork is bringing the baby. Basically, people just mixed up correlation and causation, and we want to avoid the same problem with LLMs. So there are certain techniques which we are going to discover in this section. Some of them are shown here. So we have just zero-shot prompting, which has certain flaws, as we have seen. And then one technique that we're going to study is called chain of thought, where some intermediate steps of reasoning are brought into the chain, and that is helping the model. Another one is called self-consistency chain of thought, where not just one path of possible answers is developed, but a number of different chains is developed at the same time. So this is a bit looking like some ensemble approach from machine learning, where different models are developed, and then with some voting algorithm you get to a response. But then there are many other techniques that we are going to see in this section. So stay tuned. We are going to cover all of them in the next sections. Thank you and see you there. Hello and welcome. The first technique that we are going to study here is called few-shot prompting. We have seen that also in the basic prompting section, just not with this name. So few-shot prompting is meaning that in the user prompt, we are providing some questions with the corresponding answers. And the model is then able to get some deeper understanding of how the possible answers might look like and what it should basically understand and extract from this pair of questions and answers. And then at the end, we just provide the question without the answer, and the model is able to answer it, hopefully. So here, just in a few words, we just provide some few examples of the task alongside with some expected output, and then the model is able to learn from these examples and is trying to generalize the pattern out of it. And the pros of this approach are that the model is able to quickly adapt to some new task. This technique is also very effective when the task is very well defined and the examples are well defined. And we also can use this technique for customizing the output for our specific use cases. Some disadvantages are that the performance might be inconsistent when the examples are not completely understood by the model. Also, this technique is very much depending on the quality and the diversity of the provided examples. And there might be some risk of overfitting and poor generalization. Here is some example. I've just provided some multiplication examples at the beginning alongside with the corresponding answers. And then at the end, I just provide some question, and with a question mark, I want the model to answer this specific calculation. So that is one way of doing it, and very obvious in the case of mathematical formulas. And then you can also further generalize this idea. So here at the right hand side in the example number 2, I've created some mapping between an animal and the most likely corresponding colors. So the model is able to understand that there is a mapping, and we expect the model to understand that the elephant has some gray color, the tiger is orange with black stripes, and then what should the penguin look like? And the model is answering the penguin's colors are black and white. So these are some examples of few-shot prompting. And in the next lecture, we are going to see that this idea can be also integrated into other approaches. So stay tuned, and we see in the next lecture. Hello and welcome. Now I'm going to show you another technique, which is called chain of thought. So chain of thought should overcome this zero-shot prompting and the problem of jumping to conclusions by putting in some intermediate steps. So we start with our user prompt, and at the end we want to have our response from our LLM, and then there should be a number of different steps in between so that the reasoning is clear, which the model is providing, so that everything is making sense and all the steps are validated and we get some valid response for a given question. So the idea is here to use this technique to improve the reasoning capabilities, and this is done by breaking down a more complex task into a series of intermediate steps. So when we are creating our prompt, this prompt should include some initial task and some instruction which we are giving to the LLM to generate some step-by-step thought process. And our response, our output, should be able to show these intermediate steps and also showcase the complete reasoning process, and also at the end the final answer. And for this specific technique there are certain flavors. One is called few-shot chain of thought, and the other one is called zero-shot chain of thought. So here we directly see the approach from the last lecture. And here is some example how this is done. So we have our initial prompt. So we have some question. In this case, it's saying Sophia has 7 apples in her basket. Her friend Emily gives her 3 more bags of apples. Each bag contains 4 apples. How many apples does Sophia have in total? And then this is not the question that we want to get answered by the model, but this is just some example. So this is our few-shot approach, because here we are providing this question, we are providing the intermediate steps. So we tell the model that in the first step it should be able to calculate the number of apples in the 3 different bags from Emily. Then in the second step it should calculate the total number of apples, and in the third step it should add the results of step 1 and 2 before it is jumping to the answer, which is correctly then 19 apples. And only after that, or even after we provide more than just one question answer pair, then at the end we provide our real question that we want to get answered. So here now we could ask the model a very similar question, and then we leave out the answer and let the model do its magic and provide the answer, and then it will be able to infer the different steps which we have provided here and coming to the right conclusion rather than just jumping to the answer. So this is a more complicated approach because then we have to think about the different steps in between, what could be a potential problem of the model, how do we need to define these steps ourselves. So this might be very customized and very problem specific. So there is a more simple approach, which is called zero-shot train of thought. And that is super simple. And I really can recommend that to you because it's providing very similar results and it is very generalizable. So here we are just providing our user prompt where we are taking our question, and then at the end we are concatenating that one with the statement, please think step by step. And that's all. So this is avoiding the model to directly jump to the conclusion, and it's starting to initiate some thought process, and it's starting to think step by step. So let's take a look at some advantages and disadvantages of this technique, chain of thought. Chain of thought is able to encourage some LLM to apply some multi-step reasoning, and it can also improve the performance on some complex tasks. And along with that, it is able to provide more transparency into the complete thought process. So rather than just taking a look at the answer, and that might be just incorrect, now we get some deeper understanding at which point of the chain the model has problems to do the calculation right. So this transparency can be used then to adapt the prompt again, so there is still some iteration and you can get better and better in providing the right prompt. Then also chain of thought is helping the model to get some better reasoning capabilities, and it is also helping us as the users to understand what the model is really thinking and reasoning, and then we can also debug it. And going into the same direction of transparency, it is also increasing the interpretability of the output. And all of this is basically helping the model in more complex tasks where it's having sometimes problems with some logical reasoning, or also in the case of multi-step calculations. This technique of chain of thought has shown to be very promising and providing much better results than zero-shot prompting. Some disadvantages are that the output length is increased and the computational requirements are increased, and alongside that, of course, the cost is increased. Then also you have to say that the quality of the reasoning is depending on the ability of the model to break down the problem into its individual substeps. And also it's relying on the quality of the intermediate steps which are provided in the case of few-shot chain of thought. And there might be also some risk of compounding errors. So if there is an issue in step number 1 and step number 2 and every subsequent step is building up on this early error, then this error is compounding and the final result is getting more and more incorrect. All right, let's take a look at some example. So we can jump over to ChatGPT and ask it this question. So when a student weighing 54 kilograms left the class, the average weight of the remaining 59 students increased by 100 grams. What is the average weight of the remaining 59 students? That is a more complicated math puzzle which I found under the source, and we are heading now over to ChatGPT to check this out. All right, let's just see if this works. So we just start right away with direct prompting, and we will see if this one is correct. Okay, this one is not really working. It's stopping intermediate. It's not coming to a right conclusion. So now we can just add the command, please think step by step. And we take that and run it again. We don't want to have it providing this previous answer. So now we start from scratch, put in this additional command for getting zero-shot chain of thought. Actually, I just saw that I have a problem with the maximum length. That was providing some problem with the output. All right, let's try it again now and see if it's now able to provide the complete answer broken down by the different steps. So now it's providing a right definition of understanding the situation in step number 1. Then it's thinking about the equations and calculating everything. Okay, finally, therefore, the average weight of the remaining 59 students is 60 kilogram. That is the correct answer. Perfect. And also it broke down the more complex question into some individual sub-steps. So this is helping the model to understand the problem more easily, but also for us to understand the answer of the model more easily. And the complete way of finding the solution looks very good, as well as the final answer. Very well. So this concludes our lecture on chain of thought. Thanks a lot and see you in the next one. Hello and welcome to this coding lecture. Now we are going to start coding chain of thought, and for that I have navigated into the working folder for advanced prompt engineering, and from here I've opened the starter script for chain of thought. Now we can hide that one, and we are going to import certain packages. So as a backend, as our LLM, we are using here OpenAI. So we need to import the corresponding packages. Then we are going to import pandas, OS. OS is needed because I have saved my OpenAI API key in some environment variable, which is the preferred way of doing it. So I would really recommend you to do it in the same way. Never store credentials inside the coding script. So then we are assigning it to this property of our class OpenAI. And then we are also importing pprint. And after that, we can create a client, which we are going to use when we are interacting with OpenAI. All right, let's just run this. And then that cell afterwards. And now we are going to develop our function. So the function is called finally chain of thought, and it's just consuming one parameter, the user query. And here I left it blank. This is what we're going to develop now together. And afterwards, just to show you the full picture, we are providing some user prompt. This is basically some, let's call it some complicated mathematical problem. It's called Game of 24. And this is working in the following way. 4 numbers are provided to the algorithm, and these numbers can be combined with simple arithmetic operations like addition, subtraction, multiplication, and division. And the right combination of brackets and operations will lead to a result of 24. And it is shown that LLMs sometimes have problems solving these kinds of problems. So being able to solve it step by step is really helping the model to get to the right conclusion. So this is our user prompt. This is what we are then passing into our function chain of thought, which is making the call towards OpenAI. And we get back some result, which we are printing to the screen. So this is the whole idea. Now we just have to pass in the content here. So in our function chain of thought, we just need to start coding. We need to define at first the system role. And we can define our system role definition, which is just saying you are a helpful assistant and answer precise and concise. You can come up with other definitions. This is just providing a bit of guideline to the model, and now we can create our user query in a complete fashion, because here we are just passing in the user query as it is provided here. And now we are going to set our train of thought system up in a way like zero-shot train of thought, because that's very simple to implement. So all we need to do here is we need to provide our user query and append finally the command think step by step. All right, this is our user query. And now we can set up our messages. This is the object that we are passing to OpenAI as a parameter. And here we need to specify the different roles, but it needs to be passed all as dictionaries. So the first dictionary is covering the system role. And in here we provide the content, and the content is our system role definition. But then also we need to provide our user role. And in here our content is our user query complete. Good, this is the object that we are going to pass. And now the typical way of interacting with OpenAI is starting. So we are going to fetch an object called response. And for that one, we need to call our OpenAI client. And from here, the submodule chat completions create. And this one is requiring certain parameters, like for example, the model. And here I've defined that before with the model name, GPT 3.5 Turbo. So we pass our model name. And the second parameter is, of course, messages. Good. That is our response. That's a bit raw. There are many objects and details in here. So we are just interested in the real content. So we can fetch it from the response. There you have the choices, and we just take the first one, .message.content. And then we can return our content. Good, let's see if we made any mistake. Now we run our function definition and we call our function. So here's the result. Sure, here is one way to solve the puzzle using the numbers. And then there is a first step. And this is actually not really correct. Let's just try it again. So the answers are correct, but it seems it doesn't take all numbers. It is mandatory to use all 4 numbers. So you see, it's some iterative process. We need to play with the queries and adapt it to see if it's really working now. And yeah, that looks better now. Now we have several steps. The first step is checking the numbers 6 and 4. Then we have 24 and 3. And finally, let's see if this is making sense. This is 24. So it does break down the process into different steps, but it does not really find the real answer in the end. So we have to further increase it. Please check the final equation for correctness. So we check it again. All right, that still doesn't work. So we can add a few more commands, a few more steps or hints. So one hint is to identify the basic operations. Then another hint is to prioritize multiplication and division. Another one is to look for combinations that make the numbers divisible by 24. And the model should consider the order of the operations. It should think about parentheses. And then we can also provide a hint to practice with different number combinations. And yeah, let's try it now. So we have 4 times 3 times 2, which is 24. So finally we made it. You have seen that just with zero-shot chain of thought, it is not really solving the equation. It requires some further hints to get it correct, but finally it works out. So this should just provide you some guideline and some idea on how you can implement this idea of chain of thought. And with that, we have reached the end of this coding lecture. Thank you very much and see you in the next one. Hello and welcome. The next technique that I want to show you is called self-consistency chain of thought. And that is able to improve the coherence and the consistency of the answer. And it's doing it and it's getting some better results by performing multiple chain of thought experiments. And one predicament is that these experiments should be quite diverse. And then at the end, some voting algorithm is coming into play. So let's take a look at that at the right hand side. So we have our user prompt, and then we create not just one chain of thought, but a predefined number of chain of thoughts. Then we have multiple results at the same time, and we need some voting algorithm, which is finding out which is the most common answer out of these different chains. And then the most common answer is taken as the final solution and taken as the response. So if you have some background in machine learning, that is very much the idea of ensemble learning, where you are taking some weak learners. Here you can see some example. We have some test input, then we have a multitude of different weak models, and then all of them are providing some output, which is fed into some voting algorithm, and then a voting algorithm like the majority vote is taking the most common output and using it as the final prediction. So this is the idea of ensemble learning brought into the field of large language models. Good, now let's take a look at some example. So here again, since LLMs still have a bit of problem with mathematical reasoning, here we also have a similar question from this field. So it's saying when Michael was 9 years old, his brother was 2/3 his age. If Michael is currently 40 years old, how old is his brother now? Please think step by step. So now if we run that several times, we might get different solutions. The first output might be 37, the next one might be 35.5. The last one, in this case, we just have 3 runs. It would be again 37. If we use a voting algorithm like majority vote, it would find out that 37 was answered multiple times, actually 2 times out of 3. So the voting algorithm would pick this answer as the right answer and the final answer of the model. All right, and that's the idea of self-consistency chain of thought. In the next lecture, we're going to see some coding example for that one. Thank you and see you there. Hello and welcome to this coding lecture. Now we are going to implement together the technique which is called self-consistency chain of thought, and you can find that in the working folder Advanced Prompt Engineering. So we open our starter script and we can hide now this area, and as always we start by importing our packages. So again we are working here with OpenAI and we import the corresponding packages. Then we are importing pandas, OS. We use OS for getting our environment variable, which is storing the API key for OpenAI. And then we assign it to the corresponding property, API key. And then we create our client, which we need to interact with OpenAI. Let's run this. Now we can use our function definition for chain of thought, which we have developed in some earlier lecture. So we are just jumping over that one. If you need some recap on that one, just jump back to the previous lecture on chain of thought. But actually now we want to use that and implement self-consistency chain of thought, because this one is built up on chain of thought. And here, finally, let's take a look for getting some complete picture. Finally, we are using a certain user prompt. As previously in our lecture on chain of thought, we are implementing the game of 24. So the algorithm shall find the right combination of arithmetic operations to get to a result using these four numbers of 24. And then we are calling our function self-consistency chain of thought with our user query, where we are passing in our prompt, and then we take a look at the result. Good, let's do that. Now, in our function self-consistency chain of thought, we are requiring certain parameters. The first one is the user query, and then we also need some stop criteria. We need to define the number of chains which shall be created. So here we just define a default of 3, and now we can integrate the content into this. So finally we are going to store our results in the list. So we just prepare our object, and then what we are doing is we are iterating over the number of chains. So for that reason we have fetched this parameter, and we get the result res chain by calling our function chain of thought and passing in the user query. All right, and from here we can get the result, which is stored in res chain, and append it to our resulting list. Good, that's it. Now we have a number of different results created, and now we need to ask the model to get the most common answer. So for that, we just take all the results. Res concat is the object which we are going to create. And here all the different results are going to be semicolon separated. And here we basically take the list and convert it to some concatenated string. And now we can create our prompt. Let's call it self-consistency prompt. Again, we work with an f string, and we tell the model you will get multiple answers in this mask, separated by semicolon. And then we move on and say, here is the corresponding object, res concat, And at the end, we define our question, extract only the final equations, and return the most common equation as it was provided originally. Okay, this is just one way of implementing it. And now we can set up our messages. So the messages are created as a list. And here, now we make it simple. We just provide one role, which is our user role. We could also split it up and create again some system role and some user role. That is up to you. For this simple example, it doesn't make a big difference. So as the content, we just provide here now our self-consistency prompt. Good. Last but not least, we need to create some response. And we do that by calling OpenAI client.chat.completions.create. And we are passing in here our model. And that is our model name that we have defined earlier. And we provide our messages. All right, now we have a response and we want to extract from the response the real content. So we take the response and from here we pick the first choice and message content. Okay, and finally we can return this. Good. But also we might want to see the different results and the different intermediate steps. So we can also just print here our current iteration I. And in here we have our res chain. So this is the response that we get in each iteration. So that is what we want to see. And finally, we get back our result in the content. Good. Let's make this available and see how this works. Let's maybe increase the number of chains. So for that, we have this parameter, number of chains. Let's say 5 and run it. Okay. Actually, I need to modify the prompt to use the same one that we used before in our chain of thought lectures. So with the additional hints, it is providing much better results. So let's run it again. Okay, and here we get a valid answer in the end. So 2 times 12 is 24. Good, so that seems to work. So it's really that simple. Self-consistency chain of thought is just taking a number of chains of thoughts. So you can just iterate over it, create a number of different results, and then ask the model to extract the final equations and returning the most common equation. And that's it. So with this, we have reached the end of our lecture on self-consistency chain of thought. Thanks a lot and see you in the next lecture. Hello and welcome. Now in this lecture, I want to show you another technique which is called prompt training. And in prompt training, we are starting as usual. We provide some question to the model. The model is providing some answer. So this is then the pair of Q1 and A1. But then And then the specialty of this technique is that we follow up with some next question, Q2, which is taking the answer from the previous step as an additional input. And then this chain might go on for more than just 2 steps. And then every time we pass in a new question alongside with the answer of the previous step. So also here, this is a technique which is supposed to break down some complex task into its subtasks. And each of these subtasks has its own prompt together with the last output that was provided. So each prompt is building up on the previous outputs, and this technique can be used to incrementally solve a task. And then the final output at the very end is the result of the cumulative work of the previous steps. Let's take a look at some use cases. So the general approach again is that we are starting with some general target, and then we develop some sub-target 1 and so on. And that could be used, this prompt training, if you want to chat with some documents. But you could also use this technique for writing articles and breaking them down into individual chapters. And then the LLM is developing the article chapter by chapter. Also, you could use it in the field of programming, where you start out by working on the general logic, then you provide the previous output to develop some pseudocode, then you take the pseudocode for the next task and provide it alongside the task to write some actual code. Then you can take the actual code together with the task of asking to debug the code or write some documentation and so on. So there are more and more steps. Also, if you want to plan your next travel, you could break this complete task down into different steps. Like first you need to find some destination. Then out of this first step you get certain model answers. And from these model answers you pick one and ask it to plan the flight and find some hotels and so on. So this prompt training is also very useful in specific cases. Here we can see now some example. So our first question is to generate a brief outline for a short fictional story about a magical adventure. And the outline should include the main character, the setting, the central conflict, and a high-level plot summary. So we are starting out very high level and taking the complete picture. And then we can move on to the subsequent question, and we can provide this question like using the outline provided in, and then we mask it in that way and ask the model to generate the first few paragraphs of the fictional story to set up the characters, setting, and central conflict. And then we provide the output of the previous question alongside with the next question to get some answer. So this is the idea of prompt training. Also extremely helpful in certain cases. And in the next lecture, we are going to cover some other techniques which are coming from the field of reflection. Thank you and see you there. Hello and welcome to this lecture. Now we are going to take a look at some techniques which are taking reflection into account. So if you have some user prompt and some LLM response, it would be like jumping directly, like I said before, from the user prompt to some conclusion. And this might not be the best approach, as we have seen many times before. And this idea of having some retrospective and questioning the own answer, that is reminding me very much of Lord of the Rings and Gollum, who is constantly talking to himself and questioning the own answer. So first Gollum likes his own answer, but then he's questioning it and finding out, okay, this answer might not be the best one and there might be some iteration. So this is the whole idea of reflection, that you get not just a forward pass through the network, if we take this analogy, but also to take then the output and pass it in again at the beginning. And there are different ways of doing that, and we are going to see some of them in the next lectures. Thank you and see you there. Hello and welcome. Now in this lecture, I'm going to show you a technique which is called tree of thought. So tree of thought also tackles the problem of finding solutions to complex tasks which are requiring some exploration, and tree of thought is enabling some self-evaluation of the progress, and it's also allowing some intermediate steps. The idea is here to explore different solutions and evaluating the quality before some final path is committed. So there is also some combination of the LLM with some search algorithm, and you can read more about this idea in a paper called Tree of Thought, Deliberate Problem Solving with Large Language Models. And at the right hand side you can see some high-level example or some high-level idea of this approach. So we are starting with some user prompt, and the model is coming up with different solutions. So it's breaking down the idea into different steps, and it's building a complete tree of different thoughts. So there might be a first level of different thoughts, and then starting with these ones, there might be some subsequent thoughts, and then finally it's evaluating the consistency of a walk through these different thoughts and checking if the response is consistent to the initial question. So also here we can see some analogy to machine learning. In the statistical machine learning techniques, we know about decision trees, where we also have different levels and different final nodes or leaves of a tree. And then there are different ways to go through the tree to find out about possible outcomes. So this is basically bringing in the idea of decision trees into LLMs and checking then which is the right way to go through the tree to come to the right conclusion. You can also check the internet to find some implementations of this one. And in the next lecture, we are going to see the next technique, which is very promising. Thank you and see you there. Hello and welcome. Now, this next technique which I want to present you is called self-feedback. And this approach is iteratively improving the quality of the response. It's based on a paper which is called Self-Refinement, Iterative Refinement with Self-Feedback. You can read more in this PDF document, and the main picture I've taken here. Also, you can see my own implementation of that one. So we are starting with some input or some user prompt, which is passed into our model. And then we get some initial output. But then we are not stopping here, but we are instead reflecting on that one and refining it. So we are passing it again to the LLM to get some refined output. And that still might not be the last one. So there might be more rounds. So the refined output will be checked if a certain stop criteria has been reached. So basically it's checked, is this now sufficient to answer our question? Does it have any rating which is sufficient to us? So if yes, then we can stop. Otherwise, we start the next iteration round. But then of course you have to avoid to run into some infinite loop. So set up some maximum number for the number of iterations that you want to have. So it's a bit depending on the parameters that you set. But we will see all of that in the next lecture, which is going to implement that into some real code. Thank you and see you there. Hello and welcome to this coding lecture. Here, before we start with the actual coding, I want to show you the example that we are working on. So we develop our system prompt, and the system prompt is describing what the model should act like. So it's telling the model what it can expect, an input which will be masked like this, and then it's asked to evaluate the input in terms of how well it addresses the original task of explaining the key events and significance of the American Civil War. That is the idea I brought in here. Consider factors such as breadth and depth of context provided, coverage of major events, analysis of short-term and long-term impacts or consequences, and then it should check the output. If it is fully and satisfactorily covering these different aspects, then it should state the response is sufficient. Otherwise, it's returning basically a JSON with a rating, which is scoring the output in percentage, and it should also provide some revised output and some feedback, which is not shown here, but we will see in the coding. And then in the user prompt, we just pass in the text that is our starting point and which will be subsequently improved. And then if we run it the first time, the output might be looking like this. We have our JSON with the key of the rating, and then that might be just a rating of 20 and some revised output, and then not shown here, also some feedback on the provided output of the last round. Good. That is what we are going to see in the actual coding, which we are seeing now in VS Code. Hello and welcome to this lecture. Now we're going to take a look at another technique, which is called self-feedback. And you can find that in our working folder, Advanced Prompt Engineering, in the file self-feedback end. So we are directly jumping to the final code that I have created. And here I'm just showing you how I have implemented everything. So I'm just loading the packages that we need. That is identical to previous lectures. Then we also need to have our OpenAI client to interact with OpenAI. And then we need to define our function, because later on we are going to call this function. Let's maybe just jump to that point. So in the end, we are going to test everything with a certain user prompt. That is our starting prompt. And with this process of self-feedback, the model is creating some response. It's providing as well some feedback on the previous response and also some rating. And depending on the rating, there might be another solution created, and that one will be improved based on the feedback that was provided on the last result. Or if the target rating has been reached, then it's going to be stopped. So that's the whole idea, and it's not too complicated algorithm. And the idea is here to work on the American Civil War. And yeah, I'm not from America, so I don't know too much about it. And I provided this super simple and not very sophisticated answer. And we want to improve that over time. And the model should self-evaluate its own answer and improve it to get better and better based on its own ratings. Good. Let's see how this works. So we need to pass some user prompt, then also a maximum number of iterations for having some stop criteria, because otherwise it might just run forever. And we need to also define some target rating. This is also then used for getting some stop criteria. All right, then we could also, instead of hard coding the model, we could also pass it as a parameter. Here I just use GPT 3.5 Turbo, and we provide the system prompt. So in our mask, we are providing some input, and the model is asked to evaluate this input in terms of how well it is addressing the original task of explaining the key events and significance of the American Civil War. Then I'm also providing some information about factors to consider. And then I'm talking about how the return object should look like. So I want to get some JSON object, and I'm especially interested in certain keys. So the first one is the rating. Here I want to get a scoring in percentage. So it should evaluate its own previous answer and say this is 20% of a total of 100%, for example. Then the next key is the feedback. So here I'm asking the model to provide some detailed feedback on the previous output. And then we want to get some revised output, where the feedback is taken into account and it's asked to return some improved output, describing the key events and so on. And the last part is just for making my life easier because at the end I get back some string object and I need to convert it back to some JSON, and it's making my life easier if I avoid apostrophes in this output object and backslash and so on. So this is just for making the conversion later a bit simpler. And then we have some starting revised output. So assuming that the output or the response is sufficient and we don't have any feedback at the beginning. And now we are iterating. So we at maximum iterate over the maximum number of iterations. That is our second parameter here. We are defining our prompt. So the prompt is our user prompt if we are starting with the first iteration. Otherwise, we provide a prompt which is having the feedback included and the revised output included as well. And then, as usual, we define our messages, which we need to pass over to OpenAI. And we can then define our API call. So from our OpenAI client, we are calling chat completions create, passing our model and the messages. And then there's a certain way of extracting the response and especially the content, which we are then storing in this object, content. And now this caused me a bit headache to make it work and not breaking at several loops. So I need to convert this back into some valid JSON. At first, I need to load. I could remove this part because it's just the same object. That was necessary during some iterative process when I was improving this and removing some bugs. So now we have some JSON object, and this JSON object has different keys, as we have asked the model before to create a key for the rating, for the feedback, and for the revised output. And we are converting our rating to have some number to compare in the end. And we are taking all the other parameters and define here our revised output in the end. And the revised output is coming from this key. Then we want to see at each step how everything is working. So we print our current iteration, the rating and the feedback and the revised output. And then we can check if our rating has already exceeded our target rating. Then we can directly stop and we don't need to have further iterations. Otherwise, we move on at maximum as long as we don't exceed the maximum number of iterations. So this is our self-feedback. And now we can check that. We can start with a very not sophisticated user prompt and then call our function. So let's see if this works. Now we have our first iteration with a rating of 25, not too good. Now we already are at a rating of 75. And let's see, we are at 80. So we did not reach our target rating, but we reached the maximum number of iterations. And we get some revised output, which is considered to be much better than the starting output or the starting prompt that I have provided. And here we can see it. Alright, so I'm not going over this in detail, but it seems to be at least much longer than what we started with, and based on its own internal metrics, this is considered to be a much better answer than the previous ones which we had in previous steps. So the main thing here is basically the idea that we ask the model to provide feedback on its own creations, and that is a very cool idea, I have to say. So we have also seen that this is improving the result over time, and I like that approach very much, and I'm pretty sure I'm going to use it in my own projects. So give it a chance and try it out for your own projects. It could prove very helpful. And with that, we have reached the end of our lecture on self-feedback. Thanks a lot, and see you in the next lecture. Hello and welcome to this lecture. Now we are going to see another technique which is called self-critique. And the idea is here to follow different steps. We are having some ideation step, some critique step, and some resolution step. So in the ideation step, we define a number of different ideas or outputs. These are then passed to some critique step. So in this critique step, the LLM is analyzing these different ideas and providing some critique. And out of them, it's picking the most appropriate idea. And then it's taking this most appropriate idea and improving on it before it is providing some final output. So this is also based on some paper and a very interesting and promising idea. And in the next lecture, we are going to code that together. Thank you and see you there. Hello and welcome to this lecture. Now we are going to study another technique which is called self-critique. And the script you can find in our folder for advanced prompt engineering. And then we are working with this file for the self-critique end. And for that one, we are going to load certain packages. And there is one additional that we need to install before we can use it. So we have to open our terminal and run pip install in our environment. And what we need here is called LangChain experimental. So let's just run that so that our smart LLM chain is available. So as soon as that one is installed, we're able to load the packages. And then what we're going to do is we are going to ask, as in previous lectures, a comparably hard question to the model. So it's again some mathematical problem that is supposed to be simple for a human, but sometimes hard for a model, especially if it's trying to jump directly with zero shot to the answer. But here we are going to pass our hard question to our model. And since we are here interacting with LangChain, LangChain has a very nice interface. So with LangChain, we can just set up our prompt. So we just have to import our prompt template from LangChain prompts. And then we can pass in here our hard question. And then we can create an instance of our LLM. In that case, we are going to use OpenAI. So we are using this specific chat model and import that at the beginning. And then we can specify certain parameters like the temperature and the model name. And then we can call the method smart LLM chain. And in here, we have to pass the model, the prompt, the number of the ideas that the model is supposed to be creating. And we also want to see many outputs. So we also set the parameter verbose to true. And then we have our chain prepared. So let's just run that. We just run the cell to load all the different packages. And now we can prepare our chain. And once this is done, we can just call chain.run. And here you can see what is happening. So It is entering the smart LLM chain. It's creating different ideas. So here we can see the output for the first idea with the different subsequent steps. Then the second idea is created and we only see two. There is another one missing and hidden in between. So finally, we can see here the output. So the model has been evaluating the three different ideas and finding out that the best answer is idea 3. And it's taking this to create some improved answer. And then we can check it if it's really working. So actually it's not too complicated. Here we can see if 10 workers are working on the house, the number of days it would take to complete the house can be calculated by dividing the total work by the number of workers. So in the end we have 4 days. Good. And that's just a very simple way of setting up this approach of self-critique. So you can see we have just a few lines of code and we can directly use this available package for our purposes. And now you have seen also how to use that one. All right, and with that we have reached the end of this coding lecture on smart LLM chain or on this specific implementation of self-critique. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture on Retrieval-Augmented-Generation. Here I'm going to show you the workflow. So how does it work? In short, it's called RAG, and the main idea is the following. You have a large corpus of data, so a lot of different text documents, and you pass them into some embedding model. Basically, this is what we have done before. In a section before on vector databases, you have seen how all of this is working. You take all the texts, put them into some model, and you get some embedding. So here at the bottom in the orange cells, you have just plain text. And then this dark blue, this is each time a vector of a certain length with specific numbers, which are representing the context and the inner meaning of the text which is provided. All right, then you have a certain user query, so a certain text. User is asking a certain question. That one needs to be embedded as well. And you get, of course, the corresponding embedding. And then this is also included and embedded into the vector database. You have some nearest neighbor search. So then the embedded user query is passed to the nearest neighbor search, as well as all the other embeddings that we have. And then there are some clever algorithms at work which are able to very quickly find out which of these different documents and which of these different embeddings is closest to the one that is coming from the user query. So let's assume that we are looking just for the top 2 answers. Then these 2 embeddings would be selected, and then you have the corresponding text. You have then a bundle of the embedding and the corresponding text. So these are the 2 best representing answers to the user query. And then you just take the text of these 2 best answers and pass them to some large language model. Let's say you use OpenAI, ChatGPT, and then you pass the 2 best fitting answers as well as the original user query to some large language model, and you get back some response. And that's the whole idea of Retrieval-Augmented-Generation. So you don't get just the best results from the database, because that is in effect our vector database. All this bottom stack here, this is our complete vector database, and then taking the best results, passing them to some large language model. That is the part which is built on top of it, which is then called Retrieval-Augmented-Generation. And you will see how good this is performing. So you get some really nicely shaped answer based on your user query. And this is improving the user experience a lot over just taking the answers coming from the vector database. So you see, this is a fancy name for a not too complicated topic. And in the next lecture, we are going to see how this is working in some real implementation. Thanks a lot and see you there. Hello and welcome. Before we actually start with the coding, I think it's a good idea that I show you the end of everything so that you get a better understanding of where we are going to end up. So at the end, we are working against our movie database. So we are using the database that we have created earlier in our lecture on vector databases. And we are pulling some responses from the database. So we have a certain query, like for example, a cop is chasing a criminal, and we're looking for the 3 closest films corresponding to this query. And then if we print that, we can see here the movie title, colon, and then the description of the film, and then the next movie title with its description and another one. So this is what we are going to pass then to the large language model, and then we get a much nicer answer. So this is just, let's say, the raw result, but if we pass it to RAG, to the large language model, then we get a nicely shaped answer, which is really good readable, like the names of the movies and their plots, where a cop is chasing a criminal, are, and then they are named and nicely described. So this is a perfect answer. So this is the real power of Retrieval-Augmented-Generation. Taking the raw responses from the vector database and passing them to some LLM so that we get a nicely shaped answer. Perfect. And now you know where we are going to end up. And in the next lecture, we are going to start coding everything from the beginning so that we get to exactly this result. Thanks a lot and see you there. Hello and welcome to this coding lecture on Retrieval-Augmented-Generation. I'm working now in the folder 50 rec. The first thing that I've done is I have copied the DB folder from the vector database folder into our rec folder. Because I don't want to add all the movies again to the database, I can just work with the database that we have created before. If you have not done that before, please go back to the vector database lectures and create the database. And then I have copy pasted it into this folder rec, and now we can work against it. Okay, we are always starting with the packages. So we are going to need OS. Then also for nicely printing in the end, we use pprint. Of course, we need our vector database, ChromaDB. And now here we also need OpenAI. So from OpenAI, we are using this class OpenAI, and we need to specify the OpenAI API key. And it's good practice to not expose it in the script. Actually, you should never do that. Always keep your credentials separate from your coding. So here I'm just pulling the API key from the environment variables. And then I assign this here to this OpenAI property API key. That is necessary so that we can work with it. And then we are also working against our persistent client. This is why we have copied the folder DB into our working folder, and then we can work with this instance chroma_db, and that is all the preparation that we need. Then we can check all the different collections that we have here, just to make sure that we actually have the movies collection in here, and that's the case. You can see here there is just one collection in our database, which is our movies collection. Good. Now we need some instance and some reference to this collection. So we create this corresponding object with get or create collection pointing to our movies, and then we can work with this object. At that point we can also quickly check that everything is working. Chroma collection, query, and then here we have to pass in our query text. A monster in the closet. And let's say we want to have 5 results or 4, doesn't matter. It's just to check that everything is working, and this would be the corresponding response from our database. Good, so the database is up and running and we can connect to it and pull results out of it. We might also check again that the right number of films is referenced in there. So we can call chroma collection get IDs and then pass our length function around it. We have our close to 40,000 movies in here. Good. Now we can create our function for getting the query results. I'm just calling it right in that way, get query results, and we pass in some query text and a number of results. That one is to be 5 as a default. And then we can see here, we can just run our query in the same way as we have done it a few seconds before. We pass in our query text inside the list that's necessary from the format. And then we need to, of course, also pass our n results. Good. And then we can pull all the different docs from here, all the different titles from here. And the result should then be concatenated again into one resulting string where the different movie results with the title and the description are semicolon separated. So we are calling it like this, semicolon.join. And then we have here our title and the description. And we might check that. So let's work with the same result that we created before with the same query text. Then we can just pull our results with this function. And here is it what we're getting. We have then the name of the film, the description, all the way until some semicolon is coming up, and then the next film is coming and the next description. So this is the way how our results are returned, and this is our pre-work, because that is going to be the raw result which we are going to pass to the large language model in some later step. Okay, but for the rec we need to set up our system role. This is going to tell the algorithm how it's going to work. So here you can be a bit creative. I just came up with this prompt. So I'm just telling the model, you are an expert in movies. Users will ask you questions about movies. You will get a user question and relevant information. Relevant information is structured like movie, colon, title, movie plot, semicolon, and then much more. Please answer the question only using the information provided. So that's our definition of the system, so that the model gets a better understanding of what is expected from it. Then we need to specify the actual user query. So I formulated it like this. What are the names of the movies and their plot where? And then we fill in here the user query. Actually, it needs to be an F string. And it should be here, in this case, retrieved results. Good. Now we need to set up our messages. because we are going to pass the two different information to the large language model. So we are passing the system information with the system role definition and the user query, the user prompt. So system prompt, user prompt, and this is the setup, how it needs to be structured for OpenAI. For other models it might be different, but this example is based on OpenAI. So we are creating these messages in this way, and then the model is going to know how to deal with it. Now we can create some OpenAI client. So this is just an instance of OpenAI, and as a model we just take, for cost reasons, GPT 3.5 Turbo, because it's comparably cheap compared to GPT-4, and we can get the response by calling our object OpenAI client .chat.completions.create, and then this one is requiring the messages, the list of the chat completion message parameters, what we have set up before, and we also pass the model. It needs to know to use which model in this case. Let's run that. Okay, let's see what we have got. We have here our response, and if we just take a look at that one, it's a bit more complicated. It's having a lot of overhead in here. Actually, we need to dig deeper to get the right information out of it. So in here we have to use the choices, and the first choice, and then the message and the content. And this is then the string that we are looking for. This is the output that we want to use. So this is the nicely formulated answer. The names of the movies and their plots are as follows, and so on. So this is the nicely formatted response from OpenAI. That's looking really good. And now we can actually go forward and bundle everything together. So this is the way how we can build it up and develop it, and we have seen that everything is working. Now we can put it into a function which we call rec, and here we pass in a user query which is a string, and in here we get some retrieved results. This is the result coming from our vector database. So now we have our retrieved results, and now we need to define our system role definition, which is the same as we have set it up before. Then we need to define our user query, and that one is the combination of this text, what are the names of the movies and their plot, where, and then we pass in here the retrieved results. And now we need to set up our messages. It's basically just pulling the same information that we have defined before into the function. Then we create the instance of OpenAI. We define our model, and we pass everything to OpenAI to get some response, and we pull the real content that we are interested in from this response. Great, and that is the one that we are going to return. Very nice. Now we can just run that, so the function is available, and now we can create here our final results that you have seen before in the last video. So in here we can just pretty print our response from the vector database. That is looking like this. So that is the part which is passed to the large language model, And now if we take the final result coming from the large language model, we can just call rec and put in our query. So now we are waiting for the response from the rec. And here, this is the final answer. The movies and the plots are as follows. Then the first one, the second one, and so on. So this is looking quite nice. Great. So let's just recap what we have done. This video described how to set up a system called Retrieval-Augmented-Generation. We are at first setting up everything with regards to the vector database. We're using the vector database from an earlier lecture. So we use the persistent client and use our movies database. Then we create our function to get the raw responses from the vector database. And that result is then used alongside some system role definition to pass to the large language model. And then the model is answering the question, what are the names of the movies and their plot, including the information from the vector database. The rest is just to follow the structure that is expected from the model. So it needs to be set up in this way that we define the different roles for the system prompt and the user prompt. And then once we have done this pre-work, we can create an instance of OpenAI, define the model which we're going to use, and we can then get a response from the model by calling GPT 3.5 in that way, by passing the model alongside the messages. And at that point we were already done. The rest is just making it nicer so that it's reusable and everything is nicely structured inside this function. So all the pieces that we have defined up to this point were just taken, bundled into this function so that we in the end can just call it in this way. We can just call rec with the query and get the corresponding results. Great. And that concludes our section on retrieval-augmented generation. I think by now you see the potential which this specific technique is having. So I'm expecting that this is really having a large impact on many companies. This is super powerful and extremely helpful in many instances. So this is a technique that you will need a lot, I would guess, and it's really fun to work with. But for now, I want to thank you that you followed me along up to this point, and I hope you have learned a lot. And we are finishing now this section, and I will see you in the next one. Thanks a lot, and see you there. Hello and welcome to this new section. In this section we are combining knowledge which we have gained before in different lectures. So in this section we are going to make use of vector databases, we are going to make use of rec, and you will also learn something new, which is how to create some web app based on Streamlit. So as a teaser, I show you here what we are going to develop. We are going to develop a web application which is working on a dataset on climate change, and it's a chatbot. So it's asking you, what do you want to know about climate change? And then you might ask specific questions. And then once you press enter, the model is running and it's returning the raw responses. Then you can see here the text snippets coming from our vector database. These are the ones which are then taken alongside the question which we have raised here and passed on to the large language model. And the large language model is taking this raw information together with the question and creating a nice response on it, which is really providing a really good formulated answer with the right content. Great. This is what we're going to develop. So we're working against a large PDF document. We're able to pass it into our vector database, pull the data out of that, and providing some really nice answer. That is a feature that you might use a lot because it's extremely powerful and super relevant in many different companies. So I hope you are excited about what we're going to develop now, and we are starting to code in the next video. Thank you and see you there. Hello and welcome to this coding lecture. Now we are going to develop at first our Retrieval-Augmented-Generation, and afterwards we are taking the result from here and put them into some web application. So let's please move to the subfolder 60 capstone IPCC, and from here the file 20 rec start, because that is the one which we are going to fill out right now. And the data that we are working against is stored under data. It's the file IPCC, AR, and so on. So this is the technical summary of the IPCC report. It's a PDF document with 84 different pages, and you're going to learn how we can import all the texts from this PDF document and put that into some vector database. And finally, how we can make use of rec against this document. Good. Now let's get started. So we are going to use OS and regular expressions and pprint. We have seen all of them before. Then we are going to make use of PyPDF, because that package is very helpful if you're working with PDF documents, and it's holding a class called PDF Reader. So that is the one which we're going to use to import all the text from the PDF document. And then again, we are going to use the recursive character text splitter from LangChain. The vector database is ChromaDB. And later for rec, we are going to use OpenAI. And we are setting up our API key so that we can directly use OpenAI. Let's run that. And we are starting with the text extraction. At first, we need to pass the reference to our IPCC report. It's stored in the subfolder data, IPCC. And then we can create an instance of our reader. So we call PDF reader and pass in our PDF file reference. And then we can take a look at the IPCC report text. IPCC texts. And we are going to use the reader. And from here, we iterate over all the different pages. And for each page, we are calling the extract text method. So let's try that. Let's see. We are in the wrong working folder, so I just close it, run it again. That's the quickest way to solve that, because we need to be in the subfolder 60, capstone IPCC. And now we try it again. Okay, let's see what's going on. It's a different file name. Let's copy this and pass it in here. All right, now we should have the right reference, and it seems to work. Good. As soon as we have that, we can take a look at the IPCC texts to see if the import has worked out correctly. Good, everything was imported. And if we take a look at the IPCC text, it's a long list. So it's basically taking all the different pages which are in here, and each page is referenced with the string corresponding to it. So there's a certain demand for post-processing, because then here you can see the page numbers, which we don't want to have. We have the TS for technical summary, often part of it, and then the technical summary here as well. So a bit of post-processing is needed. Okay, one page would look like this. And now we need to filter certain pages. The first part I'm doing here is that I'm filtering out the beginning and the end of the document. And I will call the resulting document IPCC without header footer. So we need to filter out the first pages. Let's see. So this is already having some content. If we are still on page 4, this is still some introduction page. So that one is still to be disregarded. And then if we take a look at the end we also have some pages which we don't need. You might also open the PDF document to find out the right pages. So that one is also not relevant. Here, this seems to still be some content page. All right, so if we want to filter everything, we can create a new object, IPCC texts filled. And we are taking our list of strings and leave out certain strings at the beginning and at the end. So that's our filtered version. And now we can remove all the header and footer texts. Because as we have seen before, there are certain texts always referencing to the page number, TS or technical summary. So there is a certain need for removing all of this stuff. So we need to remove all the headers and footers. We can create a new object. So at first we look for all occurrences of technical summary, like this one, and we're going to remove it. So we iterate over all the different strings, and then each time we just remove that. So that is for the header and the footer. So that is remove technical summary. Oh yeah, and the number before it. So in this regular expression, I have here this D+. So that is corresponding to the number which is in front of technical summary. Good, so we have removed that one. Then the next part is that we are removing the TS. So on certain pages, we still have then TS referencing to the technical summary. We are also going to remove that one. So it's as simple as that. We use regular expressions, substitute, and we are looking for \n for this line break, TS. So that would be these occurrences here, \n TS, and remove it with nothing. So that is that one. And then there is also the opposite, TS \n. So we can also remove that one. And with that, let's see if we have nicely shaped our documents. Yeah, now it's much better readable. There might be more steps which you can apply, but this is already helping us to get rid of a lot of unnecessary content and using it in the best possible way. Now we can split our text. We are going again to create our recursive character text splitter with certain separators. So we have \n, \n, or just a line break, or just a dot for finishing a sentence. Or if that's not the case, then we can use a space or nothing. So that is then for splitting all the texts. Oh yeah, this is just the separators. We also need more parameters. We also need the chunk size. I set it to 1000, and I'm also allowing certain overlap. Chunk overlap 0.2. So in the end, we are going to use our sentence transformer token text splitter. And if you go to Hugging Face, to the model card, you will see that this model is allowing 256 different words in a sentence. Everything else would be truncated. And then, since in the English language 4 tokens are considered to be a word, this is roughly aligned with this chunk size, because 256 words times 4 characters would end up with 1000. So that is then just making sure that we get into the same ballpark which we need for the sentence transformer. And now we can split all our texts. Let's call it text character split. And we call here our character splitter. And in here we can just put our IPCC without header footer. And then we can check out the length of this object. Text character split. Oh yeah, it's not called split, it's called split text. Yes, of course, this also cannot work because this one is a list, as you will see, and needs to be concatenated all together to be a string. So how do we do that? We can create a string. Let's say we are taking this double line break, \n, and call here the join function. So based on that one, we are joining all of these individual lines and putting them all together into just one string. All right, and that would end up with 461 different chunks. Good. Now we can move on and we can split all the tokens. So we are going to set up our token splitter. And this is from our sentence transformers token text splitter. And here we can also set up our chunk overlap and our tokens per chunk. 256. Now we set up a list for all our text tokens splitted. That one is empty at the beginning. And then we iterate over all the text in text character split. The one which we just took a look at. So we iterate over that one. And for each text, we split the text based on the token splitter and append it to our object text token splitted. Let's run that. Alright, it needs to load some files and some models before it can move on. I actually saw that there is a mistake. The model name shouldn't be the paraphrase mini LLM, it should be the default value. So I'm just removing that and rerun it again. And we see that for certain texts it's having some problems trying to split the texts. So we need to put that into some try-catch phrase. Actually, it's try except in Python. And then we are going to take a look at the text, which was not possible to be splitted. And only the beginning. Okay, let's try that again. Yeah. Okay, it might be a bit additional work to try to find out why certain strings were not successfully splitted. I leave that up to you for now. Here I'm just moving on, and since we still have more than enough text to be added to our database, that's totally fine. So, but if you want to have a better understanding on what was completely done in here, yeah, you can check that out, why something is not working. For now, I'll just leave that, and we will just move on with the 364 different chunks which we have here. And if we take a look at the first chunk, token split it at position 0, then you can see, all right, there is still a bit to improve. So we might iterate and start over at the beginning and remove that one, but the rest is looking just fine. It's having the right text in here, and that one is working. Good. Now we can create our reference to our vector database. So we are going to create our ChromaDB reference, which is coming from ChromaDB, and we will actually make it persistent now, persistent client, and the path is going to be db in the subfolder. I've done that before. I will just delete it for now so that we do that together. So now we run that, and a subfolder db is going to be created, and we can also create the reference to our Chroma collection. And I like the save approach more. I like this get or create collection. And the name is a bit long. Let's just call it IPCC. Good, this is going to be our Chroma collection. Let's see. That is running. The subfolder db was created. Good. And we can start to prepare all the documents which we want to add to the database. So the first one is that we need to have some IDs. And the IDs need to be unique. So we are going to create again some list comprehension, and we will fill out the beginning at the end for I in range length of text token splitted. So we iterate over all the different strings inside our list, and we will just get the string out of it. This is not totally safe. It might be that certain strings are completely the same. It's not the case in our example, but you might also use some more safe approach like UUID for creating the IDs. For now, I will just work with this approach. And if we try to add our documents, we just have to pass in our IDs, which we have done now, and our documents. And the documents are coming from the text token splitted. Good, that's it. Let's just run that. Yep, again, some wrong function here. It's called just add. And now all the embeddings are created and everything is stored in the database. We can already hope that this is working and move on to create a query. So let's create a query. What is the impact of climate change on the ocean? I don't know, some specific question that you might ask yourself. And then we can run our query. So we pass in our query into the query function, and we also can specify some parameter like n results. We want to only have the 5 most important results. Yeah, we need to pass in here our query texts as a list. And then we get the right queries back. So then we can see here the distances and the documents. Good. So these are now pieces out of the complete document, and possibly it's hard to find the real content out of it. So in cases like this, RAG is the perfect approach. So we can set up now our RAG system, and we will define everything in a function. I will just call it RAG, in which we pass in a query. And the number of results is also a parameter. Let's go with a default of 5. And at first we need to get our responses from the vector database. So it's working exactly like we have done it before. So this is more or less copy pasting from what we had here. And then we have our documents to be created. And then, since there might be multiple elements in this query, we only use the first one, so position 0. This is now corresponding to our documents. And now we need to join everything. So let's call it joined information. And we are semicolon separating everything and joining. And we are joining it semicolon separated. So this should be our joint information. So everything is now in one string. And now we need to set up the messages which we are going to pass to OpenAI. So at first we define our system prompt. Then the content here is as follows. So I provided here the text. Your users are asking questions about information contained in attached information. Good. That should be our system prompt. And actually we make it a bit more explicit. We're telling the system here, additionally, you will be shown the user's question and the relevant information. Answer the user's question using only this information. Good, that's our system prompt. And now we're going to add our user role. Role user. And the content is going to be an F string starting with a question, and the question is our query, and then we pass in our information as well, and that is coming from our joined information, and then we are asking for the answer. So that's one possibility of setting it up. That would be then our messages. And now we can create an instance of OpenAI. I call it OpenAI client. And then we can ask for some LLM response. And that's coming from OpenAI client.chat completions create. And in here we need to specify a model. And the model is GPT 3.5 Turbo. And the messages are passed as well. Good. Then we have our LLM response, and we can extract the actual content from it, and that is stored in the key choices, position 0, message, and content. And then we are going to return this content. So let's see if all of this is working. Now we have set up our rec function, and now we can test it. So we can define a query and call rec with our query and use the default of 5 results which we are passing. Good, let's see if this works. All right, there is an issue. I think I made a mistake here. We have choices 0.message.content. Let's try it again. All right, again, it's not perfect yet. It's dot choices at position 0 dot message dot content. Okay, next try. Okay, perfect. Here we are. This would be our response from the rec system. The impact of climate change on the ocean includes significant alterations to aquatic food and so on. So this looks like a really good answer to our question. So this seems to be our final result of our rec system. Perfect. And let's just recap what we have done. We have imported successfully a large PDF document. We have extracted all the relevant texts from here. We pre-processed it a bit. We deleted some first pages and last pages. Then we removed certain numbers and certain specific texts from the document, which were repetitive and not necessary to have. And then once we were satisfied with all the different text chunks, we added them to some ChromaDB, to some vector database, and we ran some query against that one, and we set up a Retrieval-Augmented-Generation system, which is pulling the data from the vector database and passing it alongside some user query to an LLM, especially GPT 3.5 Turbo, and we extracted successfully the result from it. Good. And now in the next lecture, you will see how we can take all of that and create a nice web application around it. For now, let me thank you and see you in the next lecture. Hello and welcome to this coding lecture. Now we are going to develop some nice web application around our rec system that we have. For this, please open up the file 30 app start from the Capstone IPCC folder. And we are going to import the same packages that we had before. We also make use of our Chroma client, which is pointing to our persistent client with the path db. And then the Chroma collection is directly making use of the collection IPCC, which we have created before. So we can run both of these cells already. And then the rec system, that's the one that we have set up before in our lecture. Actually, there is a slight difference. We are returning not just the content now, we are also returning the documents itself. This is just for showcasing in our simple web application what the raw information was, so we need that one as well. Good. And now we can actually start creating our first web application. And that is actually super simple. So you will see that it's really not too complicated. It's making use of Streamlit. And I have to say, I have taken a look and investigated several web application platforms for Python, and that is by far the simplest one. If you are a more advanced user, you might run into certain walls at some point, and it's hard to overcome them. But for a quick POC, I really like to use Streamlit. It's super simple, and you can set it up in minutes. And you will see that right now. So if we check it out here, you just have to install it once, and then you can just run it. So let's do that. So we have now our app here, 30 start app, and we need to import Streamlit. We did that already. That was one difference to before. We have imported it as this alias, st. So now we can make use of different Streamlit methods, directly calling st dot, and here we create a header and call it climate change chatbot. Good. Let's just take a look at the terminal and we can run it. So it should already work. Okay, that would be our chatbot. Actually, one cool thing in VS Code is that we can directly take a look at some browser inside VS Code. That's what I mean. Okay. Now I want to see that here. We can make that one smaller, and that looks good. Now we can move on. So the first part is that we want to have some user input field. And the user input field we can easily create by calling text input. And it should have no label, but some helper text. That is the one that is shown inside the cell. All right, ask any question about climate change. Actually, this is the placeholder text. So what do you want to know about climate change? That is the part which is shown inside the cell. And here is the helper function. So these are just the text inputs, but we want to fetch that. So now we could just write something in here, but we are not able to fetch it. So this is very simple. In Streamlit, you can just store it to some variable and we call it user query. So whenever we are now having some text inputted and press enter, then we are able to get this user query, and then we can already call our rec system. Now we get two responses. Let's just call it raw docs user query. Good. So we would take our text that the user is entering here and passing it to our rec function. And then as a result, we get the response from the system and the raw documents, because both we want to show now on the screen. So now we create another header. Let's say raw information. And then we can pass in our raw information, raw response 0, and that's raw docs at position 0. So let's see how many do we get back. We have 5 results, so let's just copy paste that 4 times. So raw response 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Since it's just 5, I do it with copy pasting. If it would be more, I would think about something more clever, but here for now it's enough. And then we can create the next header and provide our rec response. And here we want to write some output. And that is directly our rec response. Good. Let's just save that. And we can also say here, since the system has recognized the source file has changed, we can call rerun or just say always rerun. So that means every time that the file is saved, the model is rerun and we are getting something back. Okay, good. There's one small thing. It's trying to call the rec system even if no question was raised. We can work on that in a second. But for now, we can just check it. What is RCP? Once we run that, you can see here the model is running. It's getting some responses directly at the top here. And then it's answering here. It's taking all the 5 answers from here, passing them alongside the question to OpenAI, and then we get this nice answer, which is also correct. Great. And you have seen in less than 10 minutes you have learned how to set up Streamlit and create a small web application. So it's really that super simple to work with that. And now we can make a few more small modifications. Let's say I'm a bit annoyed that it's directly calling the rec system even if no user question was raised. So that is something that I want to change. All right, I solved it in the following way. I override the raw docs. So I'm checking afterwards if the length of the user query is 0. So if there was no information passed, then I reset all the strings to an empty string, and I do the same for the rec response. So if the length of the user query is 0, then I set it to this empty string. Otherwise, I keep the rec response. So once we start, the app is looking like this. It's empty. And then if we ask any question, we see the model is running and we get the raw responses as well as a nicely structured answer from the system. Great. And that's it. That is our interaction with the document. So you see how simple it is. It took us just 10 minutes to set up a web application which is able to chat to this document, which we have set up into our vector database before. Then we have used our rec function, and the web application is just a few lines of code. So it's done sequentially, step by step. You have the alias st, and then you can write some static output like headers or titles. But then you also can fetch information from the user, like with this text input field. So we have used this text input, stored the input in the variable user query, and then we used that one to call rec. We store the results in rec response and raw docs, and we put everything on the screen. And that's amazing, I think. So this is really a nice little application, and it's making the information retrieval out of a document much, much simpler. And with this, we have reached the end of our lecture on our web application. This concludes our capstone project. Thanks a lot, and see you in the next section. Hello and welcome to this new section. Now we are going to cover a very interesting topic, which is called open source LLMs, because they're not just the big companies that are active in this field, and there's more than just OpenAI and Google. So you can actually use open source large language models and run them even locally. You will see in this section how this works. So I'm going to cover these two different models. One is coming from Meta, and it's called Llama 2. And the other one I'm going to show you is Mistral from Mistral AI. So Llama 2 is a model which is provided in different sizes. So the smallest one has a size of 7 billion parameters and the largest one has 70 billion parameters. It's mainly handling English texts, and it can cover roughly 2000 tokens. Whereas Mistral is provided also in different sizes. There is a 7 billion parameters option, and there is also another model which is using 8 times 7 billion parameters. This is actually called a mixture of experts model. So there is in total, you can say 45 billion parameters, but with these different experts, it's never used more than 12 billion parameters. And this idea of having a mixture of experts has shown out to be really powerful and providing very good results by keeping a small model size. In contrast to Llama 2, it can handle some other languages as well. So it was also trained on French, Italian, German, or Spanish texts. And the token limit is at 32,000 tokens. Then here you can see some parameters, some comparisons between Llama 2, GPT 3.5 and Mistral with this mixture of experts model. And you can see that these slides are actually coming from Mistral. So the focus here is on this comparison between Mistral and Llama 2. And it shows that the small model 7B and especially the 8 times 7B model, the mixture of experts, is outperforming Llama 2, and both are providing really good results. In the table here you can see the comparison of Llama 2, GPT 3.5 and Mistral for different benchmarks, and depending on which benchmark you are choosing, one or the other is outperforming, but still they are all playing in the same ballpark. So actually the Mistral model is providing really good results. Let's take a look at some advantages and disadvantages of open source versus closed source LLMs. And this is a bit of my personal touch, so you might disagree on one or the other results here. So in terms of confidentiality, there's definitely a plus on the open source LLM, because your company is not sending any data to some closed model outside of the company network, so you can keep everything contained. The model can run locally on some on-premise system in your company. There's no risk involved in that one. If the company is very concerned about confidentiality, then that might be a plus point for the open source LLMs. Also in terms of transparency, the open source LLMs are much more open about the training data, how they're training the models. Everything is much more visible to the end user what is going on here. Also, you have complete control about the large language model which you might be running. On the cost side, it's difficult because with closed source LLMs, let's say with GPT, you don't have any fixed cost. You don't have to have a very powerful machine with a lot of GPU power, nothing of that. But you definitely have some more variable cost because you're paying per token. Whereas with the open source LLMs, there is much more fixed cost involved because you have to have all this upfront investment and then still you need to pay for the operation of the machine. So it's kind of debatable which one is more preferable. In terms of performance, if you compare it especially to the most recent version, which is at the time of this creation of the video, GPT-4, the open source versions are not as good as GPT-4. But still, for the majority of cases, they are at least sufficient to be used. Then also in terms of maintenance, I mean, if you're working with some closed source LLM, you don't need to maintain anything. You just have to use the API that is provided and send the data over and you get back the result. Whereas with the open source LLM, you have to maintain the system, you have to keep it updated in terms of security and everything. So there is a lot more maintenance involved, and the same holds for the operation. So if you want to operate it, there are some operational costs and efforts included. So there is also the plus on the closed source LLM. Depending on your use case, it might be that open source LLMs are the right way to go for you. Let's take a look at some issues when you want to use them. Because I was also having that issue when I tried first to work with Llama. Because then if you create some system prompt and some user prompt, and the system prompt is really simple, I'm just providing here information about 3 different persons living in 3 different cities. And then the user prompt is just asking where one of these 3 different persons living. Then the answer is completely rubbish. You cannot use it. And the question is, what is going on here? So why does it not understand my question? And before we come to that, I will speak about ChatGPT and why it's not needed there. Because if you use the interface, especially just the web interface from OpenAI, you just have the text input, you press the send button and you get back some nice result. But under the hood, it's also providing the information in a certain way. So you need to provide the messages in this way that you pass the role, the user role, or possibly additional the system prompt. And that needs to be provided exactly in this way. Otherwise, ChatGPT would also not be able to provide a good result. So the problem is that with Llama 2 or with Mistral, at least a while ago, it was very difficult to find this information. How to provide the messages in the right way so that the models are providing valuable results. So you should not assume that the model is figuring out the system and user prompt correctly and completely on its own. So for Llama 2, you need to pass the data in exactly that way. So here I set it up with an f-string notation, and then you have this strange format here, which is passing in the instructions and the system prompt, and then you need to have the \n and then the user prompt, and then you need to have this closing XML tag. So it's really not working if you don't have it in this specific way. And the same holds for Mistral. So for Mistral, it's slightly different. You also have this inst XML tag, which you need to use, and then you can pass in the user prompt. And that's all. As soon as you do that with the correct use, so here we now have the system prompt and the user prompt, and we pass it into some llama prompt, then we finally get back the right answer. Perfect. Much better. Very well. And in the next lectures, we are going to see how we can set up some open source LLM. Especially I'm going to show it for Llama 2 on your local system, even if you just have a CPU, which is also the case for me. My GPU is not large enough to cover Llama 2. So even if you just run it on a CPU, it's working. And we're going to see that in the next upcoming lecture. Thanks a lot and see you there. Hello and welcome to this coding lecture on open source LLMs. You can see here the model page for Llama 2 7B, and there is one specific one which is already prepared so that you can directly run it on your CPU. So this is the one that we are going to use. You can check out everything about the model, and we're going to use then this Llama CPP. If we go to files and versions, then you can find here different model versions. So the size is corresponding to the performance. Actually, the best trade-off I've read out of these different models between size and performance is this KM. So this is the one that I have downloaded, and I have downloaded into the subfolder models. So we are working now in the folder 80, open source LLM, and then in here in the models, I have this file, Llama 2 7B chat gguf file. So that needs to be at this place. And as soon as we have that, it's also described here in the script, save it in the subfolder models and the link to the file. So we are going to see in this lecture how we can make use of this model, how we can run it for inference. But before we go there, we need to import some packages. Basically, we need to have this callback manager, this streaming standard out callback handler, and then of course we need Llama CPP. There are also other ways of using it, just that you see that. This is just one way of doing it. If you take a look at the model card, you can see that there are also other projects. I heard about at least this LLM Studios, which is supposed to be quite good, but there are also many other ways of how to use that. So I'm just showing you one way of running it locally. So let's just start from scratch, run the script, importing all the packages. All right, we have already downloaded it, and we can now run these lines. These are just preparation work. It needs to be set up in exactly this way, and we can create this instance of Llama CPP where we are passing in the model path. Similar to OpenAI, we can specify here a parameter for the temperature. So how much creativity should the model apply? Do we want to limit the number of tokens? How many results do we want to get back? And we need to specify the callback manager from before. And we also need to set some parameter for verbosity. So let's run that. This is going to take a few seconds. In the meantime, we can take a look at the system prompt and the user prompt. It's just a super simple example. So we provide some information. So we don't want the model to provide anything from its own internal storage, so to say. We want to provide some information about 3 different persons living in 3 different cities. And we are asking then the model, where does one of these persons live? And the right answer should then be Hamburg. So it's that simple. And now we can take a look at the naive approach. So assuming that we don't know about how to pass the data correctly to the model. So let's just create our prompt, naive, and that would be just our f string where we are putting in our system prompt and our user prompt. And now if we run it, if we call our LLM object, so we're passing this prompt into our model, and you can see the results are flying in. It's just recapping the information provided in the system prompt, but it doesn't really provide an answer, so that doesn't work correctly. So there is a certain way how we can pass the information correctly to the model. And for that we can just jump back to the model page, and if you scroll down, here we are. So here is the prompt template for this Llama 2 model, and it should look like this. So this is required to be passed in exactly this way so that the model is providing the right results. So let's do it correct. Let's call it Llama prompt. And in here we can pass this prompt, which needs to be exactly like this, with the instruction XML tag, with the system prompt \n. Then we pull in our system prompt, then we close the system prompt and pass our user prompt and close the instructions. That looks good. And now if we pass it with this Llama prompt to the model, then we are going to see that it's providing the right answer. Awesome. Based on the information provided, Eve lives in Hamburg. That's amazing. And that's it. So this is what I wanted to show you in this very short lecture. For now, you can see here what we have done. We have just imported some packages, and we're working with this package Llama CPP, which is some interface to using Llama. So we are passing in the path to the model, some additional parameters so that we have this instance, and then we can, once we have created the prompt in the right way, which is looking exactly like this, then we can call the model and get the right result. So this looks really good, and now you know how you can run some large language model locally on your system. And that's it for this lecture. Thank you very much, and see you in the next one. Hello and welcome to this lecture on data augmentation. So when do we need data augmentation? Well, if you want to fine-tune a model and you don't have enough data, then you need to extend the data source that you have and either look for more data, or you use the data that you have and you adapt it in a certain way. So to say, you augment it, and then it's assumed to be working as if you have more data from the beginning. So there is a certain analogy to computer vision, where you often have the same problem. You might have just not enough images to train a model correctly, but then you take the small number of images that you have and you adapt it in certain ways. So there are certain ways on how to pre-process images so that the model is actually using the same images but still getting a better learning out of it. So you can take one image and apply certain modifications, like for example converting it to grayscale. You can rotate it, flip it, you can crop it and zoom into certain areas. So all of that might be in the end helping the model to learn more out of a small number of images. And the same holds for texts. But there is a certain problem. Because in NLP, when you have some original sentence, like for example here, the sentence is "I saw a man with the telescope," then if you change it with the telescope, "I saw a man," it's having the same words, but the meaning is completely changed. So it's not that simple to adapt a sentence. So it's much more simple in computer vision to adapt the images, but with NLP you have to be very careful with the augmentations. But there are certain approaches that you can use, and some of them I want to provide to you here. So one of them is back translation. Another one is random insertion. Then you also have contextual word embeddings. You might also replace words with synonyms, or you might delete randomly some words out of a text. And then there is another technique called contrastive learning. And we're going to take a look at all of them in the next videos. Hello and welcome. In this example, I want to show you the idea of back translation. So for example, you start out with an English sentence. The pen is mightier than the sword. Then you translate it, for example, into German, and then you translate it back. The pen is stronger than the sword. So it might be that certain words are exchanged due to the back and forth between different languages. And then you have another sentence, which is still having the same meaning as the one before, but with this intermediate other language, which we used for the translation, you come up with a larger text corpus. Another approach might be to replace it with synonyms. So we have some source sentence, which is now the quick brown fox jumps over the lazy dog. And if you apply some augmentation model and you replace certain words with synonyms, then you end up with a similar sentence where certain words were just replaced. And then it reads completely different, but the context is still the same. So that would be the replacement with synonyms. Another idea would be random deletion. So we have our source sentence, the pen is mightier than the sword, and then randomly some words are deleted. So that is a different technique that also might help the model. Another one is called word embedding augmentation. And that one you might use certain embedding models, like for example the ones we have seen before, like Claude, or some other ones like word2vec, fast-tag, BERT. And then you would choose a nearest neighbor. So for example, if your word is fly and you look for words which are very close to fly, then it might be hover or wing or float or glide. And then you would use any of these, or maybe just the closest neighbor to fly and use instead of fly. So these are just some of the different ideas that you might use for augmenting your data source to come up with a good text corpus for training a model. Here I summarized for you some other articles which partially were used for this video and which are really good to read. And then also there are some packages that you might use in this regard. So these are some further reads to dive deeper into the topic. And in the next video, I'm going to show you how we can code this together. Thank you and see you there. Hello and welcome to this coding lecture. Now we are going to use our first technique, which is called back translation. And you can find the script in our folder on data augmentation. And it's based on a model provided by Facebook. And you can see the model card here. So it's called M2M100. It's a multilingual encoder-decoder. So we can use it for translating a text into a different language and then translating it back afterwards. So that's the idea of back translation. And it shows this specific model because it's covering a lot of different languages, as you can see here. And also the way how to use it is perfectly described in these code snippets here. We are not going to code that completely because there is not much learning in here. It's very specific to this specific model on how to use it. So we are just going through it and you can just follow me along when you open this script. First of all, we need to install another package, sentence piece. So it should be installed right away for you if you have created the environment at the beginning of the course. If not, this is an important package to make this work. And now we're going to load the specific classes here from transformers. We're using this M2M100 for conditional generation and the corresponding tokenizer. And then first of all, we need to create references to the model that we're going to use and to the tokenizer. So we're going to use this specific class, and from pre-trained, we use then this model, and we use the corresponding tokenizer, of course. So this is the first part. It's taking a bit longer if you have not downloaded these models before. But alongside that, we can already start taking a look at the next pieces. We're going to use some original sentence, the one from the slide set, the pen is mightier than the sword. And then we create our tokenized version. So I'm calling this object then original encoded. Then we are going to create our tokens by passing it to the model. And we have to follow along these exact definitions that we have here. And then we have here our target. So this is the translated version into German, because then I can check it. So the model is running now. Der Pen ist stärker als das Schwert. Alright, pen was not correctly translated, but that's not an issue for us right now. There would be a different word for that. Anyhow, the rest is working quite nicely. And now we need to create from the target language, which was German, the back translation. So again, we take our target encoding, and for that one the tokenizer. We pass in our translated sentence. We have to specify here that the return tensors are PyTorch, as we had it before. And we also specify some parameter padding true. And then we create our tokens and check out the result. All right, and here in this line, I did not store it in a variable. We can see the result. The pen is stronger than the sword. So our starting point was the pen is mightier than the sword. And now with the back translation, we were able to translate it into stronger. So that's the power of starting with a language, translating it into some target language, and going back to the original language. Good. And with this specific model, you have all the options. You can use many other target languages to check out the result. And this is our first algorithm which we have learned on how to perform data augmentation with NLP. Thank you very much. And in the next video, we are going to see how we can replace text pieces with synonyms. Thanks a lot and see you there. Hello and welcome to this coding lecture. Now we're going to replace with synonyms, and we are using a new package for that one. And the package is called NLP-Org. You can see here the GitHub repo. And if we scroll down a bit, you can find out about many of the different options which we have for augmentation of our data. And we are starting with this synonym approach at the beginning. So in our file, replace with synonyms, we just need to import the package. And we are using this alias NAW for NLP-Org Augmenta Word. And now we use the sentence, the quick brown fox jumps over the lazy dog. Then we have to create some instance of the synonym augmentation. And we need to specify some augmentation source, which is a specific model. And here we use WordNet. Then we are going to use the augment method from this object org, where we are just passing in the text that we want to get augmented, and the rest is just printing out the results. So it's really that simple. We are just running it through the model. And instead of the quick brown fox jumps over the lazy dog, it's saying the prompt brown dodger jumps over the odious dog. Well, you can argue about the quality of that one, but that's the idea of replacement with synonyms. Thank you very much, and see you in the next lecture. Hello and welcome to this coding lecture. Now we're going to use another technique, which is called random cropping. Again, as in the last one, we're going to use NLP-Aug, and we are importing it with this alias. Then the text is the quick brown fox jumps over the lazy dog, and we are creating our instance of random word aug, and here the action is now crop. Then all we have to do is we have to call the method augment, pass in our text, and we get back our augmented text. So let's see how this works. That is super fast, and you can see that it's actually not doing anything fancy. It's just cropping out certain words. So it's removing the word the, brown, and jumps. Okay, it's just randomly picking out words which are left out on purpose. And this is supposed to still help the algorithm to get some better understanding of the text. Good. That's the idea of random cropping. Thanks a lot, and see you in the next lecture. Hello and welcome to this coding lecture. Now we're going to take a look at another augmentation technique, which is called contextual augmentation. And if you think back to the theory lecture, you have seen that we are now going to use some NLP model, and in that case we are using BirdBase uncased. And we are trying to find words which are contextually very close to the word which we are studying right now. So all we have to do here is we need to import the package, then we have to specify the right model, and then we can create again some instance which we call augmentation, and now we are calling the method contextual word emps-aug. That one is requiring the model path, then the action, which is substitute in our case, and we can run it on CUDA if available, otherwise just go with your CPU. The text is the pen is mightier than the sword, and then we just have to pass it into the augment method from this object augmentation. Since now we are using some rather large model, this is much more computationally effortful than the last techniques. And then we can take a look at the result. So the result is saying the tone is mightier than the typical pencil. Sounds funny, but that is what the algorithm has provided. All right, if we run it again, you can see there is a bit of randomness involved. So it's every time providing slightly different results. But yeah, that one looks a bit better than before. So the main idea is that now you have some code pieces which are showing you how you could implement contextual augmentation. And that's it for this lecture. Thank you very much, and see you in the next one. Hello and welcome to this coding lecture. We are going to study the next technique from our data augmentation. And now we are going to take a look at word embeddings. So it's starting as before. We use our NLP augmentation for words and import that with the corresponding alias. And now we're going to call the method words emps-aug. And in here we use the model GLAV, the one that we have seen before at the very beginning in the introduction into NLP. And we also need to pass the path to the model. So it's this specific txt file. And we're going to use the action substitute. All right, and then we just can define our original text and pass it into the augment function, and we get the corresponding result. Actually, since I spoke about the model path, You need to, of course, have this file, the specific model, inside the folder. So you need to download that because it's too large to be hosted on GitHub. I don't want to spam my repo with that one. So you can just head over to this page. So to the GLAV page from Stanford NLP. They actually put the large models up here, and you can find here the GLAV 6B in different sizes. Or you head over to Kaggle. I also found it here. So there you can also find the 6B 100D model to be downloaded. So there are different places where you can fetch it from. And then once you have downloaded it, you can place it in your folder and you can use it. So now we can run it. GLAV 6B 100D. Let's see what's going wrong here. Maybe I'm in the wrong working folder. Yeah, I'm still working in the wrong working folder. Let's just rerun everything so that it started in the right folder. And in a second, the model should be available. And then we are going to call the augment method on it. All right, and here we are. So now it used the word embeddings from GLAV to find close words. So now it's saying the Mont Blanc is blender than day sword. All right, so let's run it again. Okay, I'm not sure if I'm so happy about this approach, but yeah, this is another technique that you might use to augment your data. All right, and in the next video, we are going to use another technique to augment the data. Thanks a lot and see you there. Hello and welcome to this coding lecture. Now we're going to use another technique from the area of data augmentation, which is called fill mask. And you can find many different models on this specific task on the Huggingface-Model page. So in NLP, you can just filter for fill mask and find many different models here. If we go with the most popular one, we can scroll down in the model card and find that there are many different models in this area which we might use. And then also the way how to use it is described down here. And we can take the code snippets directly and use it for our purpose. So we are just importing pipeline from transformers. And then we need to create an instance of our pipeline. So here we just have to fill in the task, which is fill mask. And then we can use this pipe and provide our sample sentence. And the sentence is just the pen is, and then we put the mask around mightier than the sword, and we get the results. So here you can see now that the most reasonable results are stronger, thicker, bigger, better, and louder. So this is just another technique from the area of data augmentation. And with that, we conclude our lecture on data augmentation. And you have seen and learned many different techniques on how you might apply this to your own needs. Thank you very much and see you in the next section. Hello and welcome to this lecture. Now we are going to talk about a very interesting new LLM. Now we are going to talk about Claude. So let's find out what Claude is. Claude is another LLM, another large language model, and it was developed by a company called Anthropic. This company was founded in 2021, so quite recently, and a bit in contrast to OpenAI, they are laying more focus on safety and interpretability of the model. And there's also quite some overlap. It is led by former OpenAI researchers, and they have released just recently their Claude 3 model family, just right now in March 2024. And as you can see here at the right hand side, this is coming from their webpage. You can see that it's even outperforming GPT-4, which is the benchmark at the time of this recording. and it's outperforming GPT-4 on many different benchmarks. So this is really very promising, and we are going to check that out later. In the family, they are having 3 different model sizes. This is also quite normal nowadays, that in a family you have models with different sizes and then with different capabilities. So typically the smallest models are the cheapest, the fastest, but also then of course the performance is not as good as the largest models. So the largest model is called Opus, and the other ones are called Haiku and Sonnet. And Opus and Sonnet are available in many different countries. You can find that out on their webpage, and Haiku is going to follow as well. And here at this graph you can see the performance, or you could also call it intelligence, based on some benchmarks, versus the cost of 1 million tokens. So here you can see how these different models are performing. And one very good approach to check out different models in a very independent and stable way is called Chatbot Arena. You can find it under this URL. And the idea is the following. You have 2 different models which are competing. So you can enter your prompt and then send, and then the Chatbot Arena is selecting randomly 2 different models and providing the output to you. But at the beginning, you don't know which model is underlying, the left-hand side and the right-hand side. And then it's up to you, it's up to the user to decide if the answer from the model A or from model B is better. Or there might be also a tie, or you could also return that both are providing bad answers. So this is a really good blind study, because only after the user has evaluated the results, you are going to see which was the underlying model. And this is important because there might be some biases. For example, if somebody, for whatever reasons, does not like company A, which is developing that model, that could directly affect the rating from the person. But that cannot happen since the user does not see in advance which model is providing which answer. So this is a very good independent way of studying it. So it's following the double-blind study approach. And this is also a very important concept coming from medicine. And it's considered to be the gold standard in medical trials, because in a trial you have different patients, and then you want to find out if a real treatment is better than just a placebo. So the patients should not know which one is which. So it's important that the patients do not know what is the real stuff and what is just a placebo. But also it's important that the medical doctor or the scientist does not know which is which. Because there might be also some incentives that the doctor is showing certain preferences and the patients might see that. So it's important that both sides of the page do not know which one is which. And the same holds here with this chatbot arena. You have the users, they don't know which model is returning which answer. So they have to decide independently and just purely based on the answer which one is better. And then the algorithm which is analyzing the result in the end. And that one is also then independent in doing the analysis and creating a leaderboard, as you can see it here. So this is the Chatbot Arena leaderboard. And this is a screenshot from today, from 8th of March 2024. And like I said, the typical leaders currently are the different GPT-4 models. But then already, and it just appeared today on the leaderboard, is Claude 3 with the biggest model. So Claude 3 Opus is directly jumping to rank number 3. And also you can see here a bit down that there is also the second largest model in this family, Claude 3 Sonnet. It's also visible. And then you can compare them basically on this ELO score. So this is the metric which is deciding which is the best model. So Anthropic has really developed extremely powerful models here, which are playing really in the ballpark or even are outperforming the other best models in this field. So it's definitely worth taking a look and making ourselves familiar with Claude. Alright, and in the next video we're going to see how we can get access to the models from an API level and create some Python code to fetch answers via Claude. Thanks a lot and see you there. Hello and welcome to this coding lecture. Now we're going to use Claude via API, and there are just a few steps. The first one is that you have to sign up for the console account. Then we are going to look how to generate the API keys, and we need to explore the API reference to find the reference code, as you can see it here at the right hand side, for using it via Python. And then we're going to test it. Alright, let's get started. Okay, here we are on the page on entropic.com, and here you can see that Claude 3 is now available, and here is also the link to the API. We can just click on Get Started Now, and we are directly forwarded to the console. Alright, and here on the console we can just log in. If we already have an account, I will just use social login via Google. Alright, and here we are. Now we can click on Get API Keys. And I'm going to delete the other one. So we are at the same page. Now we can create our API key. Just click on it. Let's call it my Claude key. Click on Create Key. Then you can copy it. Then I'm going to set it up as an environment variable. So I just looked for the system properties, and here on the environment variables, I'm going to create a new one. I will just call it Claude _API. And in here I'm going to paste the value and save it. Alright, now we have to find out how we can use it. So we can just go and head over to the docs. And in here in the docs you can see the API reference. Now, in the API reference, here we have different client SDKs, and here's the code for Python. Now let's head over to VS Code and take this code. Okay, and here in the subfolder 110 miscellaneous, I'm going to create a new file. Let's call it Claude test.py. And in here we can paste the code from before, and you can see already we need to install the package Entropic. And at first I need to activate the environment. And now we can install the package, pip install Entropic. Good, that should be covering the package. We can just test it and just load the package at first. And now we need to get our API key. For that we are going to use OS, because we are going to fetch it from the environment variables. And we can get that os environment.get, and we called it Claude API. Alright, that should be it. Now we can just run it and see if it's working. And this is the return. So we have now set up our client, the submodule messages and create. We have passed the model. We are using here the largest one. Maybe we should, due to pricing, use another one like the Sonnet model. Then we can also specify parameters like the maximum number of tokens. And then we are setting up a message, which is looking very much like the setup of OpenAI. So we define the role. We just use a user prompt, and the next key is corresponding to the content. And here we have hello Claude. And then from this message, we can extract the content. And we can even go deeper to just get the message. Message.content at position 0. .text. So that would be it. This is already the response from Claude 3. Now we can play with it a bit more. We can define a bit more complicated questions like the one I showed on the slide set. You want to build a team of 11 players for soccer. I just want to define something which is really challenging the model. So let's say all players are animals. Which animals in the different positions yield the best performance in a tournament? Now let's see how it performs on that one. And here we are. So we see, while it's fun and creative idea to build a soccer team with animals, it's important to note that in reality animals cannot play soccer in an organized manner. So let's maybe make it a bit nicer. Okay, that one is better readable. So it's coming up with the different positions for the goalkeeper, a gorilla, which is good. I ran it earlier. There I got an octopus, which is making more sense even. Then we have cheetahs, elephants, kangaroos, honey badger, okay, horses and dolphins. Yeah, interesting compilation and yeah, a fun way of challenging the model. Great, and now we have covered nearly everything. Now you know how to connect Python with it and use it from some API level. If we head over again to the console, then you can just go to your account and check out the usage. And here on the usage page, you can see how much you have already used. And it's separated into input tokens and output tokens. So it's really good for checking out how much you have used already. And then if the two requests I just ran before cost me 4 cents. If I want to make it cheaper, of course, I can use the different model. I can use Sonnet instead of Opus. And if that initial money, which was provided for free to me, is not enough, then you can, of course, upgrade to other plans. Good, and that is what I wanted to show you on Entropic's Claude. It's really promising, and I want to follow up on that one because it's providing very good results and it's playing really in the same ballpark as GPT-4. So yeah, I can just encourage you to check this out and keep it on your radar. It's making a very good first impression. Thanks a lot and see you in the next lecture. Hello and welcome to this lecture. Now we're going to talk about a topic which is called LLM functions or tool use. with LLMs. And let's start with the problem that we want to overcome. The problem is that you have a user, or you are the user, and you want to ask a model a question that it cannot answer it directly. And the main reason for that one might be the cutoff date. If we take a look at the Chatbot Arena leaderboard, we have seen that in an earlier lecture. Then we can see here all the different models and what the current leaders are. But then if you take a look at the right, you will see a column called knowledge cutoff. And that is basically the end date of the training data, which is going to be part of the training of the model. And you can see here, for example, for GPT-4 Turbo, for the first one in the ranking here, the last date is December 2023. So if you ask the model anything that was happening afterwards, then the model won't be able to answer that. And you might have seen that already in action. So how can we overcome that? We will find out that in this lecture. The other reason why the model might not be able to answer it is that it doesn't have access to the data at all. So first of all, it was not part of the training data due to the cutoff date, but also, for example, because it is non-public data. You're working inside a company and you have your databases, and this information is not available to the large language model. So one way would be to send as much data as possible during the prompt that is sent to the model initially, but that is not feasible for a reasonably large data set. It's only workable for a very small data set, but even then it's not efficient. So a better way is described in this lecture. Let's take a look at the solution. We are having here our question that is not possible to be answered directly by the model. So we are going to make use of a functionality of the large language model to generate the function input parameters, which is then fed into a function, a Python function that is able to retrieve additional data. So the LLM tool is at this point purely for extracting input parameter for a custom function. And then once we have retrieved the result from our own function, we can then pass the result to the large language model in a normal prompting way and ask the model to generate some final answer. So that's the approach that we are going to follow here. And now we can take a look at some example. So here's our workflow. And in the app that we are going to develop, it will look like this. The user is getting a prompt and describing, for example, a company and what it is doing, because the user is not aware of the specific ticker symbols or even the name of the company. So it's a very broad description of the company and what it is doing. So the user is saying they are very successful in selling GPU chips, and the LLM function is finding out that the company that is looked for is NVIDIA, and it's returning this information in a JSON, and we are able to extract that because now we have a structure that we can use like normally with Python, and then use the ticker, pass it into our own custom function. The custom function is for retrieving the stock price information. So we pass in the ticker symbol together with some start and end date. And as a result, we get some data frame of which we can extract the price at the beginning of the year and the current price. And then the model can formulate some nice answer around the company, what the company is doing, what the stock price at the beginning of the year and now is, and then formulate that in a very nice way. So that is what the overall process is looking like. And in the coding lecture, we are going to develop this complete interface together. But for now, let's take a look at one specific part. The main part here is actually this LLM function generation. And this is something that is possible for all different large language models. I'm going to work with Claude 3 for this example. And in that case, we need to pass this information in a parameter called tools, as you can see here at the right. And then there are a few parameters required, like for example, the name, the description, and the input schema. So the name, this is just the internal function name. Then we need to provide a good prompt for the description. And in the input schema, we are describing the parameters. So we want to get back a parameter called ticker, which is of type string. And then we can also provide some description here. Afterwards, we can also specify this one to be required. And if we want, we could even add more tools and more functions into this list of the different tools. But in this case, we are just fine with this one function. And we can extract the ticker symbol in that way. So from the content of the response, there then is some input with a key called ticker. If you want to read more about this, you can just read the documentation of the developers. And for now, that should be it. In the upcoming lecture, we are going to develop a small web application, which is going to be able to answer all of this. And you will see all of this in action. Thanks a lot and see you there. Hello and welcome to this lecture. Now we're going to implement that together. And for that, please navigate to the folder 110 miscellaneous. And there you find the script which we're going to work with. It's called stock price app. And before we dive into the explanation on how this is working, I'm going to show you the final result. So here you can see the final app which we are going to create. We are starting with some description and task for the users to describe the company you want to know the stock performance for. And now we can describe what the company is doing. They develop computer chips, mainly GPU, and are listed in Nasdaq. Something like this. So it can be a broad description, and the function should be able to extract the ticker symbol as it does here. And then it's returning this ticker symbol. A function for downloading the stock performance data is run. Then the result of that one is passed to another LLM call. And then this one is formulating this nice final answer. Good. And that is what we're going to develop now here together. So for this, we are going to use another package for creating this nice chat interface, which is called Panel. So here at the beginning, you can see at first which additional packages are going to be used and which are to this point not yet part of the requirements txt. So please install just via pip install yfinance, Anthropic, and Panel, because these three are needed in this lecture now. And we are then importing these yfinance as yf, Anthropic, and Panel. Datetime and OS we just need for fetching the current date. And for fetching some environment variable, we are going to use OS. And then we just need to call pn from panel dot extension to be able to use the chat interface. And then we need to create an instance for the messaging client from Anthropic, in which we are passing the API key. So make sure that your API key is stored in this environment variable, or for a quick test, you can even pass it directly here as a string, which is not ideal for production purposes. For but for a quick test it might be okay. So this is what we are going to use. Then I defined some constants like the model. I used the smallest one from Claude 3, Haiku, for cost reasons mainly. And then I also defined the maximum number of tokens. And then here we have our user function. So this is the function for getting the stock price information. Here we make use of Y-Finance, and to get the data frame of the stock price for a certain time period, we just need to call the function download, in which we pass the ticker symbol, a start and an end date. And these are the three parameters that I pass to this function, and then I just return the data frame. Then here we have our LLM function. That is the one for extracting the ticker, and it's consuming the description, basically the chat input, the description of the company provided by the user. And we are fetching everything and storing it in this response. And here we now need to make use of this beta of our client. So we need to use beta tools and create the messages in the following way. We pass the model and the maximum tokens, but here importantly, we have the tools parameter. And the tools is a list of different dictionaries. So there might be multiple of these different functions. Here we just have one for getting the stock ticker. And very important is that you provide a very detailed and good prompt for the description. So here I just define the prompt as provide the stock ticker for the most probable company, which is described in the input text. If in doubt which company to choose, use the company with the highest market capitalization. But you might also play with that and try to come up with a better one. And in the input schema, we are defining the parameters. Mainly here we have the ticker. That is our key that we are going to extract afterwards. It's going to be a string, and then also it's required to have some description. All right, and then we also need to define this one as a required parameter, because the subsequent code is building up on that. Good. Once we have that, we just need to define the messages. So we define our user role and provide here the description as the content. Finally, we have the result stored in this response object, and from there we can fetch the content. From this list, we take the first element, and here we have the input parameters. And there is just one, and there is our input parameter, the ticker, that we are interested in. So this one should be a string corresponding to the ticker symbol, like for example, this one. Good. Then we have our callback. Before we dive into this one, let's take a look at the chat interface. So here we have the content from the panel function, because we want to have a nice chat interface. If we check out the documentation of this package, you can see here different chat modules. So chat feed, chat interface. We are going to use this one. And it's set up in this way that we define our chat interface with this class, and it's requiring a user, basically just a username, and a callback. So this is the function that we are going to define afterwards. And then we are just having our send button, where we are describing the first prompt, describe the company you want to know the stock performance for. So if we jump back to here, this is our starting point, which is provided here. And then we also get this bar down here for sending the message with the send button and so on. Good. The username is called LLM here. And we need to show this chat interface as well. This one is just the setting up. Then we show it. And finally, we need to create the panel app in that way that we create this panel column with the chat interface, and we need to start the server. Actually, here is some testing code still in here, which we need to get rid of. Good. Now we can take a look at the callback function. The callback function, you can read more about it in the documentation. It is requiring the parameters question, user, and interface. Here we just need to define the question, and that is basically the description of the company. And we are extracting also the current day. So it's not hard-coded, it's getting the most recent day if you run it tomorrow. And the ticker is then the response from the first function call, from the getStockTicker, from our LLM function. Then we have our ticker as a string, and this one can be passed into our user-defined function in the getStockPrice function. So here we have our ticker. And then from this resulting data frame, we can extract the price at the beginning of the year in that way. So there are different columns like open price, close price, and some others. And the very first one is corresponding to the price at the beginning of the year, since this one is starting at the 1st of January. And then we also have the price at the most recent date. So that's the close price at the end. And then based on both information, we can calculate the performance since the beginning of the year and use all of this information in the next call to the model. So here we have a normal message that we are sending to the model. Again, we need to pass our parameters, model and max tokens. And here we have the user role that we are defining. And the content is describing that the model is acting as a stock analyst. It's asked to describe the company and the performance for the stock with the current ticker, which is having a specific performance since the beginning of the year. They started the year with a price which is extracted here, and the price on the current day was that one. And then it's just saying round the result to one decimal place. Cool. And that's it. Then we are just extracting the text from this answer and providing it to the chat interface. So that is then the result that is provided here. Good. And that's actually how we can set up a chat interface. You have learned that, first of all, but then also how you can make use of functions so that the large language model can consume information and provide information which was created after the knowledge cutoff. And as you have seen, it's not so complicated to set this up. So the main thing is here this LLM function, where we're now defining some tools and defining exactly how the return string should look like and which parameter we want to extract. And then in the second call to the large language model, we are making use of all the information that was extracted and formulate a nice answer. And that's it. That is our introduction into LLM functions. Thanks a lot and see you in the next lecture. Hello and welcome to this final chapter of the course. And in here, everything that is left for me is to say thank you to you, because it was really a lot of content and you kept your motivation and walked through everything. That is really a great achievement, and I just can say thank you for that. But I want to stay in contact with you. So for this, you can see here different ways to contact me. So I'm on LinkedIn, please connect with me. Then you can also reach out to me via my homepage or via phone. Just directly give me a phone call or write me an email. So all of this is possible. And if you like the course, you can check out my other courses here on Udemy. And also I want to make you aware of that there are other courses I'm offering in-house or remote. So if you want to see me as a real person, you can just reach out to me and we can discuss some details. And I cover the complete data layer. So if you need some introduction into Git or SQL, I'm your man. But also on the programming layer, I work a lot with R and Python. So I can provide the basics on R and Python and go all the way up to data science and machine learning. And with this, we are really at the end of the course. And once again, thank you so much for joining the course and supporting me. And I hope to see you soon. Bye.